And welcome to day 2 of the 2024 Engine Performance Expo. I'm Joe Costello along with Lake Speed Jr., Dennis Borum, joining us here at the start of the show as we kick off another day of high-speed information technology about the engine trade. We had a great day yesterday, Lake, but day number 2, it's going to blow it out of the water.
Absolutely, just keep it higher and higher levels. It's a beautiful day here today, East Tennessee. Off-season time, and last night Project Pontiac was standing up here, and the guys have been doing some work. It's laid down here. It's still at S69, but it's going to get at H85. It's going to get honed later today, because we got to do for you what this guy did for me and my dad, right? Because if you were watching last year, if you haven't watched last year, later today, after you finish hanging out with us today, you should go back and watch some episodes from last year, because we took that old 20-year-old Ford NASCAR engine and, man, you put the tune-up to it.
That's right, brought it to life.
So it was, when we first dynoed it, remember we had been sitting for 20 years and it had run and overheated a little bit, and we did figure out why it overheated eventually.
Yes.
But it was down like a lot. It made like 470-ish.
Yeah, it was stupid.
It was bad.
Yeah, it was really bad.
But once you worked on it.
Yeah, got it to where better than what we thought, I think.
792 is the last number I remember.
Yeah.
That's a pretty big jump right there.
That's right.
I hope we can duplicate that kind of increase.
That's right.
With the old Project Pontiac. But really, watching that process and now trying to duplicate something similar, we kind of deviated because our block was broken and we couldn't just do the apples to apples comparison. Right. But it's so much bigger than just building an engine, right? Like, everybody's interested. Everybody wants to see and hear, and that story in that video does so well of watching the arc of what it was to what it became.
Well, we want to do for you what Dennis made possible for me and my dad, is to take that old car and be able to get that engine fixed back up. And that whole process by itself was so much fun. Working with the guys at Comp and at Edelbrock and all the guys in your shop, CP, and everybody that was involved to take that old engine that looked like it was going to be a boat anchor, and then make it almost make 800 horsepower. I wanted 800 so bad to come 8 horsepower short of 800. Is like, there's got to be something left. But it was so incredible to do that, and then to go put it in the race car and go to the racetrack and hear that thing run again and see the smile on Dad's face. Yeah. It was pretty incredible. So I'm hoping we get to do the same thing for you.
That's the plan, and we're working on it, and the smile on Dad's face. Like, there's nothing better than that, because he's the one who got you into this world, and everybody that you communicate with, touch with your passion for oil, for engines, it's all his fault or responsibility, one way or another, good or bad.
Well,
right? Mr. Lake
especially sweet to me that this guy was building engines for my dad in his career. Yes. So that it's not like, okay, well, it's somebody else adjacent. It's like, no, this is full circle coming right back around.
No, it's pretty special right there.
Yeah.
And to work with everybody, I think we all learned something from it about people and what we're doing. So that the experience gained from it was great. And I think you had the same thing in this, all the people coming together to do it.
Yeah, it's cool.
Pretty awesome.
Humbling. It's certainly been humbling, and watching this thing go. Saw Dave last night in the restaurant, and he's like telling me about different issues, and I'm thinking, oh my goodness, like, all of this is right. I have put this upon people, but not really. And he was just so excited about it. So we're going to keep progressing throughout the day on Project Pontiac. We're going to meet some celebrity guests. We're going to talk some technology, and we're going to just kind of keep up with the entire process throughout the day.
Well, you just kind of mentioned something that everyone comes together and contributes, but that's what the expo is all about. It's all of these people coming together, sharing what they know, and we all benefit from that exchange of ideas through the Engine Performance Expo, which is what makes this event so special. Which is, I'm glad you tuned in. I'm glad you're watching. Again, come hang out with us. It's going to be fantastic all day. But to start off the day, let's go watch this video of my dad getting back on the racetrack.
If you went back and watched a NASCAR race from the glory days of the late 1980s, Lake Speed is a name that you would see. Lake was a regular in the Winston Cup Series for over 20 years. Prior to that, he was a world champion go-kart racer. In 1986, he built a shop in his backyard and started his own race team. As you've seen on this channel before, we showed you his entire race shop. That's still in his backyard, where he has 2 cars left and 2 engines. They have not been touched in 20 years. He made us a deal. He said, you know what, you take that engine, get it freshened up, make it make some more power, put it back in the car and I'll drive it again. And he's 75 years old. So we took it over to Dennis Borum at Pro Motor Engines. Dennis has been building NASCAR engines for over 30 years. Over the last several months, we have been all over the country, documenting, sourcing, and explaining the parts that we've used to freshen this 20-year-old engine time capsule of NASCAR technology up to some more modern stuff without changing the bones of the engine. It's still the same block, the same heads, the same crankshaft, the same rods. It has new pistons with a modern design, a new camshaft with modern design, and a very specific cylinder wall hone and ring package of modern specs. We're here to blend nostalgia with technology and get a legendary racing driver back in the seat of one of his favorite race cars.
All right, Joe, been 20 years. You got about 100 more horsepower than you ever had before. About 20 more years experience for me. You've been a good old boy. You've been close so many times. Can't wait, Father. Can't wait to put you on the racetrack again and let you show me what you got. You got special tires, some Goodyear, new camshaft, you got new pistons, piston rings, the latest and greatest of everything, Trek oil pan. You got some special fuel for you. Gonna taste good, you're gonna like it. Got some slick oil that's so slippery you won't even know you're running. Been my favorite race car, always has been. I hope you're ready, because I am.
Did you have a talk with Job this time when nobody was around?
No, after the last trip, talking to Job owes me one now.
Back to the track, and you could just see that great energy, the emotion. Yeah, it was a lot of work, and there's some numbers, and you made X amount of horsepower, but it wasn't anything about that. It was about seeing your dad get back in that race car.
It was awesome. Every time I watch that video, the hair stand up in my arm. The sound of that engine and him going through the gear shifters at that racetrack, whew, it was something else. It was awesome. I mean, it was a bunch of, a lot of hard work. I mean, there were so many people, like you were saying yesterday, feeling like the driver of the race, trying to remember all the sponsors.
Yes.
There were so many people.
I forgot to mention Keith Wilson, but amazing
yes.
stuff. And we've got Darren Morgan here joining us, guys. Talk about going heavy hitters right at the start. And he's got a laptop, and he's going to do a presentation. And I'm Darren, what's it about? Hemi hand grenades? That's right up my alley.
I can see this. I'm like, okay, I'm all in. Yeah, so it's like, yes, we're starting off the day full horsepower, right? Engines making power, and then we got this guy, because airflow is what it's all about. We can't burn it if you don't get it in and you're the induction guru, so I'm going to shut up and listen.
Yeah,
and learn.
exactly. This, Dodge Hemi Challenge, U.S. Nationals, one of the biggest single one-off events for cars that were never designed to go that fast, going well beyond the dreamed capability when they were manufactured. It's one of the greatest events in all of the drag racing world. Happens each year at Indy. Tell us a little bit more.
Factory engines were never meant to do what we're doing, ever. We push them to their limits, and then a little bit more, and then a little bit more, and then a little bit more, until basically they end up as eggshells. And I'm going to go through not only the foundry process of casting these cylinder heads, which are cast at Profiler now. I'm going to show the cores and everything else. But we're going to go through all the machining techniques that we use and why we do what we do as far as developing these engines, primarily the cylinder heads and intake manifold, which is my job.
Okay.
So this is the foundry. This is at Profiler, and this is a core box. You get to see the intake cores going into the core box itself, and the exhaust cores. And there in the center you see the water jacket. Now these cores are painstakingly put together, glued together, and this is the factory cylinder head. This is what, if you call up Mopar and you ask for a 426 aluminum cylinder head, this is what you're going to get. This is how they are cast. And the Superstock Hemi rules dictate that you must use the factory casting. You can't use an aftermarket casting. They have to be basically the same exact thing that you could buy in 1964 or 1968. But Mopar, in their infinite wisdom, has developed race parts for this class. The blocks are now thicker, stronger, and heavier, I might say, as well as the cylinder heads themselves are also thicker, which allows us a little more latitude to push them even further.
So it's the same design, but you just are adding a little more material when they're pouring it.
Yeah. Yeah, I'll show some actual cutaways of the cylinder head and the relative thicknesses throughout and show you what we go through. This is how I like to start with a cylinder head. When I'm developing anything for any class, I want the raw cylinder head. And normally you can only buy the cylinder heads with seats and guides already installed. Well, that for competition use is limiting, because a lot of times what we'll have to do is qualify the core. So basically you have a core with a water jacket and the ports going through. You have to basically machine this thing up to where the thicknesses in certain areas are sufficient enough to do what you do. So in other words, if you're just going to square the whole thing up and machine it like the foundry does, that would be insufficient for what we would use it for. So what we'll do is we'll actually jog the head fore or aft to make certain walls thicker or thinner to optimize the situation.
And that's just because when you pour something, they're not all the same.
They're not all the same. And there's shrinkage and core shift. In other words, the water jacket itself is a very thin, let me back up here a little bit. The center, what you see there in the center is the actual water jacket core. When you pour the aluminum in there, that's going to be the hollow area. And you can see the little holes there, that's for the valve guides or the spark plug hole. Now that is a very fragile piece. And if it's not glued down properly, what will happen is when you pour the aluminum in, it will float up on one side or the other, or the whole thing will float up. So these things are all glued in place. And if you get a water, and this is pretty common, or used to be very common, called water jacket core float. You pour the aluminum in there and the sand would float up. So that makes your roof thin and your floor thick, or vice versa. So now they've pretty much done away with all that. They've been able to cast these things uniformly and get the water jackets and everything small enough. Now, nowadays we have 3D printing. You know, we can 3D print water jacket cores that were absolutely impossible to make 10 years ago. They're very fragile, very small. It gives us thick walls everywhere. It allows us to do things that we couldn't do. But in this casting, that's not allowed. It has to be a factory OEM casting for this class. I'm going to go in a little bit about the differences between the modern 5.7 Hemi and the old 426, 64, 68 Hemis. And what they've done to actually increase its efficiency and power overall. Now, the engines, some of the, like the drag pack engines, the elephant engines that we build at BS, those things will make anywhere from 1,500 to 1,700 horsepower supercharged. And that's a standard, standard drag pack engine, 1,300 horsepower, that's nothing. I mean, yeah.
Just throwing out 1,500, 1,700.
The reason you can squeeze that much efficiency out of these things, that would be difficult to do with the old Hemi, is because they've optimized the chamber design. And here you see that the chamber isn't the old 45-degree hemispherical, just a globe cut off. It's a hemispherical chamber. Even at Glidden's, what we would do with the Ford Hemi heads is weld the combustion chambers up and make them this exact shape. I mean, this is what he did.
Standing the valves up more and basically making
We couldn't stand the valves up. We didn't stand the valves up then.
Okay.
But what we did was we concentrated more on the chamber than anything else. And now we have 2 spark plugs per cylinder, which in the Hemi is mandatory if you're going to squeeze any level of efficiency out of this thing. Because if you have a big chamber and the spark plug's on one side, the flame propagation is 360 degrees away from the plug, and then it moves across the combustion chamber. So if you have a lean or spot in that combustion chamber and that flame front moves across that chamber and pre-compresses that lean part, bang, off it goes. But if you have 2 flame fronts, the ignition timing is 10 degrees less, the flame front is much faster, and the efficiency is greatly increased. And here, this is what you would buy if you just bought a 5.7 chamber. And you can see that everything is brought in. The chamber surface area to volume ratio is reduced. It's down as much as you possibly can. As opposed to, this is a prototype I'm working on right now. We're doing 2 sets of iron heads and 2 sets of aluminum cylinder heads for individuals in this class. And this is a very big chamber. Very
giant.
Inefficient chamber. And that is one of the problems with the hemispherical cylinder head design. Its assets are that it has equal pressure recovery around the valve. When that valve opens, it sees open area all the way around it. And the decrease in airspeed is uniform all the way around it. So it has a higher CFM per square inch of valve area. I mean, it flows more air per unit area than any other cylinder head ever designed, period.
That's its strength.
That's its strength, exactly.
Okay.
That's its strength.
Not the fact that it's this giant globe.
But then you have to put up with the fact that the chamber surface area acts like a quench. It tries to put the fire out, So what you do is you will CNC this dome or this combustion chamber into the cylinder head, and then you transverse that onto the dome. And then what you will do is you will manipulate that shape to increase the flame travel in these chambers. So instead of having a perfect hemisphere that fits up into the chamber, what you'll do is you'll bring the sides in and the top down. So what you're doing is you're literally forming this crevice that opens at the top, and you're trying to harness all the air-fuel mixture right over that plug as much as you can. And by bringing the sides in, you're shooting the air-fuel mixture up to the plug.
Push it in.
Yeah, and you're talking 5-10 horsepower here. You're playing with up at 9,600 RPM. I mean, just getting it just a little wrong has a big effect.
Is it like almost like a giant quench? You're trying to push everything into that area near the spark plug so you can bang it out and you get that great burn.
Yeah. Try.
That's cool, man.
Try.
Yeah.
We
Try. Yeah.
I mean, as opposed to like a pro stock engine with a 45, 46 cc combustion chamber with all the flat area that just shoves everything to the bore center. This is really, really difficult. It takes an immense amount of time and energy to produce these cylinder heads, up to 150 hours a set.
Whoa.
Yeah. And I'll get into the welding later. This is what I have to deal with. It's basically an eggshell from the very get-go. This is a cross-section of a Hemi, a stock 426 Hemi cylinder head. As you can see, the wall thickness it's not gracious, they're thin. So you start porting on this thing, you're going to end up with very thin walls. And this is why I call it a hand grenade, because by the time I'm done with this, you're going to be shocked at how little is left. Basically what I do, the super stock rules dictate that you have to maintain stock intake port CCs. That intake port, exhaust port, and the combustion chamber have to hold the same volume as the stock engine did. So how am I going to make this port bigger in order to flow more air?
So
Yet
the
still
total amount of
maintain-
CCs
yeah,
has to be the exact same.
Exact same.
So I'm assuming you're going to try to make a giant funnel out of that to increase airspeed.
I try.
You try.
I don't get there, but I try.
Because you don't have enough material.
I don't have enough material. So what we have to do is, if that runner has to hold the same volume as a stock engine, if you sink the valve into the cylinder head, you can enlarge the cross-sectional area, right? And thereby it holds. If you mill the intake flange, you can again enlarge that cross-sectional area. There's no way to make this cross-sectional area large enough to support the flow potential and RPM potential of the engine. There's no way to get there. 50% of my time on a prototype is working out trying to get the cross-sectional area as even as I can. In a perfect world, what you would want is the throat to be the fastest part. And then everything, like you said, to funnel up. It gets bigger as it goes out. You can't accomplish that here. It's absolutely impossible.
Ooh.
This is a 5.7. This is the modern Hemi.
So this is the factory.
Yeah, this is the factory 5.7 Hemi, a cross section. So what they've done was, instead of the old 45-degree Hemi, they've stood the valves up, which shrinks the combustion chamber volume, increases flame travel, flame speed. So there they've gotten some efficiency as well. And the valve train itself all works out. So now we're going to get into volume and length. Back in the 60s and 70s and even 80s, people would say, well, I have a 355 cc port, or I have a 300 cc port. That metric is no longer used. It cannot be used because back then you had an OEM cylinder head. Let's take a 23-degree small block Chevy, okay? Well, you're not going to modify that thing too much. And the bigger you can make it, the more power or the RPM potential of the engine is going to go up. The problem is, back then you couldn't make them big enough. So everybody started bragging about, well, I have a 220 cc or a 225 cc. And what that related to was the RPM potential of the engine. And then the aftermarket in the 90s allowed us to vary cylinder head design wildly. We could do anything we want. And now there's a plethora of cylinder head designs with different length runners. So you can't say, well, I have a 355 cc runner anymore. Because let's just take, for instance, a standard big block Chevy. You go buy a standard conventional big block Chevy cylinder head from Brodix versus the newer 20-degree cylinder heads from Brodix. Well, the 20-degree cylinder head is 5/8 of an inch longer port length.
5/8 longer?
Yeah, than the original conventional cylinder head. So a 355 cc port in a standard conventional head would be 400 cc's in a 20 degree. But cross-sectionally, airspeed wise and cross-sectionally, it's the same. So this is where people will get off on that.
Sounds like CCs are like RA for surface finish. It's a number, but it doesn't tell you the whole story.
And here what I've done is I have taken an 18-degree, an SB2, and a Brodix canted valve. Mm-hmm. Both cylinder heads hold the same volume. Both cylinder heads flow exactly the same, but their length differs quite a bit. So if you go to the far right of this depiction, you'll see that the airspeed varies wildly. So if you look at this, the 18-degree can hit 9,000 RPM. The SB2 would be about 8,800, and that Brodix canted valve would be lucky to get past 7,000 RPM.
Okay.
Here's a depiction of like a big block head. The Brodix Big Duke both versus a Profiler spread port. Both have the same volume. Both flow the same amount. The average cross-sectional area varies drastically. There's 500 RPM potential difference between these two cylinder heads just using CCs to base a cylinder head on. So that metric can no longer be used. So now we'll get into how much power can you get out of a 426 Hemi? Well, they're not actually 430 or 426, they're actually 435 cubic inches because you're allowed 60 thousandths overbore and 5 thousandths plus stroke. And if you give rules to a racer, he's going to push them.
Right.
Yeah. So if they allow you 5 thousandths over stroke, that's exactly where you're going to go.
Yeah, exactly.
And if they allow you 60,000, that's exactly where you're going to go.
Yeah.
Because if you're making 2 horsepower per cubic inch, every cubic inch is 2 more horsepower.
Right. Yeah. Exactly. Yeah.
So what I did is you can do this simple calculation for a 435 cubic inch motor. These engines do make peak power at 8,800. And they're limited at 8,800. You can't get past that. And I'll explain why here in a little bit. But the required airflow to attain 8,800 RPM is 473 CFM. Now these engines have a 250 stock valve. And they flow 475 CFM. Because a Hemi is the most efficient flowing port that you could possibly get. This is what they actually flow on the cylinder head. Now, when I say I take most of my time in developing the ports, getting that area as big as I can, usually in a normal port design, you'll have the throat at like, let's say 90% of the valve, and the opening upstream would be like 100 or 105% of the valve. It would increase and taper. And here, you can't get there. You just can't get there. I spend all my time just trying to make the average cross-sectional area the same as the throat.
Oh, just keeping it the same.
Yeah.
So it doesn't taper
because of it's
small.
Yeah. Because you don't want anything upstream smaller than that throat.
Right.
So that is the limiting factor right there. This is why these engines are RPM limited. They are cross-sectional area choked off. Once the airspeed reaches a certain point, that's it. That's where it's going to make peak power, and the whole game is to try to carry it out. Try to carry that peak power as far as you possibly can. 20 years ago, they were spending these things 9,000 RPM, and now, because of advances in valve train, we can shift them at 9,600. But doing that comes at a severe cost.
Price, yeah.
Yeah. So let's look at a standard cylinder head. If lift LD ratio here, you noticed off to the right of this LD, that's lift to diameter. In other words, if you have a 250 valve and lift it 0.23 times that diameter, it should flow about 90, 91 CFM per square inch of area.
Got it.
Okay. And if you lift it 0.4 of the LD, it should move anywhere from 117 to 118 CFM. That's with any cylinder head. It doesn't matter if it's a wedge, a cannon valve, or anything else. Other than a Hemi, that's it. You aren't getting any more than
That's
118.
just the choke of the area, right?
Yeah. Yeah. Once you reach a certain airspeed, that is the limiting factor. And any cannon valve engine, if that's the target, to hit 118 CFM per square inch of valve area by 0.4 LD ratio.
Okay.
So if anybody wants to know how much flow can you actually get out of a cylinder head, now you have it. Now the Hemi, being the most efficient flowing design ever conceived by man, it will actually flow 375 at 0.23 or 0.25. So it's 94 CFM per square inch of valve area. And they'll hit 119 to 120 CFM per square inch of valve area up there at 0.4, which is astounding. You would never be able to achieve that with a cannon valve engine or anything like other than that. But that's the limit. Now, if I could actually take that limited 475 cubic inch or 475 CFM that I'm getting out of the cylinder head and make everything upstream of the valve perfectly sized, like I can in Comp Eliminator or Pro Stock or any other class, then the engine would peak power at 9650 and you would shift it at 10.5. So if I could do it, but I can't. So that shows you how limiting that port cross-sectional area is. So in an unlimited, I could shift it at 10.5 And now that this cross-sectional area is so small, it knocks it back down to 96.
And that's just because of the velocity,
Yes.
because you can't go faster than that.
Yeah, it hits what's called the mean inlet Mach number. It hits 690 feet per second at that point. And once you hit that point, they call it a choke. It is a airflow choke, but it doesn't. The power doesn't stop. It just stops increasing. So basically, the power band will come up and nose over, and the idea is to carry that out as far as you can.
Right.
So let's say you're making peak power. They'll make about 1,000 to 1,025 at 8,800. If you can carry that out and still have 990 horsepower, 500 RPMs later, you can move the whole power band up and average more power. So you're basically dropping back down into 100 more horsepower because you've raised that whole thing up.
Yeah. You're trying to limit the losses at this point.
Yeah. One of the other limitations is the valve train. This is one of the reasons why these things are hand grenades. Here you
Okay, so the one on the left is the original 426 factory. The one on the right is the modern 5.7 factory engine.
Yes.
Okay.
And you can see the valves are stood up. Mm-hmm. But what they've done in the modern cylinder head is you'll see that the lifter bores, the cam is raised up way in the block, and the lifter bores are splayed out. Mm-hmm. So what that does is it makes the valve train what we call in plane. In other words, the rockers and everything are directly in plane with each other. Where the old 426 Hemis had the push rod way down in the block, and everything is out of plane. So managing the valve train dynamics on these engines has always been dicey at best. And if it wasn't for Jessel really working with these racers, we would never be able to hit 9,600. And plus, we have two push rods going right by the port.
Right.
So that limits me as well.
And now you have another physical limit. You have your rule maker, then you got that daggone push rod hanging out over there.
And the push rods actually protrude into the port.
Yeah.
And the newer valve trains, they've moved the push rods out, but that has a detrimental effect because you're moving things out of plane again.
Yeah.
You know, it's like, okay, do I sacrifice the valve train to get the port volume, or do I get the port volume and sacrifice the port for the valve train?
Yeah. What side of the sword do you want to fall on? You're going to bleed either way.
This is a stock valve train, basically. And you see everything is, you know, you couldn't get that past about 7,800 RPM without incurring some major issues.
Just a lot of mass there too.
Oh yeah.
I mean, not only do you have the geometry issues, there's a lot of mass in this. Yeah.
This picture, it's hard to see, but you know, you have steel, you have a long rocker arm on the exhaust, so you have a steel rocker arm that's just a little razor thin all the way. This valve train took 1.5 years to develop. And what you don't see here is the standard Hemi valve train has 5 bolts going down right through the center, and that's all that's holding it.
Just 5.
Yeah, so you have a valve train this wide with push rods on both sides held right down the middle. So the whole thing wants to sit there at high RPM.
You don't need to be Danny Jessel to realize that's a bad thing.
That's a bad thing. So later on, iterations use the extra spark plug hole as a stand and triangulated 10 bolts. That has 22 bolts.
22?
Yeah.
Wow.
That has 4 pedestal stands, bars underneath the intake, and things you can't even see.
That's cool.
That took the engine from 9,400 RPM stable to 9,650.
Yeah.
And that
just doing the just doing that.
That's the difference between 159 miles an hour and 160-150.
How about that?
Unreal.
Yeah.
But what we had to accomplish that, raising the RPM range, is what has made these things hand grenades. I mean, racing one of these engines is like pulling the pin on a grenade and just playing with the trigger.
And that's why people show up to Thursday at the U.S. Nationals to see these cars. In this race, there are so many people, and you deal with them on a regular basis. They spend a ton of money, a ton of time, a lot of effort goes into it for one event a year. And then the car goes away and they go back to work and try to figure it out again. And that's why you got to go to the U.S. Nationals, folks.
Yeah.
Spending $80,000-$100,000 on one of these engines is not uncommon. I mean, it's just the amount of work that goes into it. I mean, just welding them alone, you've got 2,000 in welding and then 100, 150 hours. You've got $16,000, $17,000 in labor and welding before you even buy parts. So,
You want to play the big boy table, there's your ante.
Well, exactly.
the new 5.7, shorter push rods, better valve train alignment, everything's in plane. And now you look at the old block, the push rods are next to the cylinder. You have a lifter like this, you have a push rod leaning over, you have, everything is not right. So everything you do in this area is made to optimize, move the bores over a little bit, get rid of some of that angle differential. And the old blocks have to use a stock core cam, which is also limiting. And the newer blocks, you can put a 60 millimeter cam in those things.
Oh, wow, okay.
So some of the Elephants, some of the bigger engines, you can put 60 millimeters in there, no problem. So that allows you have a better valve train, able to lift the valve higher, and you have a longer rocker arm ratio, fulcrum length.
Right.
Because the fulcrum length on a stock Hemi is really, really short. So let me go to the board real quick.
Yeah, go for it. Isn't this great? Oh, this is awesome. This is a master class.
this is how
I hope y'all are enjoying this because I'm loving this.
Yeah, this is out of control. We got Darren Morgan at a whiteboard.
Right, this is cool. This is so cool, yeah.
So if you look at the arc on this as opposed to this, so basically you've got this much on the valve stem. That roller will move this way and then all the way to the other end and then move back with a short rocker arm because you have only so much arc to work with. So as you're opening the valve, this tip is moving across the valve and then moving back. And at a certain point, you're going to stand that rocker arm up and any more motion is not going to do anything. All you're doing is moving that roller back on the valve and wasted motion. So on the newer stuff, you can get 1-inch lift, and on this stuff, 950, 965 lift is about as much as you can squeeze out of it. So that's another limiting factor. Because the 60 millimeter cores, as opposed to this, will automatically raise the RPM range 1,000 RPM, just with increased lift, decreased seat duration, increased valve speed. You do all that, that's 1,000 RPM.
Just 1,000 RPM.
Just
No big deal.
1,000.
Yeah.
And you're talking
This
about
is old school, and I love this now. We got some stuff in the port. Here we go.
that 1,000 RPM nets 125 plus horsepower.
Yeah.
Yeah.
Yeah, just
easily.
Something. Yeah.
So when I say you have $2,000 worth of welding and brazing in these cylinder heads before you even start work on them. Now, by the way, this is an art form. Brazing these cylinder heads up, or I've had some cast iron welded before. But most of the guys that do this are in their 80s and 90s, or retired.
Right.
It's almost impossible to find people to do this anymore correctly, because this cylinder has to be brought up to temperature until it's cherry red, and then welded, and then brought down over a period of time very slowly. And if it's not done correctly, it will cause stress in the casting and crack it. And then all your work's for nothing.
And it's already an egg to begin with.
Yeah. You're going to see an eggshell here.
So this is like a Fabergé. This is basically a Fabergé egg you're building here.
This is what I start with. Now, I want you to notice the intake flange here. It's all solid across there. And we even have a indent or a chamfer where the intake bolts are. This is the exhaust side of the cylinder head. And we raise the ports up about 3/4 of an inch on the exhaust side. Now these are the iron heads. The iron heads take more labor than the aluminum heads do.
Yeah.
When NHRA allowed us to run aluminum cylinder heads, I was like giddy because that allows repairability. And the cast iron heads, if you lose a bearing and that piston hits, it's gone. It's history, it shatters. If you lose a valve, it shatters. Anything happens, these cylinder heads shatters, and 150 hours, it's gone.
Out. Yeah.
They are not repairable. And this is why we do 2, 3, 4 sets at a time.
So you have a spare.
Yeah, you got to have spares. You won't complete a season without spares. I angle mill the flange, and again, the whole idea is to mill that intake flange to gain volume so I can increase that cross-sectional area. I will take that flange and mill it 3/4 of an inch, and then in 150. Now, the NHRA stock rules dictate that the valve cover bolt, the stock valve cover bolt, you cannot mill into those threads. That's my limit.
So you go as far as you can to get to those threads, and that's where you stop.
So if you just milled the flange, you would get half of the volume. So you angle mill it to get that big chunk out of it. And what that does, this is a raising of the exhaust port by the time it's all done. And by the time you get done with that, you can see the flange has holes in it, and those bolts holding the intake manifold on, there's about 5 threads.
That's just enough, huh?
And you can see where it's just protruded into that bolt hole, which they allow it legally. The bolt hole's at an angle, and you can mill into those, but you can't mill into the top and move it. And believe me, people do that. People will weld up that bolt hole and move it in so they could get more off of the intake flange. And when there was some creative interpretation of the rule book back in the late 90s, early 2000s, people were milling the entire intake flange off of these cylinder heads and building it into the manifold like an FE Ford.
Got it, yeah.
Yeah, which is completely, they've made that illegal, which it is.
So the one on the left that's not factory as cast, right? No.
I'm sorry, I'm not following.
The photo on the left, the port on the left compared to the port on the right.
That's welded up. The whole floor is welded up.
That's welding it up. Then the one on the right is the one as finished once you've opened it all up.
I'm still working on that, but it's close to finish.
Close to finish.
Yeah.
Look at that. I can't believe we're seeing this.
This is awesome.
It's like, I'm surprised. Are you allowed to be doing this, Darren?
He's doing it. Don't stop him. It's like Scooter says, right? The more you tell, the more you sell. So let him keep talking.
Here we go.
This is basic. Guys like Westcott and guys Barton, and they've been doing this for 40 years. This is old hat to them. I'm not telling them anything new.
Yeah.
But for the people who don't know actually what goes into these, and you see the epoxy work in there, and I will spend probably a week on this port just trying to get the cross-sectional area to not have a choke in it somewhere and still maintain the airflow.
Just a question real quick on that. Go back, if you don't mind. Would you consider that, because obviously what you guys do at BES, y'all are covering everything, right? Obviously this is a specialty, but you guys do everything.
We work on everything from Briggs and Strattons to Bugattis. It doesn't matter.
There you go. That's what I was thinking. Would you consider this kind of work almost more artisan, old school? Cause I remember when my dad first had his NASCAR team and they were building engines, watching guys like Gail Pauley who worked for Dad. He was doing this kind of stuff, but that was almost 40 years ago. Now you walk in and you see stuff. My time at Gibbs, and everything's CNC'd.
Yeah.
You're not doing this anymore. So this kind of feels like this is like old world artisan craftsman type work.
Yeah, this is a rarity nowadays.
Okay.
Well, that's all because you're dealing with the rule book.
Yeah.
Like all of this is related to the NHRA stock, super stock rule book, which the whole point of it, and the fastest museum in the world is an NHRA stock, super stock race, automotive museum, because they have to be what the factory put out to a point.
Yeah.
And like
stock valve size, stock port volumes.
And what you're doing with that the valve cover hole, it's got to be in the, okay, well, we're just going to cut the bottom off of it. Excuse me.
It's a game of how far we can push.
That's why so many people get out there at 8 in the morning to watch stock and super stock. And this is the highest level Hemi Challenge at the U.S. Nationals, but it's amazing. And call it artisan, old world, whatever. This is what they have to do to circumvent the rules.
To have the advantage, right? It's like how much further can I push it?
If you are going to win races and set world records, you have to be willing to do what nobody else will do or knows how to do.
Boom, that's it right there. That's what we do this for. The whole expo is that right there.
T-shirt.
And the days of doing things that other people don't know how to do are greatly decreased. So that increases, you have to work harder and longer.
Amazing.
Yeah, all right.
Keep going. Yeah. And for those that are wondering, typically our bits go about 20 minutes. This is like all hands on deck. We're getting to the end of this regardless. Like this is unbelievable
However long it takes.
Unbelievable start what we're seeing here.
Yeah.
So the welding, you can see over there on the left, the welding of the intake ports. I'll have about 8 hours of welding to these cylinder heads before I start. And the rod you use and how you preheat or don't heat or quench that cylinder head, these things warp out. So you have to be really, really careful when you weld these things because they're already thin wall castings. It's not like you're starting with something, that's not going to warp out 20, 30, 40 thousandths by the time you're done. And the valve train, getting these things to wind up, working on that valve train, that's the last decade, that's where it's been at.
Valve train.
Yeah. Because 9400, you could go to 9500 and all the parts would end up in your lap or on the racetrack. I mean, it's finite. I mean, these things, if you overshift this engine, the engine comes out of the car. If you make another run, boom. If you hit that 10,000 RPM limiter, you have overstressed the valves I'm about to show you. And what will happen is the head will shrink and they'll pull into the port. Because if the valve train goes out of, if it goes chaotic, which it has a finite limit, and that limit is about 9650, 9700 RPM. And if you hit that 10,000 RPM limit and things start going crazy, it will destroy the valve integrity, the structural integrity of the valve, and it will drop a valve the next pass, 90% chance. Now, a stock valve is to the left, and the modified valve is to the right. Now, this is, again, how we gain another 400 RPM, with hollow stem stainless valves.
Got it.
Now, also, if you think about it, I have to maintain that port volume.
Okay.
You see it.
Yes, sir, I do.
The tulip valve takes up volume, allows me to increase the cross-sectional area. Now, a flat valve will flow better, but I can't use it. So now I have to work that give and take of, okay, how much tulip can I put in there without hurting the airflow and gain the amount of area I need to make that cross-sectional area the same as the throat. That's the game.
That's awesome.
Now the back cuts on that valve, we have to, again, push it to the limit. So the throats are past what we would consider optimal because we have to make them bigger. So we're actually hurting the discharge coefficient enough, a little bit, to gain enough area to raise the power band. We're working on that razor's edge. So the big increased back cuts help turn the air. So with that big throat, you can't set the air up to turn around the valve. So you put those back cuts on there to cut that air to try to move it. This is basically an aftermarket stock Hemi valve. It weighs 147 grams. If you tried to take that past 9,000 RPM, you have problems. Now, if you make it a hollow stem valve, reduce 2 degrees on there, and make it about 150 thick at the base of the radius, yeah, the valve itself is an eggshell. So that's why if you overstress the engine and send that valve train chaotic, it's done. And again, you can do it once. And I seen it at the racetrack twice. Now, my brother was the engine builder at Rare Morrison who built all these. And I did all the heads and manifolds, which we'll get into here a little bit. At the racetrack, he hit the 10-2 limiter twice. And my brother said, get it out of the car. It's going to blow up. He didn't make it out of second gear the next pass. And the pistons were in the oil pan. I mean, this is why I call them hand grenades. And you have a finite set of runs on the cylinder heads too, because as you sink those valves, you say you make run after run after run, you have to freshen them up, you have to go in and recut the seats. Well, that moves the valves in a little bit. So that affects the valve train. You're dealing with multiple compound angles within a Hemi. And any change you make on one of those dimensions is going to have profound effects downrange on the valve train, rocker arm geometry, or what have you. So you're working in this small little window. This is a standard 426 Hemi cross ram manifold. Now, NHRA rules dictate that the carb spacing must remain stock. So you still have to maintain that stagger, which is a major problem because the cylinder to cylinder variation on these engines is profound. I mean, you have to stagger jet. I've seen 10 jets in these things staggered trying to get them even. They're horrible.
Yeah, corner to corner trying to make it,
drilling out air bleeds to try to, it's absolutely horrific. And the manifold design is pretty goofy because two things. One, if you look at the flange angle there, here you have this beautiful flange and then you mill it. Yeah, now you end up with flanges like this. So where before you'd mill a manifold 45 thousandths and drop 50, now it's going to drop 80, 100. So hitting that target of port match is really difficult as well.
Because it moves so much.
Oh, yeah. Wow. And they're goofy as far as the plenum looks because the runners are way down. I mean, the ports are only that far off the deck. So the runners are aimed way down like that. And the last thing you want to do is have a port like this and put a runner stand up. You want that a straight shot. Now, this is one of my manifolds, and it was the best running manifold I'd ever done. And you can see how I incorporated the offset into the plenum itself.
Yes.
And these billet runners, again, you are working with an angle here on the runner. So when you measure a Hemi runner, you're not actually measuring the cross-sectional area because the flange is like this and the port is like this. So the measurement that you get, that's hard to explain. But again, compound angles. These things.
You gotta like geometry if you're gonna work on one of these things.
Yeah. Runner length. Let's get into runner length a little bit. If you notice, those runners look kind of long, but they're really not because I've milled all the port away. The port's only that long. So you look at that and you think, oh man, that thing's not going to wind to 9,800 RPM. But yeah, it's actually tuned perfectly to 9650 is where that is tuned to. And how do you tune a runner length? I'm just going to get into it real quick. You can go to schwartzracing.com and he's made this so simple. This is the second harmonic, which almost all sheet metal manifolds are tuned to. If you look over here to the right, you'll see if you want to turn 10,000, you walk over here and it should be 10 inches.
Oh, they do the math for you?
Yeah, it does the math for you.
I like that.
Yeah. So a lot of times you will, there's two harmonics we use, the second and the third order. You know, the old days in the single plane manifolds, you'd use the third order. And all sheet metal manifolds would be the second order.
Welcome back to the Engine Performance Expo. We experienced a couple of technical difficulties, but Kurt Johnson got on the text machine and sent me a text. Kurt, thank you very much. We've solved the problem, Lake. We've solved the problem.
Well, it was Darren's technical download. It didn't just blow our minds, it blew up the computer too.
Right? Everybody's out there, we're watching, we're getting like to the, Darren is just about to reveal the secret bat cave where all of this is about to happen, and it crashes. But hey, seriously, we've got some inclement weather in the Tennessee area coming through. Who knows what was the reason, but let's get back to it immediately. Darren Morgan, take it away.
Speaking of all the wind blowing outside, let's talk about airflow again.
Yes.
I think we left off here. with
Yes.
this.
Yes.
And basically people, when I talk about orders or harmonics in an intake manifold, people are confused, and I was for a decade, because it's not an easy thing to grasp, you know. The concept itself is, what is happening here? Well, basically, it's a reflection of the signal. So when the valve shuts, it sends a reflection, it turns around, comes in, goes back out multiple times. But each time it goes out and comes back in, its amplitude is lower. It has less energy. So you want to capitalize on that and use the first order you possibly can.
So what you're saying is that when the valve closes, the air bounces backwards. So the air isn't always flowing just in one direction.
Okay.
Right? Because I know
It's not.
Well, because I know Kazi, Kazi's here in the building, right? And years ago at AETC, he showed this video where he had a clear intake manifold runner, right, and put his finger in there, and you can see his finger literally bouncing because it's actually bouncing back the other direction.
Yeah, that is the actual pressure wave.
It's a pressure wave.
Yes.
Okay.
It's not the airflow path itself. In other words, upstream the air is still moving, but this pressure wave is going back and forth. But it's not affecting the actual molecular flow of these molecules going.
Atoms are still moving this direction.
Yeah, this is a pressure wave that moves back and forth.
Okay.
So the air doesn't really stop. It stops closer to the seat, but the air is continually trying to move into the engine.
But
this pressure wave, the air's moving in, this pressure wave bounces back and forth, and right before the valve opens, it raises the pressure at that valve. But when you open it, boom, you get a hit. You get to start that cycle.
So you're trying to time.
Yes.
Oh, no difference. So Dad and I do vintage go-kart, all two-cycle stuff. So we're always tuning the exhaust pipe runner for this same thing, because with a two-cycle, there aren't valves. So you're using that pressure wave tuning as the valve to try to close that valve to trap the air to make the power.
During overlap, when the valve is just opening, there's no piston motion, there's no pressure drop. All you have is the overlap cycle going on. So if you have this high pressure, high amplitude pulse there, you get to start the intake cycle. You get to start moving air into the cylinder earlier. You're not going to make it up. If you don't have a high enough pressure or a lower pressure at this point, you're not going to make it up later in the cycle. You've lost. You need to start it as soon as possible. So the timing of this is perfect, has to be perfect.
This is one of the ways you can have an engine that can create more volumetric efficiency than 100%.
Yes.
If you don't do this right, you're not going to get there.
And you can achieve trap volumes of 124% volumetric efficiency. So that's 24% more than nature would otherwise allow you if you didn't have these harmonics in the system. As well as, it's a long story, but this is the start. You have to time this perfectly. Otherwise, everything else falls apart. So you have the pressure wave that starts it all, and then all the air starts to accelerate into the cylinder, and then the piston comes around, the valve shutting, but now you've built all this airspeed. You got it started early, you got the airspeed high, and even though the piston's coming up and the valve shutting, the air is still coming in because you built all this airspeed and it's sitting there moving into the cylinder. That's how you can raise the VE. So what I did was I thought, well, how am I going to demonstrate a harmonic for people to look at, or the multiple harmonics? And I thought, okay, well, I'll just go into my electronics lab, and I made a dirty little sine wave that has harmonic content in it, and I just put it up on my spectrum analyzer. So you have what's called the fundamental frequency. That is the cycle of the valve. The valve is cycling at 10,000 RPM, that'd be 83 hertz, 83 times a second. That thing is opening and closing. And that is the first bump you see here off to the left.
Your first order.
Yeah. So this is at 1 megahertz, but it doesn't matter if it's 83 hertz or 1 megahertz. You still have a reflection of the wave. Here you have an electron going down a steel cable at 65% the speed of light, but the reflection, the time distance behavior is the same. The physics are the same. So you want to choose the second harmonic or the third harmonic. Well, we always use the second and the third. The valve is closed, the cycle's taking place. We don't use the first. We always use the second and the third, or the fourth if you're absolutely stuck and you can't use another one. The reason you want to use the first one is the amplitude. Every time that goes out and comes back, the amplitude decreases. So you don't get that hit, you don't get that start. And the reason we use the second harmonic, the second time it arrives at the valve, for sheet metal manifolds. But in the old days, 10 years ago, we used to use the third or fourth harmonic for single plane manifolds because all the runners converged. and you had this nasty plenum area, and you couldn't fit the runner, and you couldn't have runner isolation. The runners were all together. And when you don't have runner isolation, they don't act separately.
Right.
You have crosstalk and suborder
Yeah.
frequency. You have all this mess in there. So you have to drop a harmonic down. But nowadays we have 3D printing. And we can make these manifolds with runner isolation, and we can hit the second harmonic perfectly. And for truck pull classes where you are dictated, you have to have a cast manifold, which is kind of a dumb rule nowadays, because you can just 3D print anything you want.
Right, back to the rules makers. You're not saving people money anymore.
Right.
Costing them money now. It's not working the way you originally intended.
And basically, if you're a singer, each order is 1 octave. It's a doubling of frequency. So here you have 1 megahertz, 2 megahertz, 3 megahertz, 4 megahertz. Boom, boom, boom. It's just a doubling of the frequency. That's it.
Amazing.
That's awesome.
Amazing. What a great way to start day 2 of Engine Performance Expo. Subscribe, click the bell, click share, notify your friends. This was a big time informative deal. And hopefully people are now more interested not only in the Hemi hand grenades, but the whole concept of class racing and trying to take automotive history and make it as great as it can possibly be with our modern technology.
Absolutely. Not only did he blow our minds, he blew up the computer, but we're back and we're running.
Yeah.
And the next thing we're going to go to is kind of a series here we're going to tee up. So we're going to go to the Dortons, and they're going to be talking about R07 engines, line boring, cam versus crank alignment. Something that should be very near and dear to your heart, Project Pontiac.
Yes.
So let's go ahead and watch that video.
Okay, well, I'd like to welcome everyone to a presentation over here at Keith Dorton's location, and we have special guests here with Dan Begley over here from Molly, Ed Keebler from Rottler, Jeff, of course, I don't need to introduce, and this is the man here, Mr. Norton. Sorry, my whole day off a little bit. Bottom line is, my name is Randy Neal, and my mission today is to do a deep dive into Keith's knowledge. Where our topic is more on curiosity of understanding how a block is being machined properly, getting proper geometry, and we have a lot of questions for Keith as to what is the best data point of an engine. Now, we will probably have multiple answers here, and that's the whole purpose, is to say there maybe is another way to skin the cat. The unfortunate part is the cat is the only one who's mad about it. Our job, though, is to give you some good data. And we're going to start right away by saying that I'm going to start here with Ed for just 1 second. And Ed, I want to give you a sort of a quick overview on line boring as far as our machining process. So would you please start there?
Sure. So obviously, what we're trying to do with a line boring a block is we're trying to make all 5 or 6 or 7 or heck, however many caps you've got on there, all within a very straight and parallel line. Obviously, if there's any core shift or if there's any shift in those blocks whatsoever, or mains, I should say, you end up kind of eliminating some of your oil clearances, which is detrimental for your bearings.
Not a good thing.
And so that's the main object is to make those bores straight with each other, and of course round for the bearings also to have a good base.
So, when we talk about engines in general, and let's be fair about it, we've evolved a long way from very basic. In fact, you want to talk about engines that are rather unique. All of us are aware of the flathead fork. Well, here's the guy. Yep. This is the guy has really got this thing tuned up. Now, what's important, though, is if we talk about, in the old days, we used to use the common phrase called balance and blueprint. Well, we're going to talk a little bit about balancing, but blueprint is really what an engineer has designed a product, and he's established a data point, and then from there registers and geometry in order to allow, for instance, Dan's product to work in concert with the crank and make sure that it can handle load, but more importantly, live. So we're going to go back and forth on this whole thing. It's really going to be a very open dialogue conversation. And again, where I want to come back to is that it's a system, though. Everything about prepping an engine or design or whatever, it's wholesale to a single goal of perfection. That's the goal, but we have the challenge. So I want to start now. Now I know Jeff and of course Keith here, they forgot more than I'll ever know. But I'm going to simply lean on them pretty heavy to get their inputs. And so, Keith, if I wanted to start with an engine, where do you go? And maybe this has changed over years. Maybe we used to go one way, now we're going another.
Well, when we started talking about this topic, the first thing that came to my mind was a lot of the people that will be seeing this, it's a different era. But when we got started, we would build, say, a 350 Chevy for a oval track engine, and we'd do 2 engines. They were, as far as we were concerned, they were identical. Mm-hmm. One ran, one didn't. You know, and we didn't know why. You know, at the time, it took a lot of years to figure out some of those things. And drivers would complain. Mm-hmm. You know, why did you build John a better engine than you did for me? And so it was some politics involved there too. But it was not until after I've been doing this for quite a few years where the technology became available, where we realized some of the things that was happening. The primary topic right now, I guess, is the alignment mm-hmm. of the main bearing, cam tunnel, and so forth. And we initially, when the technology became available, we were able to correct that alignment in the main bearing. We could get it what we thought was round at that time. We could get it what we thought was straight at that time. We still had some variation in power and things like bearing wear. Right. You know, and why did number 2 and number 4 main look a lot worse than number 1 and 5? We didn't know, but there were some people a lot smarter than me that started working with counterweight placement mm-hmm. and so forth. Mm-hmm. Things got a little better. Then the technology became available through some, by today's standards, somewhat crude about measuring cam to crank alignment. And these 350 blocks that we were talking about, we found out pretty quickly then that not only was the camshaft not parallel with the crankshaft center line, but it was off side to side also. That affected cam timing. Mm-hmm. You know, the valve event had a pretty critical part of sure. performance, not so much of a durability thing. So once we were able to correct that, or as best as we could correct it with what equipment we had, things got better. Drivers still complain.
Oh yeah,
that's a good one. But mechanically things definitely got better. And as things progressed, we found, and a good example, we found that blocks are not as rigid as we thought they were. Right. Mm-hmm. A good example was we were doing Chrysler small block engines for a race team, and Chrysler did not have a good race block. They had the Trans Am block back in the 60s, which was a good block. Wasn't specifically made for racing, but it was a good block, good heavy bulkheads and so forth. Couldn't buy them new. They went to the junkyard and bought every one they could, had main caps made, and we put a good heavy main cap on them. Right. We aligned bored them very crudely, and we aligned honed them to finish. And the team, very particular, especially in that era about precisionist, being everything in line, had a checking bar made for us that was, what was it, 1,000 under?
I think so.
1,000 solid
sure.
steel
mm-hmm.
bar done in a crank grinder so we could check the alignment. So we'd do it in the line on the machine. Once we were finished, we'd slide that thing through
we knew we were right then. I mean, that told the tale. So that went on. It was okay until they had a checking bar made. Same thing, same people, same dimensions. We actually compared them. One day I got a call and said, this block ain't right. That's what you mean. He said, the bar won't, you can't drive the bar through it. So I went over there, took our bar. It wouldn't go either. So the block, you know where this is going.
Yep.
The block was on an engine stand bolted to the bell housing face.
Right.
And it took me, after sweating about it, about 45 minutes, I thought, I didn't line on it that way. Let's take it and put it on the table. Right. Set it flat on the table, on the China rails there. Bar slid right through. How do you fix that?
Studio here, Piney Flats. Day 2, welcome Randy, Keith, and Jeff Dorton. We just saw them in video. Are they live or are they Memorex? They're live here. And,
Yeah, it looks kind of familiar, doesn't it?
Right, right. Well, you know, one older person got the reference, but they're laughing. And Ryan, who doesn't get the reference at all, doesn't know what Memorex is, but that is okay. Line boring, very, very important, obviously, the geometry of an engine block, and we're learning it out here right now with Project Pontiac. If you can make it perfect, make it perfect. Seems to be the way to go.
That's true. And we found out, I guess decades ago now, how misaligned some of the blocks were as far as cam and crank alignment. And of course, everybody's got their own opinion on what's critical, you know, how much plus and minus you have, including the OEMs. But we found it very beneficial, both for longevity and power, to go as accurate and straight in alignment as you can, because everything's referenced off of those two, initially from the mains and then the cam and the mains. If you think about everything in that engine, that's your foundation.
Well, I think about what Darren was just talking about, the Hemi, and how complex all the valve train geometry is. Well, basically you're talking about the same thing here. This is well, it's not the valve train, but it is down here, and where you build from that, if these things are not aligned, they're not straight and parallel, then you're just almost like a baby with a hammer running wild. You're basically asking for somebody to come in and do some damage.
Yeah. And initially, how do you determine that? How do you determine what's right? Well, we started by doing the main housing bore first, and then with some rather crude ways of measuring and fixturing, indicating to check the alignment. And we found not only were some of them off parallel horizontally, they were off side to side. Right. So that can affect valve timing, because your lifter, the load location and angles are different. So it's just but it opened up a can of worms for us.
Well, and I want to go back to that moment. I think about, like, when you started, you presented with this piece, the engine block, and it might have been easy to assume that it was just correct. The moment that you realize that these aren't correct.
Yeah.
These are, wait a second. They look like they're right, but they're thousandths off. They're in the wrong direction, and it's causing all those problems. Like, that must have been kind of a troubling but eureka moment at the same time when you figured that out, that these are not right. There's something there that we need to fix.
Very much so. And I guess I'm doing the talking now because this was actually almost before Jeff's time when we first encountered that. But we just assumed that, they were correct. But, gosh, we found blocks, and things are better now. The aftermarket blocks, they're pretty doggone good. But then we found 15, 17 thousandths misalignment from front to rear, from crank to cam, both vertically and horizontally. And with rather crude fixturing, we found that, well, rather crude machining practices to correct it, and very time consuming also.
Yeah.
But the benefits were worth it. Things started getting better.
And Ryan, that's where Rottler comes in. It's not only a machining device, it's a measuring device. We saw it yesterday. Just, this one it was amazing to see how rapidly it made those calculations.
Yeah, I mean, and part of what the discussions with what we did when we filmed that segment at your place, and as you're talking about, Joe, I like what Keith said about assumptions, and I always say this is, whatever we do, whatever we go, and when we machine a block, no matter what, we have to make an assumption and pick a datum. And the conversation we've had over the last year, are we picking the main, are we picking the cam? And then also the question of, like you said, back in the day, maybe you can't correct that, maybe you can't, you kind of just have to at some point say, I think that's good. Mm-hmm. And the question is not, is it good or not, it's what's good enough, because you just work with what you got. And things have gotten better because technology's improved, the equipment's gotten better, what Rottler's gone in and done with the probes and the software and the visual interfaces where you can see that, you probe something, you can compare it to blueprint values and give the machinist the option to shift things back, whether that's on the main line or just your cylinder bores. But like Keith said, that heart and soul, that main line, that cam, having things in line, it affects everything. And, Lake, what you've done with honing and what we've done with same thing, right? I mean, if you can get things aligned, you can pull friction out of the system, and the sum of all these things all together, it helps you make a lot of power and improve longevity.
The longevity part of it, to me, I think is what just keeps coming back, right? I think about what Larry Wallace said to me years ago, and I've said it probably at every expo, is that he had that line that, if you go to Mount Everest, all the dead bodies are at the top. They're not at the bottom. It's kind of hard to fall off the bottom of a mountain. But the higher you climb, the less margin of error there is. So with a stock pickup truck making 0.75 horsepower per cubic inch, well, a whole lot of stuff will work.
Right.
But when you're getting up here at 2-3 horsepower per cubic inch and you're turning 10.5, now all of a sudden your margin of error is itty bitty tiny. So these little things like misalignment, now they're everything in terms of, can it make more than just one run?
Right.
It's like, it's.
Yeah, you see that people want to make more than one run, and God, it is very cool. For me, I manufacturing side, I just geek out over that. But having the tool available to, like Keith said, you can check things now and you can correct it. And like we've talked about, like having the option here in 2024, and you have the option to take these things and ask these questions and say, are those right? Can I fix them? What's, how much can I actually get out of this thing? And being able to do that, and what, Randy always likes to say it, what technology lets you do. I mean, it's a whole different world now.
It is pretty cool. This next coming up video back at your guys' shop, and it's Jeff and you guys at the F69, and it's pretty interesting. And the R07 is this very advanced, compacted graphite, highly engineered block, yet you're seeing that after you run it a few times, it begins to sag.
Yeah, that would, again, we assumed. But these blocks, I mean, this is as good as it gets.
Yeah.
And
but you still have to go in there and clean up and do some fixing.
There's some margin.
Yeah, it's a little bit of something. So you're gonna love this. So watch this video, then we're gonna come back and we'll discuss it a little bit more.
Today we have a NASCAR Chevrolet R07 block that we're doing some linebore work on. We have about 15 thousandths to come out of it. We're all indicated in, set up and ready to cut. So Ben, you'll start the cycle.
All right. Clear? Yep. So one of the things we're looking for on this pass is making sure that it's not going to hit the block. We're just trying to cut the caps right now, and then later on we'll, when we change the bit out, we'll go ahead, do an establishing pass, and then we'll do our final pass.
Looks like it's hitting pretty well even.
Yep,
Yeah,
parting line looks good.
Yeah.
Just dusting. To be fair though, this was a lot out. 8.1, 7.4.
Yeah.
So it makes sense. Yeah, it has a larger crown than usual. Another thing you like to look for is the finish in the cap as well. We did hit a little bit in the block, but that's okay because it's just slightly hitting, and we can go ahead and move our, when we move our bit over, we can go ahead and move it basically just another tenths out. We zero the old, we zero the location of that on the old bit, and then we move it a tenth out. We'll do a pass, so that way we know where we are, and then we'll be able to do our final pass from there.
We've done quite a few of these blocks now, and what we've found is a trend of the 3 center saddles and the mains being crowned a little bit. So even though the front and the rear won't hit the block where we're at right now, we are taking a little bit of material out of the 3.
This is something else you want to look for, the chips building up. Usually the chip breaker does a pretty good job knocking them off, but if it doesn't, what I like to do is as soon as it indexes up, stop the machine and make sure that it's stopped because you don't want to get your hands caught in it or nothing. And then pull the chips off of it with a hand or rag or something, and then you can go ahead, yellow out the other locations, and make sure that you have adequate vertical clearance. And then you can start auto cycle again and resume where you left off. Gauge is zeroed. Go ahead and clean all the chips out of the bores. Just want to make sure to get those out to get as accurate of a measurement as possible. It's reading 5, 5 thousandths to go in the front. Five thousandths and 6/10. Five thousandths and 4/10. Five thousandths and 4/10 again. And 5 thousandths and 3/10.
Back in the studio. Now that is a block right there. Keith, share with everybody out there, Randy is down on the end, and Randy and I are constantly having conversations about seeding this field for the future, finding the young people that are interested in machining and are going to, fill the sport and fill these engine shops when you guys eventually decide to move on and go out and sit on the couch, which will never happen. Ryan just told us he's 30 years old, so Ryan is young. But the kid we saw in that video, tell us about him.
Well, he's, I hope he's not one of a kind, but, he's one of a kind that we've had in quite a while. And as I was just talking earlier, a year ago now, he knew what a micrometer was. Didn't know how to read it. Had no idea what a dial bore gauge was. But we needed somebody to operate the machine. We got a contract to do quite a few of these blocks. And Jeff and I didn't have the time to pull away from everything else to do it. So we talked, how are we going to do this? We can't lose the contract. But how we can't work 26 hours a day. We just can't. So this boy had been working with us as an apprentice, or tear down, clean up, done anything. But he truly a yes sir, no sir guy. Very respectful. Wanted to learn. So we said, what about Ben? All you got to do, punch buttons, right? And so we asked him, would you like to learn to do this? Sure. Give him the manual, tell him watch videos, come in. We work with him, show him how to read the mic, let him take one and practice with it, same way with the dial bore gauge. And of course, he's not intimidated like myself with the computer. And so he takes to it right away. And within a few days, he's operating the machine. And he's reading within tenths and machining within tenths.
There you go.
A week before, he had no idea what a thousandths was. So we had to physically show him how much a thousandths really is, much less a tenth of a thousandths. So now we would not turn him to the wolves without. So we were there. One of us was over his shoulder, emphasizing speed is not what we're after. Accuracy is what we're looking for. That's what we have to have. If you're in doubt of anything, stop. Come get one of us. And he was smart enough to do it and not too proud to ask. So, we were amazed. And it took that burden off of us. Now we can, with confidence, do this job. But it's kind of funny. After doing 4 or 5 blocks, I was watching him and everything going good. Yes, sir. I said, you realize this is a $20,000 block? He said,
now you made him nervous.
I did not say that to intimidate him, but he needed to know.
Right.
He said, I had an idea that it was very expensive. I didn't think it was that bad. And it didn't intimidate him. And I said, and I explained to him and emphasized, this is not to scare you. This is to show you that you're qualified to work on something that critical and that expensive, and you can do it.
That's motivational. And that's what it is. Randy, you talk about it all the time, that we need to motivate And I think that's a perfect example.
Inspiration is a key part of the ingredient, but the first thing we need to recognize is that there's an awful lot of talent out there that is looking for a place to land to find a career. EPE, a lot of the foundation of what we've done in the beginning here, has always been about motivating young people to say, hey, this is a good gig. This is something where you can learn, you can have visual hands-on, but the technology we bring to the program now, they're interested. You know, it's not the deal in the old day when I grew up. Man, I started in the cleanup department. When I got home in the night, the wife wouldn't let me come in with the clothes stripped there, didn't come in. You know, it's a different gig now. Now we got opportunities to have a really bona fide career with these young men, but it's supported. And this is the key part of this thing. This is what EPE, I think, is all about. We're giving visual applications. We're showing right now $20,000 blocks can be done to perfection with good talent. But the bottom line is, it is all about learning. We are moving to that next level. That's what's going to excite the next generation. We need to keep them involved.
Well, one thing Keith just mentioned there I thought was pretty interesting is we chatted about this a little bit yesterday, is that what I feel like is happening right now is that everything's a coming together of that there are a lot of younger people like Ben, like my son Ben, that they know they don't want to have a desk job.
Right.
But what career options are out there for you? And the idea of learning to read, you know, old machines with load meters and stuff like that not intuitive to them. But digital stuff is intuitive. That's what they grew up doing that. So the fact that you now have, you know, balancing machines and mills and hones and things that can do it with that digital interface, that you can go back and watch some videos. And then be able to kind of pick it up and run. I mean, perfect example. I mean, Jolie's back there, you know, Dominator's daughter, machining your block.
Yes, exactly, and into it too.
Yeah.
I spoke with her yesterday. She's 16 years old. I didn't realize she was that young. She's 16 years old. It's like, you want to do this? She's like, I want to do this.
Yeah.
It's like,
That's great.
what do your friends think about what you want to do? She's like, they're not that into it. I was like, why not? And she said, well, it's too much for some of them. But when you started, not everybody was into cars either. The car culture, you know, you think about a high school and the football and all the car guys in the movie Grease, you know, the car guys were a smaller group. Outcasts. It just naturally, maybe not outcasts, but smaller group, or outcasts, certainly. Always, it's just a natural thing. It wasn't always a mainstream deal. Ice cream, vanilla, is the most favorite and most purchased flavor, but it's not the best flavor. And that's the thing. And so you don't have to find hundreds of young people who are ready to dive into the machine shop, but you have to find the right ones. Right. And it looked like you found the right one, and you're working it. And it's funny watching the block get shaped into something that's going to make a lot of horsepower, and the person doing it was in that similar situation. Right. I think that's great.
Yes, it is. Tell them the only problem we got with him right now.
Yeah, one thing about Ben is where we seen that we could really make this deal work was when we started on machine, is machine movement. Like, he knew which button to push, like just come to him just like right off the bat. And that's been the hardest part for me to adapt to the machine when I was learning it. You know, if I wanted to go right, I went left, you know, and that sort of thing. But he had the machine movement down all the way. I mean, just like
the interface to him was just intuitive.
I guess being so much younger and was just right off the bat. But the only problem we've had with him is he got, and this has happened just recently, is he got to take a little bit longer to indicate in. And what he was thinking was way off. He was only off a matter of a couple tenths. He was thinking the indicator was a little different. So he was, on a last word indicator, he was a needle width off.
Yeah.
And from one end to the other, and he was having trouble getting it to repeat. But it was a needle width on a last word stereo indicator that he was worried about. And he was very, very concerned about it. And I was like,
because he knew it's $20,000 block, he didn't want to mess it up.
And I was like, this is what I consider perfect. If you can get them like this, for you to do this on this part of the thing, if you can get it within that needle width, I mean,
you're good.
That's
awesome.
great.
What we had to explain to him was the machine over there that we did this process before, if we were within a thousandths, that's as good as it's going to get.
Right.
You know, no matter how good the operator and all is, you know, that was, so that was really gratifying that he got Jeff, you know, to explain this to us.
He was bothered by it.
But we had to explain to him that, and now he's going to love it.
We're setting the target for genuine perfection. Right?
Yes.
Keyword perfection, though. Let's think about it. Perfection 40 years ago, perfection 30 years ago, 20 years, 10 years. It's a moving target, right?
Yes.
Okay, but that's because technology has allowed us to challenge that. What we used to do, we sort of surrendered to the available technology. Look what we got now. I mean, if I took this back 40 years, holy moly, you know, this would be killer. This is what's new about our industry now. This is where it's really quite exciting to the young generation. They can come in and take a legitimate qualified technician and make him sit back and say, holy moly, this guy's good. It's neat. It's a nice transition, and it's all beneficial to the young people.
Yeah, and I think that's exactly what the content of this next video is all about, is going back and overview of that history and progression to get to where we are today. So stay tuned, watch this video.
Hi there. We have a new episode here for the Engine Performance Expo, and I am honored to say that I have some of the most knowledgeable guys in this particular discussion. I'd like to start right to my right first, self-introduction.
Ryan Thompson, lead applications engineer here at Rottler Manufacturing. Keith Dorton with Automotive Specialist in Concord, North Carolina.
Dan Bagley, I'm the technical sales engineer for Molly Levi Engineering.
And I'm Randy Neal of CWT Industries, and we have a treat for you guys today because there's a giant opportunity for tooling to be developed, or let me rephrase that, that's now online and available that can fix some of the anomalies we have in establishing geometry through the block. Ryan, pick up on that.
Yeah, I mean, you know, Randy, it's the conversation today is it's always about data, and I think that's, you know, why I'm lucky enough to be on this panel is working at Rottler and working in this industry with the machine tools. You know, it always comes down to the fixturing. Rottler's success, Rottler's brand is built on, well, anyone can go out and buy a CNC machine, but when you're doing engines, to buy this equipment and buy into this industry and what you're investing in is a solution for specific applications. And we're always looking at it. It's my job here is to go out, talk with gentlemen such as Keith, such as Randy, as Dan, and we go out and say, well, what are the things that aren't quite right with these engines and how can we correct that? And no matter what we do with any fixture we develop, we have to make assumptions. And we're assuming when we, you know, like we have back here in our fourth axis and we're picking up the main and picking up the cam, we're assuming those things are in line. And a lot of times don't even think about it. We throw a block in and we say, yeah, that's a round straight hole and both ends 1 and 5 are in line and the cam should be, you know, straight up and parallel. But the reality is, and as Keith can elaborate on, it's not. So if it's not, and we're just machining things away and we're not correcting those things, and we're living on those assumptions without even thinking it, are we putting the best product forward? We have modern equipment with CNC machines with probes and data collection, and we can look and truly paint a very accurate picture in blueprint blocks. But how do we go about that process, and what is the process?
Actually, that's a key point here because fortunately with technology that we now have behind us, it has gotten to the point where machines actually almost have the ability to take the variability of what our beliefs are versus what we can now measure and predict an event of geometry. Knowing that we have the cam boards and the main boards working in harmony, in absolute parallel, that assumption before, we had different types of tooling out there, but the best guess, and that's where we have changed this. Keith, for a second, pick on that for me.
Well, let's just assume we're talking about a small block Chevy to start with. Then it's to apply to all engines. We've seen it on the small blocks where back a number of years ago, decades ago actually, where with the crude equipment we had, let's say we put steel caps on the block and we align board it. We we know that was all center lined on good. And then we put it in our fixturing to check the cam alignment, and we found some horrible discrepancies in the cam alignment, both side to side and vertically. It was hard to correct with the equipment we had then. We did it with a horizontal line boring machine, and very confusing, very tedious work, but we were able to take as much as, some of them were close to 30 thousandths out of line, both directions. So you were correcting alignment in two different directions. But, and we did it by using oversized cam bearings. Started with with the big block Chevy bearing in it, and having a cam made for that. And then that evolved quickly into use 50 millimeter roller on the upper level engines, which helped cam bearing wear load on the cold starts and things of that nature. But our performance and longevity of everything seemed to increase with those modifications. Now that we have the F-69, and we assume, just like Ryan said, that everything's in line. And it was also mentioned earlier to me that should we line up off of the cam boards to the crank board and then do the lifter? For sure, that will make the lifter right, but it's still out of whack. Right. So my theory is we need to correct that cam prior to doing anything else. That way when we put it in this machine, we'll know we've got a solid foundation. Everything is based straight up on center lines. We got that geometry dialed in. So the way this machine will do it, we can, if we know the center to center, I mean, that's easy to find out what it's supposed to do. So we put the block in here after we do the main tunnel, set it up, setting up off the mains. We can go this way and this way forward for whatever size bearing we want. And bingo, you put it back in the machine and everything else is, is going to be right. Lifter angle, deck angle, the whole deal.
Yeah, and I think, Keith, when I was out at your place recently, we were experimenting with some of this stuff.
Yeah.
And you hit on a good point, and I agree with you. I mean, I look in some of this for me is working with the fixturing. What do we have? What's the process? That also makes sense because at the end of the day, you got to find a way to be efficient and make money on this. I mean, that's what we're in it for. I mean, you're making a good product, you're making money, and what's your name on it? Doing with the F-69, being able to line bore, hit that crank line first, and we know that that's our good datum. And then when we go to do that cam tunnel, we can stand this block on that. Use that machine surface that is that main line now, and we talked about this, is we can hit the bell housing, right? We can shoot the cam tunnel. So now we have our main line and our cam line parallel in line in both directions. We don't have that 25, which is crazy. You'd have to take out so much material to correct that. Yeah. And now you have a perpendicular bell housing. So I have to think that for me, from the engine, I go, if your cam's in line and if your crank's in line, you got all the power going out through the crank, and you're perpendicular on the bell housing. All the power is going to go out through that. That's got to be, for the 3 points to hit first, that's got to be probably, you're setting that foundation for everything you do after, like you said. Now we can put it in, especially going back to using the fixtures, our fourth axis, we're centering on the main and the cam and the bell housing. So if I've done the main and the cam and the bell housing first, before you can go into that's got to give you the best result for your cylinder bores, your lifter bores, your jacks, all of it at that point. I mean, you've truly created a datum and then built off that datum to your point.
All right, let me kick it a little bit different here. Everything that we do was with the goal of making his bearings work. If the bearing, in other words, the geometry, the fit, the alignment, if that is not correct, what happens to your bearings?
Yeah, I mean, parts don't lie. When you read parts after the engine comes apart, they don't lie. They're telling the story. Misalignment. If bearings misaligned with a shaft, you reduce the oil film thickness in there. When you reduce the oil film thickness, you have less margin. Less margin, the crankshaft's going to hit the bearing. Frictional temperature starts melting the bearing, and next thing you know, now we created a bearing failure due to misalignment. something that we see, but they're only as good as the lowest melting point of the overlay, and friction kills that.
So misalignment is really extremely important, is it not?
Yeah, when you work on bearing, you're setting X amount of clearance for the shaft to the bearing, and then if you move it, now all of a sudden that clearance is not there what you thought it was, and you're not getting oil film around there, and you definitely have a problem.
So sometimes the products that you're seeing unusual wear, it's not the failure of a normal cycle of events, it's because of alignment geometry issues.
Absolutely. I mean, equipment like this is helping put everything back where it needs to be, and the engines that we're building today are not the engines we used to build, and they're less forgiving, oils are getting thinner, so everything you're doing now is more critical for today and what we're doing.
Sure. We've arrived at a state now because of technology, and Rottler has just one of the key components here. And then we have the talent with someone of the history of engine building, Keith. He's sitting there tuning us up, so to speak, and advising and directing. I got to tell you, Keith, though, but is it just a parallel, or what about the relationship to the lifter bores and the angularity and the straightness of that?
Well, there's nothing that's not critical. Okay,
fair enough.
There you go. There's nothing that I don't mean there's nothing that we can't improve on, but we can correct it to what it's supposed to be. But let me back up just a bit, telling you, to the extreme of some. For we had some issues. If anybody's ever like a dry sump pump, you put that pump on there and the belt walks off. The pump's a little crooked. Well, we seen that on a belt drive, on the cam. Why is that happening? And well, it happened. We seen it both ways, where it walked off the front and where it walked off the back and actually rubbed the block.
Really?
Well, what's causing that? And it was that vertical alignment there.
There we are.
So that kind of helped start, what's going on here when we fixtured it to try to, in a crude way, to find what was going on there. But yeah, the lifter placement. Going back to where we had to run flat tappets. Your fore and aft alignment. Because that lifter's got to be so much off center of the load, sure. and like on a Ford, it's offset opposite on each bank. And they do that to keep the cam
centered up.
So, but I don't know. It's just like a carpenter using a plumb bob. To me, you use that plumb bob front and rear, and you get everything dialed in, and you go from there.
Okay. So let me ask this and put this in summary. With your history of building, all the things you used to do, knowing all these things, would you go back from where you are now?
Boy, it'd be hard. Can we go back without an iPhone? Yeah, I could do that. But I wouldn't want to go back without these.
Technology is your friend. We now have the tooling. Remember the $6 million man? We now have this. Well, here we are, and this is the moneymaker. This is the one thing that pushes you to the next level in your engine building.
Back in the studio here at the Engine Performance Expo, Diesel Roundtable Lake. So Cass has rejoined us. Good morning, Cass. How are you?
Doing good.
Of course, Chuck Lynch and Chris here. What'd you say? You're here for comic relief?
I'm here for comic relief, yes, Joe.
And Matt Hussey with us. We're going to get in a little deeper with Matt a little bit later today. But it's kind of interesting. Like, we've carved out these features for diesel conversation. But it's not, it's not that separate from the rest of it. What have you guys been taking in from the expo so far? Cass, I'm looking right at you because you're the diesel master.
So there's cashews and M&Ms. There's a lot of snacks in the back. No, I'm just kidding. That's your job, right? The comic relief.
Yes.
Sorry. No, it's always great. Like I mentioned yesterday, just getting to talk to guys. There's a lot of. At the end of the day, a diesel engine doesn't know it's a diesel engine. It just knows it's an air pump. So a lot of the things carry over from, guys like Darren Morgan or guys like Billy Godbold. There's so much there that, you get to hang out with those guys and talk. And even though that they're not per se diesel guys, there's a lot of technology that still, infiltrates itself and finds itself into our world.
Well, I see the work. I've been to your shop, and I see the work that you guys are doing there. And it's that progression that, just like we were talking about with the previous roundtable with the Dortons, that as you begin to go further and further away from what the OE designed it for, I think back to what Darren was doing this morning, it's like you start pushing that limit, you have to now start bringing in like the connecting rods and the stuff you've done in the previous segments. Talk a little bit about when you're trying to build something big power, because diesels are big. I mean, they're already pretty massive engines. They're robustly built, but it doesn't mean that means, you can just put 1,000 horsepower to it and you're good.
So the things that are major, the major differences in diesel is torque tears up everything. That's the thing that is just so destructive. And piston speed has a tremendous amount to do with that, with compression ratio on top of the piston, and we're slowing the piston speed down. You can do the math off of it and find out, at a given RPM range that we're going to operate, our piston speed may be 25, 27 miles per hour going back and forth in a, 4-inch, 134 stroke.
And having to stop each time.
And having to stop and reverse. It's busy. It's got a lot going on. But because the piston is so much slower than that of a 8,000 RPM engine, it is what we call there's a longer duration that it has to maintain that load. So there's a lot of torsional forces that are acting on that. So bottom end is always a big problem with the diesel. I use this analogy all the time. When I was flying aerobatics, we would do high G maneuvers, but the maneuvers that we would do, we might pull 8 Gs, 9 Gs on doing this, which sounds like a tremendous amount, and it is. But, you got guys that are flying F-18s, and they may pull 8 Gs, but, these guys are wearing G suits, but we're not. Well, what's the difference? The difference is that unless I did like a split S and pulled it around where I have a lot of kinetic energy, and then I can pull it all the way through the bottom and hold that load, I don't have to worry so much about G-lock and all the things that are that are going on with that. The big difference is the amount of time, the sustain. If I say this microphone, right, is it heavy? You would say no. And I say, okay, great, hold it here. I'll be back in 8 hours. And you tell me, is it heavy? There's a lot of difference. Now, that's because we're slowing that piston speed down. Difference between that and maybe a big block Chevy or whatever, gasoline engine here. So we have all that load that's staying for a lot longer. And that's where we really start running into problems. And that's the reason why, we might match up a bigger single turbo with a different AR housing, a different compressor wheel and exhaust. That is going to push the RPM up higher. That's going to increase our piston speed. Our duration now is not as long. Parts live longer lives when they're happier. And so there's a lot of things that are different though in the world because of the RPM range and the compression ratio that we're dealing with, the cylinder pressures. So that's the major things when we're looking at fixing things. It's starting. I'm looking really the two ends of the spectrum, the bottom end and where the head gasket is, right? And it's always the fuse.
We're gonna get there later today on the head gasket side,
And the fuse moves. You've got a guy that says, me and Chuck talk about this all the time. But you have the guys out there that say, I keep tripping that 20 amp breaker. All I need to do is just put a 50 amp in that thing, and next thing you know, the fire department's at the house and it's burning to the ground. The guy goes, I don't know what happened, right? The breaker was initially it was tripping, but the wire couldn't support it, right? So that 12 gauge wire is now fried in the house, and the house burnt down. We're always moving that fuse to see what the next thing is that's causing the problem, and that's just development.
So in that bottom end system, what is the weak link? Man, I remember being at your place before, and when we went and visited some people together. When you look at one of those wrist pins, those things are significant.
Yeah.
Especially you compare, if we had one of those wrist pins from one of yours and put one of Ben Strader's wrist pins from Spinal Tap next door, I'm pretty sure the Spinal Tap pin would fit right through the center of your pin and have lots of clearance.
Right. Yeah. We got 1,800 plus grams of bob weight here, closer to 19 at times. His analogy is exact. Can I stop a Honda from 60 to 0 easier, or can I stop a freight train loaded down with inertia? Who's going to stop first? I'm trying to sling 1,900 grams here. Talk to any of these gas guys in this show right now and ask them what their bob weights are. They'll be, and when we tell me and Cass tell them what our bob weights are, they're like, "Are you kidding me?"
Our piston weighs as much as their assembly.
Yeah.
Right.
830 grams on a 6.4, 30 over pistons, about 825 to 830 grams. Piston rings.
Without the pin.
The pin, no, that's
with the pin.
Yeah, that's with the pin. So it weighs about 830 grams. I mean, you could tell me, with pretty close to what what y'all would see. But that's a good example of seeing the differences, between the two. So that's a major deal. Now you're asking about what, where's the weak link? It's a lot of force. Where's the weak link? And the answer is I'll return a question. What engine platform are we talking about?
Right.
It's not all the same. I could take a Cummins rod and I can make, depending on what year that rod is, before the common rail, they were all a forged rod and now they're a powdered metal rod, but they're different years, makes, model. They all have their own, they're all different entities and they all have their own weak links. So we talk, 6 liter, well, okay, head gasket failure. First thing that the guy's going to think of is this 4 bolts per cylinder head. That's going to be your head gasket failure. We talk about maybe a 6.4, it may be a completely different bottom end issue. If you look at the surface area of the bearing versus compare it to maybe a Cummins, there's a huge difference there. If we move it over to maybe a Duramax, that may be issues that we might start seeing with even crankshafts, maybe not, connecting rods. It's just a mix and match of parts, and it is a lot in the mindset. And the thing I like and I really enjoy about it is understanding the mindset of the engineer for the application. Cummins is an engine company. Right. So the reason why their internal components are heavier in this application is because they're going to use it over a broader span of applications. Exactly. So
they didn't build that engine for that truck.
Right. It's a marine application. It's a gen set. It's a stationary power. It might be mining, gas. Who knows what it's going to be used for? It's a lot cheaper to build one part that will do multiple things than to be one, isolated. And you look at a Ford Power Stroke International's version of it, right? Which is 7.3 all the way to 6.4. That's intent was pickup truck, class 4. That's the range and it operates in, right? So there are different things that we start seeing that will fail in certain areas for those reasons. It's design intent is what it boils down to.
Yeah, you and I spoke about the B-Series Cummins many years ago, going back to the 90s, okay, this particular engine application replaced the Perkins for the most applications because it was in tractors, it was in generators. Okay, I got 1,470 applications for this one engine platform. So, okay, you have to build with all of that in mind that this is going everywhere. And then, again, you jump back to a truck and the duty cycle that you're even testing for, the amount of engineering you put into it. So, like I say, that's where that fuse, okay, what is the intent and how robust are we going to try to build this because of every climb and place that it may be?
That's a very interesting perspective. Yeah, you don't really think about it. You're like, oh, it's a diesel, right? And you see the truck, and you just kind of forget about that. Yeah, there is a thought process and engineering procedure that went into building that engine. In some cases, that was designed for the purpose, like you said. That I'm sure when GM did the Duramax, they knew it was going into a vehicle. It was never going to be in a gen set in
the design on the heads on the L5P is nothing short of amazing to me. I've been through them, chopped them up, looked at them, poured moldings of them. I'm a calibrator first. I'm a machinist second. And the design of the port work that they've done on the L5P to promote swirl is probably the best head on planet Earth right now in a pickup truck, in my honest opinion, from what I've seen.
And that's because of emissions, right?
Well, it also, honestly, I'm sure that's part of the driving factor, but
I don't think so.
You don't think so?
I'll tell you the reason why. I think that I think that they have had to step up their game. We're making 500 horsepower. I don't think that the emissions truly is the issue for that. Swirl is for the reason for emissions. Now, there's a lot of different guys that talk about different things like that, but if you're trying to reintroduce, the combustion event takes place after the fuel is, before the fuel, the combustion event takes place as soon as the fuel is injected in. It's not like a gasoline engine where we're mixing and we're tumbling and we're trying to make sure that atomization has occurred because of the mixing of the gases and the oxygen. So the swirl port, really and truly, you start seeing that there's two major advantages for that. Lower RPM velocity, right? So we can get off the seat, we can increase the velocity of the air, we can have a little better throttle response. Totally get that. But the main reason for that, secondary, is so that we can introduce the exhaust gas, the recirculation.
EGR.
So we need to swirl that because we're actually bringing that through the port, right? We're not bringing that into the cylinder.
Right.
So there's quite a bit difference. But yeah, to Matt's point, L5P is absolutely amazing. It's a total redesign, but they're having to keep up with Fords that are making 500 horsepower and the Cummins and everything else. Yeah, so they've done a lot of it.
The EGR part of that makes sense, right? Because you got to manage that EGR if you're going to make power.
And in 2023, Ford just released the HO, the high output Ford truck, and we've been fortunate enough to get it tuned and calibrated. We've even done a 24 successfully, and Cummins was the only truck that we knew on the market that would release an HO, high output calibration. And you think about that, that's pretty amazing. That kind of power, that kind of torque. And then our job is to help him too, because we work with a lot of other engine builders as well to help an engine live. Because we're big on larger injectors, and a lot of guys frown on that. We're like, well, what happens as RPM goes up? Well, we start running out of time to inject. So now we start stretching in duration of the injector. We start adding excessive time in, because now we have to start the injection event with the piston so much further down in the bore to get the time we need to get the fuel in. Our EGTs start to get out of control. And then that's where you see the flowering of the bowl. Guys show pictures of how you look. You see a lot of these have like 8 spray patterns, 8 little orifices, and you see this pretty little flower, and you're like, man, it's getting further and further out of the combustion chamber of the piston, and it's working its way further and further to the edge of the piston. Well, what do we do with larger injectors? Well, we don't need as much timing. We don't need near as much duration, and we can get as much or more fuel in where we need it to happen, which is in the combustion chamber. That's why guys delip. The Max Force 13 pistons that everybody's ranting over on the 6.4 is really simple. I can put a Molle OE 6.4 piston right here, and I can put a Max Force, and everybody here, if nobody knew anything about pistons, they could easily go, well, God, that bowl is so much bigger on that Max Force. That's actually a good thing for me, because now as I'm trying to add time and add duration, I'm not getting outside of a small bowl that's creating hot spots. And because let's be honest, it's an aluminum piston, is it not? It's not forged. It's not forged, but it lives longer. There's a reason it lives longer.
Yeah, and that's all about parity. We talked about that a little bit yesterday, though. Once you increase that injector size and volume, you have to make sure that it can still atomize, because if you can't atomize and you're putting droplets in, and that's where swirl and tumble help you keep those droplets beat up so they'll be an atomization, because if they collect and come together, now I have fuel that lays on the piston. You still have auto ignition, but you, instead of having that boundary layer, that exhaust boundary layer that usually gives you some protection so the piston doesn't overheat, now it's on the piston. So you see these pistons that are melted down.
Cass has a whole bunch of those in his place. If you want some examples.
When you pull your exhaust manifold and it's got plugs of aluminum stuck in it,
So it truly, and the thing about that is to kind of expound a little bit about what he's talking about with this combustion bowl. Truly, there is more relationship between the tumble, and my persuasion, in the combustion bowl itself, because you got to consider this is being squeezed into a very, very small area, right? So when the injector fires, there's literally nothing left. This is whatever we brought in has already been mashed, but it is the relationship between the combustion bowl and the cylinder itself, the quench volume, right? Then there is the actual port, unless we start talking about, like I said, at lower RPMs and those things there as far as emissions are concerned. That's where that takes place. When guys are manipulating the bowl, whether through delipping or fly cutting, you're doing more to disrupt the design intent there. And for good reason, we know, because of we have hot spots that occur in certain areas of the combustion bowl because it's a reentrant bowl. It's having to reverse flow and go back the other direction, so there's going to be a dwell. It's like taking a rod hone, right? So you have to go off the end of and come back on because you don't want to dwell in that one area, so that we have an area of dwell. So that's the area that begins to get hot. That's what happens is it starts to break down. Burn holes, things crack, bad things happen.
And talk about atomization. If it wasn't important, we wouldn't see Duramaxes that started life on a CP3 pump. That a common, full throttle pull is about 23 to 24,000 pounds of rail pressure on an older model. Now we're well into the 30,000 pounds of rail pressure with these late model 23s and 24s. They're building bigger rails to handle it. They're upgrading the material on the nozzles. And it's like, well, why is that? Because obviously we know what happens as pressure goes up, atomization just keeps getting better and better and better. You can actually make horsepower on a diesel by doing nothing more than increasing rail pressure. Nothing else.
Right.
Just rail pressure. You know what I'm saying?
Yep.
Or duration, or, I mean,
let's dwell on that for a second. Sorry. I know Chris is the comic relief and I'm bad at puns. Thank you, Jeff. Joe. So the point is, if you can't atomize it, it will not vaporize. If it doesn't vaporize, you can't burn it.
Let me add something right there. I've been listening to this. So
out the tailpipe.
When we look at designing an intake port on a diesel, it's much different than a gas engines because we want to promote as much swirl. If you think about it, the diesel fuel molecule, it burns like an onion. So you need to peel layers. So the way we look at things is with the more swirl, you think about peeling an onion, you're able to get those layers off quicker, and then the quicker you can do that, the better and more efficient you burn that molecule. So we promote high swirl. We actually have an enhancement what we do on the intake valve side of things in the diesel engines to help with that low lift number to get that swirl process as quick as possible type deal. So it's a totally different. If you go back to Chevrolet and look at some of the early model Vortec heads, GM was experimenting with swirl with gas because you can literally see it in the port. You can literally see it in the old 7.3 in the way the intake runners and the way they do it. It's almost like a bobsled corner, what they're doing type deal, to get that air moving like that. So we promote high swirl in any of the port development we do on the diesel side of stuff.
So the 7.3 was before the VGT. So a lot of the reasons why you're seeing that on the 7.3 is because it was a non-variable geometry turbo. So the 7.3, the acceleration of the 7.3 is very poor, you know, compared to the 6-liter, right? So to increase the velocity, they add, basically you've got that port, right? Exactly. So now because we are narrowing that port down, we're increasing the velocity, so that helps with the instant coming off the throttle. As far as big power go, when you start looking at really big power numbers on these tractor pools, you look at a port and you see right through it. There's nothing. I mean, it's straight. There's no swirl, there's no nothing. Because of the port design between a pickup truck that's on the road and one that's out for all out making power, totally different idea.
Yeah, there's a giant difference between wide open throttle and park throttle.
Right.
We're going to talk about that more in depth later. So hang on, if you hang out all day, just feel free to sit whatever you're doing. You are learning something, so this counts as work.
And to address the exhaust side, what we look at that type deal, I address that with a camshaft because the highest velocity on the exhaust side, as soon as you crack that valve, okay, it's once out of there. You know, I've been made fun of for years, but I use your favorite carbonated beverage. When you pop that pull tab, have you got to pull it all the way for all the gas get out? So literally, on diesel camshafts, my duration on the exhaust side is shorter than what the intake side. And lack of a better term, you know, velocity spools that turbo, so let's hit it and forget it. So I shut the exhaust valve off very quickly on the diesel stuff. And any of my customers you talk to is throttle response is much better like the gas and the whole bit. So in looking at a lot of this type stuff, you know, the crankshaft issues and some of this other stuff can be corrected with some simple, you know, parts. But as what Matt does and what Cass does, but then you've built all this power, now you got to have that bottom end to support it. When that demand grows, now you got to have stronger parts to support that demand.
Fun fact, as my mind wanders, and I know that we've got to wrap up, what is the common thread between, because not only do I like the diesels as the engine, but just as a whole, right? So what's the common thread between Anheuser-Busch and Klesse Cummins? As far as what's the common thread between there? Anybody know? You know, don't you? Because I've told you. The first purchaser of Cummins engines when they came over, Anheuser-Busch. Mm-hmm. They were the ones that first invested in the company. Oh, wow. Which I thought was very interesting. You know, you would have had a Busch diesel engine if it had have worked out, but there was a parting of the ways. So, or an Anheuser. I don't know how that would have worked.
I guess
Doesn't sound near as cool as Cummins.
Doesn't sound near as cool as Cummins.
I guess they knew that Cummins was going to have to replace the Clydesdales.
I guess so.
Horsepower.
Had to do with towing heavy gear all around the country and distributing.
Yeah.
They were looking for a better way to do it.
So, speaking of boost, making big fuel, atomization, we're actually going to do a video about the Engine Performance Expo engine and running it on boost and naturally aspirated, and then analyzing the oil, which if you know me, you know is like one of my favorite topics. So stay tuned and watch this one. And on boost, we decided we would take an oil sample of the engine after we've done all the NA runs, and then we'll take another oil sample after we're done doing all the boosted runs to see how much difference we see in the oil just between the engine being run NA and running on boost. So let's take this sample from the NA runs, then we can compare it and show you the results from the boosted runs. Okay, we just made a whole bunch of big boost, over 20 pounds of boost, dyno runs, making over 1,300 horsepower. Now, let's take a sample of this oil after running on big boost. Now we'll send it off to the lab and show you the results. More boost always means more fuel, and the oil is showing the proof of that fact. First thing we see with these oil test results is the sample that ran on boost definitely has more fuel dilution, which has lowered the viscosity of the oil. It's also raised the amount of wear. When we look at the amount of iron and copper, aluminum, so that's, your iron is going to be your cylinder bore wear. The copper is going to be from the bushings, both in the lifter and the lifter bushings themselves, as well as the aluminum obviously is the pistons. So what we see right here is on NA, we were about 49 parts per million iron, 13 parts per million copper, 13 parts per million aluminum. Everything's doing pretty good there. But when we go to the boost, that iron shoots up to 75, the copper goes up to 16, and the aluminum goes up to 18. And part of that is that loss of viscosity due to the fuel dilution. If we had not had that higher level of fuel dilution, the viscosity wouldn't have decreased, which wouldn't have increased wear. So I think we could probably change the viscosity of the oil and be able to make this work. Now, when we were running here, we were actually running the Driven 5W30, the break-in oil in it. So we did that as kind of a test for the guys at Driven to kind of see, okay, with that lower viscosity oil, how well does it handle a whole bunch of boost? And I'm gonna say right now, it actually handled it really well for that viscosity with 1,300 horsepower. That's a lot of horsepower thrown at it, so I think it did pretty well. If you go back and look at the previous samples, when we were at a higher viscosity, that 1540 blend, those numbers were quite a bit less because there was more viscosity. So really more of a viscosity issue here. Other thing that kind of jumped out, obviously, in red when you first looked at the page, is the water. When we ran the engine previously, we didn't see those higher levels of water. Let me tell you why we didn't see a lot of water previously, but we did this time. And it's all about engine operating temperature. Before we were running the engine, we hadn't been running just on Q16 the whole time. We had been running on some other fuels. But then we also were running the engine at a little bit warmer oil temperature and water temperature. What happens when you heat up water? It evaporates. What happens when it's cold? It condenses. We're seeing condensation here. Obviously, every combustion cycle is creating water, and because we were running the engine at a lower temperature to prevent detonation, by the way, we didn't want to blow it up. We were trying to be safe to keep detonation from occurring. Consequence for that is that lower operating temperature created more water, and we can actually see the samples were positive for water. So the boosted sample did have more water in it than the NA sample, which makes sense. Now, the report just shows it's positive for both. It doesn't report the actual number. I saw the actual results, and the actual results say there was more water in the boosted sample than in a sample, which again just makes sense. More fuel means more power. That's more combustion happening. That means more water being created. So overall, these are really interesting results, and we can see that pattern from when we initially ran the engine, the very beginning, when we were running NA and then added a little bit of boost. We can see the wear metals go from 28 parts per million iron up to 35, up to 63, as we were just kind of moving our way up. But then when we go to the lower viscosity oil, making that same high level of boost, now we go from 49 parts per million compared to 28 or 35. Now we're also seeing that go up because the viscosity went down. Obviously, when we go to a higher level of boost, we go from 63 to 75. So what this tells me isn't the engine's in distress, but it does tell us we need to make some changes to how we're operating the engine. We need to run the engine at a little bit warmer temperature. If we need to back some timing out of it in order to prevent detonation, that's the best way to do it, because we don't want a lot of water building up in there, because that's going to cause rust and other issues. We don't want that viscosity loss. We know we need the fuel to make the power. So what do? We're going to have to increase the viscosity of the oil to offset for that, because we can basically see that as long as the oil viscosity was around 12 to 15 centistokes. That's a flow measurement. We had really low wear. It was when viscosity went below 12, which basically a 30 grade oil or lower, that's 12 centistokes and down, like 12 and a half and down, is a 30 or a 20 or a 16 or a 12 or 8 or whatever. We really need to be in that 40 grade range. I don't think we need to go all the way to 50 because we're running this engine fairly cold. Even though we're going to run it a little bit warmer, we're not going to be running it hot. So we don't need to have a 50. You need enough viscosity, but not too little viscosity. If the oil is too thick, it won't flow enough, and we can have piston scuffing problems and things like that. So we want to have enough oil getting where it needs to be at the right place, at the right time, at the right amount. 4 R's, talk about it all the time. So I think in that 40 grade range, probably around 14, 15 centistokes is right where we need to be at 100 degrees C on this test to be able to have the right viscosity in the engine as it's running, even making boost. So that's why we do the oil analysis, is we can run the engine, we can get all the data from the engine, we can take the oil sample, and we can let the engine talk to us, tell us what it likes and what it doesn't like, and we can make some changes now on how we run the engine, what oil we need to put in the engine next time to make sure we have the good performance, but also that we're reducing wear. Well, that's the fun part about oil analysis. It's science, not speculation. We can know what's going on in the engine and make changes to make it better. So you get more of me, but you get Billy this time too.
Hey, it's fun. Now, I love water vapor. It's like, you don't know a lot about this, but in previous, Scooter talks about previous life, right?
Right.
In a previous life, I really was a physicist. And one of the things that we studied was, when I was a kid, ozone was a big deal, right? Mm-hmm. So we had a big thing at Rhodes College on the top of the physics tower. I actually had the highest office at Rhodes just because it was on the physics tower, on the top. But we had a heliostat. It's a mirror system that tracks the sun. Okay. And we're measuring the ozone, how much ozone absorption there was. Well, water vapor is one of these things that people don't get, that water's all out there. And all this water vapor, being from Memphis, we have tons of it.
Yes.
There was like only one day that whole year that had low enough humidity that I could get a good ozone test because the front had come through and knocked all the water out that day. But normally we're just surrounded by water. And so when you do these tests, you can wind up finding out something that you just don't expect, right?
Absolutely. And you'd think in Arizona, of all places, it would be very low humidity, that water wouldn't be an issue. But in this case, we're using an oxygenated fuel, plus combustion makes water.
Yeah, it's one of the byproducts of it. Like people don't realize when you take octane and combine it with oxygen, you do get H2O as one of the products of combustion.
Absolutely.
So you're making it, and not only that is, when you're putting all this fuel in, that it's cooling all of the parts of the engine.
Yeah.
So you've got this latent heat of vaporization sucking all this temperature out of your intake manifold, out of your cylinder heads, things like that. And then all of a sudden, as soon as you hit that dew point, as soon as it gets cool enough to hit that dew point, any little bit of water out there will just throw your test totally off because it wants to condense on every surface.
Well, the other thing too is we were totally squirrels, distracted, because we had combustion analysis this time, right?
Yeah.
So the first time we built the engine, we didn't have the cool combustion analysis. So what you do, you just make dyno run, but this time around, we were so fascinated by the data we were getting from the combustion analysis that we're sitting here spending minutes studying the data so that the runs weren't consecutive back to back to back like they would normally be in the past. And I really believe that's the main reason why there was the water that was so positive in these oil samples this time when we didn't have it historically.
Right. You know, when Ben got that Plex system and you start getting real academic level data, you know, there's so much to dive in there. It's easy to make a 30-second, 20-second dyno pull and spend the next 20 minutes, 30 minutes, 2 hours looking at each RPM and how the engine's doing differently.
Right.
And you don't think about it, but that whole deal is that you're not getting, if you keep that engine cool. You know, I used to think when you were at Driven, I came over there, it's like, guys, I've got a product idea. You need a stand to put next to people's engines so they can go and warm up their oil to like 230, 240 degrees. Make sure it gets past 212 to get all the water out, because water's just trying to grab hold of everything in that engine until you get it up over that, you know, get it up over boiling, and then all of a sudden, you know, it gets to be your friend, right?
Right. And one of the other, I think, takeaways from the data from this one, which I think is really important, is that, you know, oil is going to do exactly what it's designed to do unless it's acted on by one of two outside forces. One of them is temperature, and we can try to mitigate that through many ways. But the other one is contamination. And contamination is the one that I see in practice that does the most damage. And that's typically one of two things: fuel or water. And in this case, we got both. And boy, the numbers don't lie, right? When you add fuel and water, that iron level just shot up compared to when there was just water, not fuel. I mean, it's big. And when you get over here where there's not positive on water, not positive on fuel, I mean, it's literally a third of the amount of wear when you can control it better.
Right. I mean, you know, we came back to these things that I love so much. So you get this little surface plate. Well, you have to realize there's just certain room on here. And when anything else other than the oil grabs hold, you know, then you're going to have a problem. And those detergents, the water, you get everything in there, and it just
fuel and water washing your oil away leads to higher wear.
Right.
It doesn't seem like rocket science, does it?
No, I mean, it's weird. I'm trying to explain to it like it's complex, but no oil here bad.
Yes, really bad.
Right. And like if you're going to wash if you're out there working in your garage and you get oil all over your wrench, what are you going to do?
It's going to slip out of your hand.
Right, but you got to clean it, right?
Yes, you do.
Well, you might wash it off with water. You might put it with soap and water. You might spray it down with carb cleaner. You might dip it in fuel, right?
Yep.
Exactly what we'd use to get the oil off of the tool.
We're getting it off our cylinder wall.
We're putting it onto our cylinder wall.
Right, yeah.
Sorry.
Yeah. No, but that's the thing. But we've got to put more fuel into the engine to make more power. So that's why things like operating temperature, these little things that you may not even think about, subtle changes can make a huge difference. Because we didn't change the oil, we didn't change the mechanics of the engine, but you could change the wear in the engine
by the environmental.
Yes. And that's huge. But again, that's why we do these things here at the Engine Performance Expo. We want to show you these little subtle tricks and tools you can use to make your engines work better and live longer. And another part about contamination is you really want to keep all that water that's the coolant inside the coolant passages and not so much in the combustion chamber.
Yeah, that's
or in
really,
the oil
you know,
pan.
it always wants to go where it's least beneficial. So, you know, kind of keep it there, you know, and that's where you get finish of the deck, good gaskets. You know, these multi-layer gaskets these days are so good. You know, there's a lot of different options there. You know, try to keep your coolant where it needs to be, you know, and things that you don't think that hurt you. If it, you know, rust, washing off the surface, there's 1,000 things that water, glycol, just keep it out of there.
Yeah, absolutely. So that's why we have our buddy Chuck Lynch who's going to talk to you about surface finish and gaskets.
Applications engineer from Rottler here, and I'm standing here with Chuck Lynch.
AERA.
We know that one. And Matt from MSH Machine.
Yep.
And you do a little bit with diesel stuff, right?
Yeah, that's our main thing.
That's your main
Sure
thing?
is. Yep.
You brought this beautiful looking, well now beautiful looking
Duramax head.
Head in for us to play with today. And we're here to just hang out, talk as we have all day today, a little bit about gaskets, surface finishes, and the ins and outs of surfacing.
Yeah, so we're not just trying to make the head shiny and pretty, right?
Right.
There's actually a method to our madness, what we're trying to achieve here when we resurface cylinder heads. So actually, you know, when we talk about surface finish on gaskets or cylinder heads and whatnot, what dictates the surface finish that we choose is the type of gasket. Whether I got an aluminum head or a cast iron head block, that really doesn't matter so much anymore. You take a look at all the bi-metal stuff out there and what's changed over years. Like this is a small block Chevy composition gasket. They're paper clay, Kevlar fiber on a, you know, some kind of core material. And over time, they've evolved pretty much across any type of engine. And we're looking at multi-layer steel shim gaskets. So in the past, surface finish was kind of, we had a rougher finish maybe on a cast iron block, a little bit smoother finish on an aluminum head because we didn't want the expansion and contraction of the head to shred the gasket. So as we've increased more power per cubic inch and so forth, we've gone to MLS gaskets, we use torque to yield head bolts, and these layers, you know, one is against the block, one's against the head, and then you have a stopper layer which is going to control your thickness, but they allow for lateral movement and expansion and contraction, expansion and contraction. And with 9.0 I have all that movement. I want to reduce that high friction, as I mentioned. You know, you don't want your gasket shredded by the surface finish. So now we try to get as smooth as possible.
So that's where the, you know, the whole thing, so it's always been that since MLS came out, it was
smooth.
That's smooth. That's right. How does it play in? I mean, Chuck, you know, the applications beyond just, I mean, you made a step back. If you're, you know, the grocery getter, we were talking about the grocery getter, a little high performance, you know, all the way up the diesels. Like, where are you looking at with gaskets and different applications? Or is there anything that
you know, that's a good question. It's really interesting because we always say that the performance world kind of sets the precedence for what we'll see on the street ultimately.
It does.
You know, because they push the envelope. And the MLS gaskets, you know, we know the names. I mean, the one that really resonates in the performance world to us is like Cometic. And, you know, and that's like their thing is the MLS gaskets. And they're in every application of high performance gaskets typically, right? But, you know, L-Ring and Felpro and Molloclevite, and they're all in this gasket game. But it's all the same thing. We're looking to be able to react to the head lift, maintain combustion seal.
Keep the clamping force there that needs.
Yeah, but what we're doing here, I mean, like I say, it's not just about shiny. We're trying to make sure that surface is not only the roughness that we want, but we have to try to achieve a particular flatness. And you know,
yeah, I mean, you know, it's you know, what we were talking about earlier is we always get, I mean, it's surface roughness. As soon as you get one of these profilometers or something, you can go off the rails, and we all do it because they're fun to play with. But you know, those things, you got to sample too. And even with roughness, Volvo has a study, and they averaged that you got to take 26 measurements with a roughness gauge to actually average that out to really say, yeah, I know what that surface is. Right. That's just to do one thing. And then if you do all that, we don't talk about these other things, the geometry of the head, the parallelism, the flatness, you know, waviness doesn't even, it's really just kind of starting sometimes to come into conversation with a lot of people.
And if you're not measuring, you're guessing.
If you can't put a number to it, whether that number is even good or not, that's a great point, man. I mean, whether that's good or not. And so while we're on that, let's touch on that point with your shop.
Yep.
You know, where have you gone with it as a guy who's out there with diesels and doing all types of different work?
The profilometer, man. I mean, again, it's
on the profilometer.
I mean, nobody can walk up and look at a head and actually say, oh, it's got a 20 RA or it's got a certain RZ. You know, over an average, you need to invest in a profilometer, and you need to have the software to be able to test, so you know what you're doing and what you're putting out of your shop for your customers.
Yeah.
Right, and you know, as we, again, the power per cubic inch that we're trying to achieve now, you and I discussed earlier, 2.7 Ford EcoBoost is 167 cubic inches, but it makes the same horsepower as two 464s.
Right.
And
it's a small displacement.
So what we used to get by with, you know, when we would just use a comparator and say, oh yeah, that looks like the same surface finish, you know, the days of dumb luck have passed us by, you know, because we're challenging everything, you know, how with tunes, forced induction, the materials, we're trying to take more and more mass out of everything, right? So the smaller footprint we have, we press it even that much harder. So things like, you know, we were talking about waviness. Waviness is also a parameter that is harder to measure because you have roughness is basically your traverse speeds across and the tool, the type of tool you're using, and that's what gives you surface roughness. So it's peak to peak to peak, no different than
small
what we're
undulations.
Yeah.
The way I always say, so you can think of waves on a water, or you can think about the road that we all drove in on, and you have big, large undulations and mountains and hills, and then you also obviously have some texture within all of those features, right?
Absolutely.
With this, we pick up that texture. These skidded style profilometers they can't get waviness measurements. You need a different tool to look at that and look at those bigger things. Or, which I'm excited to talk about now, you know, let's talk about some of the depression films. I mean,
yeah, so the kind of the one that everyone knows, and there's other pressure sensitive films, but Fuji paper, it's kind of like saying Coke. You know, it doesn't matter what brand you use. You say, okay, we're going to measure the flatness of this surface by bolting this joint together, and then see where the high concentration of load is. And the nice thing about that is I could take a head and a block and no gasket and measure and see where the load distribution is, or I can do it with the gasket and see, okay, the embossment area in the gasket, because whether it's a MLS head gasket, we have these embossments that put really high concentration of load, and you know, because you fire ring a lot of applications,
a lot of these.
So you're trying to increase that load even more.
Correct.
And more of a traditional gasket is going to have what they call flange over body balance. So we're looking at the flange around the combustioning open that is actually greater than the body, because we want more of that stress applied right around the combustion seal, because that's the hardest part to seal, right? But there's a balance. If I get too much combustion seal, then I leak coolant, I leak oil, I may, you know, the oil returns, the high pressure oil, things of that nature. So it's a real fine balance. Well, MLS gaskets being more rigid, they can't conform to those real close waves. So it's made us look at things different. So that pressure sensitive film can help us answer that question. Hey, am I getting a good distribution of load? Because things can just go haywire on us in the machine shop, right?
Sure, absolutely.
So, you know, maybe it's the concrete floor and I traverse back and forth past it with a forklift. So I shift something and now I have a foot on the machine that's kind of soft. So now I have some waviness, and I always use the example, you know, back in the day when they measured waviness, they used light band technology, right? So we looked for kind of that prismatic effect. Well, if you're in a stand back at the right angle, sometimes you can look at cylinder heads and it looks like a rainbow. And it's very uniform frequencies. Well, that's one indicator that I have waviness.
And you have a very, share with us that story. I mean, you were talking about it, and you've been in shops and been in those situations where you're like, yeah, you begin when you do it enough and you were putting numbers to things, you're correlating seeing that rainbow to that number.
And then
and it's real and it's tangible, and then put a number to it and you go, whoa,
Yeah.
Time to
We
start
actually,
packing things back.
you know, looking back in history, have taken machines out of manufacturing for that, because then when you would do the pressure sensitive paper and look like, wow, there's no wonder that thing always blows gaskets toward the intake, because I'm not applying that load there. So just because it's shiny doesn't mean that it's flat. But that's why we have the gauges to check this stuff. We have, you know, it's a plan, do, check, act, plan, do, check, act, you know, and what's the check? You've got to have the check in there.
Well, something I'd like to touch base on too is your profilometer can also be used to check your equipment as well when you're getting a dull cutter.
Right.
Or maybe a bearing or something maybe going out in the head of your machine, right?
Right.
So get in the habit of checking even your stones on your home. That can load up with metal.
You know what? That's a perfect, because I do those at Rottler as the applications, and you're just whacking at inserts.
Yeah.
And we've learned that on cast iron, around 45 to 50 passes, that edge is gone, because you see, like you just said, that RA, that finish, or the RZ, whatever value you want to track, it will start growing 10, 15 points. You go, time to change that cutter. It's a powerful tool.
Exactly, because otherwise we would be able to say, set this speed, this speed, it's got this size insert. I could calculate it with math and say, why do I need a profilometer? But again, we know that things change in our environment. The tool changes, the setup changes. You know, we messed around putting this head in different locations as we were doing some machining earlier, right? So you have to really test what did I change in the environment that may have
We even
impacted
talk
the
about
road.
even the mixture of your cooling. If you get it too slick, then
Yeah, if you're running a
obviously we're
coolant
going to run
machine,
into a problem. So there's so many variables that can be brought in from the outside, whether it be on purpose,
Well, and
accident,
even,
or whatever. But this
you know, we
is
spray
sandy check.
WD-40 on these, or, you know, well, everybody's got, there's PAM, Remington gun oil, Windex, hand sanitizer.
Sure. Try everything.
Everyone's got everyone. But, you know, it is true. You know, you can add these lubricants or adding just a little bit of something, and experimenting can
Change your
often lead.
recipe.
It can cool things down just a little bit more. You know, I think, and that's obviously what all the viewers here, you know, taking all this stuff back, it's like, well, yeah, I clearly need profilometers, but that is it, you know, educating people to say, okay, looking at the application and starting with that and what I need to do and how many I need to do, what's the equipment, and what's the system that has to go in place, right? I mean, you gotta know the application, you gotta know which gasket, you need to be able to check it, and you need the setup and the process and the machine tool and the inserts, tooling, to continuously do that properly, right?
And journal it. I love to journal my stuff, whether it be in Excel, on my laptop, in a notebook. Journal your stuff. Keep up with your work. If you're a racer, you go to the track. What do you check? Air temperature. You know, tire pressure.
Write it all down. That's right.
What was it when I went to the last track? What's not going right? What's going good? Going bad? I journal everything. That way, I know if I'm going the wrong way, something's going, you know, the wrong direction. Then obviously, I can get that to where I need to get if I keep a note of what my stuff is. I keep my software here with Mark, which is what's Mark?
Trace box.
The Trace box.
Yeah, and that's what we got on the
I
laptop.
love about the Trace
We've
box.
been showing it off on the
Yeah,
hone,
we
and
get to save everything.
having it, and you get that printout.
You get your customer's last name, you get everything,
and you can give
go
it.
back
And you know what I like about that is, like I said, you can track it, and if you do work for someone, you can print that out when you're done, and you can hand it to them, put it in the box with the head, put it in the box with it, and say, here's what I've done for you, and here's, you know, and we can have this open, honest conversation. Be transparent.
And what drove you to that point? Cause and effect, right?
It was.
Cause
It
and
was.
effect.
And then you get to send it in an email. Like if I send it to somebody who knows about it a whole lot more than me, I can say, hey, take a peek at this. Tell me what you think. You know, what can we do? Throw ideas off of other people in the industry. It's a very powerful tool.
It is, because, you know, I use the analogy often that you don't know what you don't know until you know, and then you realize how I don't know anything, because, you know, when you're looking at failure analysis, okay, a lot of people are like, I've never seen that before. And then when you explain how that is a failure, sometimes you're like, man, I've had that failure a bunch of times and it is my fault. I just didn't know what the contributing factors were.
Right, and sometimes it can be one, maybe it can be two or three. You know, that's a staple is going to engineering school and through that process, the testing, that methodology. I mean, what you're talking about, these things, that's fundamental, you know, failure mode analysis, and that tracking, like you said, whatever you got to do, whether it's notepads, sticky notes all over your refrigerator, Excel, something.
Yeah.
If you don't have that, or you can't at least, you know, be capturing, you know, 60 or 70% of the time, so that you can look back and say, you know, maybe there is a trend here, because trends only appear. You don't know what you don't know,
right?
And you have to look at trends until you say, yeah, maybe I'm seeing something here.
Right, and that's what these videos are they're really trying to do is, we know that not everyone has the profilometer. They may not have, you know, a pat gauge to measure the bore cylindricity, but we know that the research has been done to say, with this particular tool, I'm going to improve my chances. And then I get a tool that is reasonable for me to get, because not every tool is reasonable for us to get. Am I going to get a $150,000 pat gauge to measure my cylinder bores? No, but I'm going to buy the right tools and I'll measure what I can really control. Because my process will control surface finish.
Well, you know, you've got, and it's any problem in the world or in life, there's knowns and there's unknowns. And the more of those knowns, like I said, using all the people in this industry, there's so many people, you know, so many people putting out great content. This video series, not just us, you know, talking to people like Matt, talking to guys like Chuck, any of the AERA stuff. You learn from that and you say, okay, now I know a little bit more, enough to be dangerous. But you can start to focus your mind and focus on things, like you said, figuring out maybe some of these unknowns. But if you can pare that down so you can really pinpoint in on there, and you know, by using the tools that people are vetting and vouching for and using them in the right way, then you can really get...
And you're giving out a better product, man.
Better product, and life's good, and it's easier, and you have a little more fun, right?
It makes you more money.
Because nothing's worse than when something comes back.
That's right.
That's right. And you know, and these parameters, you know, that we're talking about, they're not something that we just made up. And we have a bulletin on the surface finishes that are required for the different types of gaskets, how much out of flatness over a particular distance, you know, the waviness specs and tolerances. And where did that come from? The guy who makes the gasket, because they know what environment their gaskets will live in. So we have to be able to try to achieve that. So they give us the parameters, we measure against the parameter, and we should be good to go.
Yeah, and what Chuck's saying is, don't forget to pick the phone up, make a phone call. Call the gasket manufacturer. They're going to tell you, if you have this tool and they give you a benchmark to hit, then that's what you want to do. You're taking the guesswork completely out of it at that point.
And Chuck, just so everyone knows, I mean, those bulletins, all that, it's all available through AERA.
Yep.
It's just
right. AERA is a membership. It's a trade association for engine machinists. So AERA is 101 years old this year. It was Automotive Engine Rebuilders Association. It's mostly known as Engine Rebuilder Association now, because we're so far from being just automotive.
Right.
Everything from Acura to Zador, like the tractors, the 3600 cats to single cylinder pony motors.
I mean, I've been on ProSys and been using it for a couple of years now, and some of the products and all the bulletins here, the knowledge is.
Yeah, we have a.
It is such a leg up. I mean, if you were just going through the dark without that.
Yeah, man, that'd be rough. That'd be rough.
And there's so much to know now. It's not the day of everything that comes in is a small block Ford, small block Chevy, big block Ford, big block Chevy. You know, now you're doing a Kubota and then an Acura.
Well, we got 6-7 Power Stroke, for example. They've done changed the wrist pin 3 times from 11 to 2023. So go straight to ARA. Boom,
and I think that's
somebody
having something like that, an online database, the internet being sometimes good, sometimes bad, as we're talking about. But having it where it gets updated, and you've got great people managing that, and you've got videos like these and information. It's the information age. I mean, get out there and get it. You know, let's just roundhouse this real quick. Maybe Chuck, you give a couple, I'll give a couple, and Matt, you give a couple. I'm just a couple tips on servicing, things you would wish you'd known, or anything you've got, people. Maybe 1 or 2 quick hitters, or things.
Yeah, I guess
things to pay attention to.
You know, if it's warped too much, you got to be careful about other things that can be a problem. You know, as you mentioned, that laundry list of things that we need to pay attention to. So if a head is warped a lot, you probably need to try to straighten the head somewhat, because I'm going to affect the combustion chamber volumes. Maybe a cam won't turn in the housing bore. You know, if I take 18 off of a head to get it flat, my end chambers and my middle chambers are not the same.
That
so things of that nature. So you know, give those things consideration. I know that we want to get that head turned around for the guy, but that's a reflection upon yourself if you put a head out there that they can never get it tuned right again.
Sure.
And again, we talked about the MLS gaskets or the conventional type gasket. find out what it needs, because you want it to perform well for you. So you don't want to resurface too rough and shred that conventional gasket. You don't want to have an MLS gasket that's leaking like a sieve, because they have cold seal. Both, this is an older technology cold seal, which is like a silicon material, and you can feel it.
Yeah, you can feel it.
It's very tacky.
Oh wow.
These are modern gasket cold seals, and it doesn't feel like it's there, but like one of the things, you take a razor and create like a checkerboard, and then a high adhesive tape, and you can peel that stuff off. Well, under that coating, oftentimes that's just, a nice shiny steel.
Really?
So these are very dry coatings. That way when they pass by things, they don't pick up every little bit of fuzz and nastiness that's in the world. So I guess that's a couple of my kind of tips.
While we're on the MLS, what's a reasonable number? What would you look for on the profilometer, and what factor would you be using? RA, RZ,
So,
what are you looking for?
RA is a number that a lot of people were comfortable with now. When I first got into the business, there was still a fair amount of RMS. RZ is more of a telling parameter that works for us, because I'm measuring the 10 peaks and 10 valleys, so it's the average total height, rather than, RA is just the average roughness. So it does give me more dimensional data. So, as I was talking about, we're trying to cold seal. So if I can look at that and say, okay, I know the peak to valley in a nice uniform measure is this high, well, that still gives me a lot of opportunity for coolant to leak through those gaps, or combustion to leak through those gaps.
Sure.
So that's a good parameter to know. So RZ, and then MLS gaskets, you're going to, 50 to...
Well, the answer is check with the gasket
Yeah,
supplier
yeah,
first,
the gasket
rough
supplier.
numbers,
but
50 to 60 is probably on
yeah,
RZ.
so with RZ, yeah, you can't MLS gaskets. We can't really resurface too smooth for those.
Yeah.
There's not enough time in the day. You would have to really lap
it all down. Yeah.
But milling, which most of us do, we mill. We're not going to get too smooth for that.
Right.
And then the composite gasket again. We've got some parameters that come from the gasket manufacturers. Just but yeah, RZ is a more telling tell of what's really happening. No different than, there's a different set of parameters for cylinder bore finish than there are for gasket surface finishes and whatnot. And Mark does a ton of presentations on all the different types of finishes. They have the place, So to say, I've seen where some folks have been talking about, measuring gasket surfaces, and they've been looking at RK and RPK and stuff. That's not really telling you what you need to know for that particular environment.
Sure.
So,
Yeah, and I think just going down on it, my two tips, if I was saying anything and being on the machining side, is picking the right tool, make sure you're using the right insert. Use PCD for aluminum, use CBN for cast iron. I don't think we can seem to beat that one in anyone too many times, because I even do it sometimes. I use the wrong insert. Just always got to keep thinking.
it's costly mistake too.
Yeah, and for me, I always beat the dead horse of, with any machining operation, it's the setup. Garbage in is garbage out. And Chuck, you hit on a good point. Leveling these machines, these beds, you might have had it level at install. Your floor is sinking, the forklifts are driving by them. Over time, that thing's warping. And for probably, 99% of us, we're leveling these heads or we're sweeping them with a dial indicator.
Exactly.
And all that's all we are doing. We always talk about using datums, and the datums we're using is a datum done by someone else at that point.
Right.
And you don't really know if that, we're making that assumption that, yeah, that was okay to start with, and I'm going to make it a little bit better. But, and it's fine. There's nothing wrong with it, and that's the way that we process a lot of stuff. But I think having that open knowledge and questioning that, questioning, I'm leveling this, but, I'm touching down here, and I've got a level on here, and I'm sweeping here. I could have some kind of funky angle going on, and that, like you said, you could have a banana in this thing, and it could be the other way. And just having an intuition, I think a conscious, mind towards what am I really measuring and how am I really processing this, and what is it going to end up, what's the gasket going to see? Mm-hmm. That would be the way.
And for me, my biggest thing, you've already touched on one, is the tooling with the bit or the cutter. The second thing that we haven't talked about, and I want to open up a whole can of worms with it, but that's your speed and your feed rate.
There it is.
So that's going to dictate a lot. If your aluminum obviously carries higher RPM, your iron and stuff like that goes with a lower cutting RPM, and then you can play around with that either way to get your best finish. But again, when you do that, I like to use a little bit of WD-40 on the end of a cut. You know, my final cut, I'll normally kind of just spritz a little bit of WD-40. It seems to make it pretty. You know, and when I run my profilometer over it.
Well, with the aluminum, you get those track marks.
Sure.
You know, aluminum wants to stick to that cutter.
Yep.
And that's why we use the PCD, but you really even still get a little bit. And like you said, feeds and speeds, so critical.
Feeds and speeds are huge.
So critical. All right. That's it. So, hope you guys enjoyed and hope you learned a little bit about surfacing, and we'll catch you on the next episode.
See you later, guys.
Back in the studio here at the Engine Performance Expo. A lot of information right there. We've got some information for everybody out there right now.
Yes, so weather alert. So this is East Tennessee, which I love East Tennessee and have a lot of experience here. And one thing about East Tennessee is, you know, like the weather, wait an hour or two, it could change. So what's happening is outside is in the next hour, right around 2 o'clock Eastern time, there's a pretty severe weather system that's supposed to hit this area. So we might lose power. If we do, we have a plan. So hear me out. If you're going to be hanging out with us all day, which we appreciate people hanging out with us and watching all day, if we do lose power, the stream will die for a little bit. We will come back because we have backups, but it will be a roundtable format to close out the day. If there are tons more videos we're going to show. Here's the thing. If you've registered through engineperformanceexpo.com, we can then email you links to all the remaining videos that you can watch it on your own. Obviously, we got the YouTube channel. They'll be there as well. So just know that there is a plan in case all of a sudden it's dark.
Right. If we're just gone, you know what happened. I am from South Florida. I am from hurricane country. I am not afraid of big wind, except I am. And so we are taking all precautions to make sure everybody's safe, and obviously people got to get home and whatnot, but you will see the content regardless. But until that happens, it hasn't happened, and we're going to proceed.
Absolutely. And like you said, a couple of guests that were going to be live guest interviews. You notice the schedule may change a little bit because some people needed to make flights and get out of town because of the weather. So again, everyone here is volunteer. Just know that everyone that's a part of the Engine Performance Expo, they're doing this as part of their love for the industry. So we appreciate that. And if they got to make it back for a football game or homecoming or whatever, they need to go, and with the weather. So there might be a few changes, little tweaks along the way, but be worth hanging out and staying because we got a lot of really great stuff coming up, especially an interview with one of my favorite guys who has my favorite nickname for me.
Yeah, lack of speed. Let's check out an interview with Jason Line.
We have an opportunity here that rarely ever happens in my lifetime. I get to work with a genuine racer, a bona fide racer. This guy has started from grassroots, stock, super stock, and gone to the highest of pro stock. What I would like to do is, Jason, I'd like you, before you just give me a quick synopsis.
Yeah, I actually started bracket racing when I was young. I thought I was pretty good at it. Probably wasn't as good as I thought, but kind of evolved into stock eliminator with the influence of some friends, some of my dad's friends, and yeah, it's just sort of a good hobby that got out of hand, really. So, but it's been fun ride, of course, and racing's been good to me and my family.
Well, we're in my business room. I would say this is where you have made your success by collecting data, understanding dyno, and just beating on things to find ways to make more reliable horsepower. Fair enough?
Yeah, fair enough. Yeah.
All right, but now all of a sudden, I think we're on a new venture for you. I think you've gone to the next level.
Well, trying to, for sure. You know, trying to make these engine blocks, which has been a favorite saying on that is every university costs money. This one's no exception. I stole that from Bob Fox, and it's been a very hard process. We're still learning, constantly learning, and it's evolving, and it's been fun. To say it's been a challenge would be an understatement.
Well, you know, the old saying, the only constant in life is change. Racing that is it in a nutshell. Yep. What we did yesterday is a memory. Yep. Now, maybe we learned something. Sometimes we learn what not to do more than what to do.
Yeah.
That generally has a whole bunch of parts involved, and they're not original state.
Yeah, they changed the way they look for sure. Yep.
Yeah, so the power making that we've done now, that's really the big change. And the key, though, is keep that power contained. In other words, making parts break is not the goal. Making power that's going to generate energy, that's your goal, right?
Yeah, for sure. Yeah, well, you want to make something better. I mean, I don't care what you're making. You're making widgets, right? If you make a widget, you want to make the best widget. If you look at every single part of the race engine, right? Every single piece of it is better than it was 10 years ago and 20 years ago and 30 years ago. And they say, well, why don't we just make it right the first time? Well, it's not possible. The environment changes and the needs change. It has to evolve. There's just no quick road to do that. You can try to speed the process up by having more, better people and test things faster, but it's still, technology changes at a certain rate, and not all of it's the same rate, so you got to grow with it.
Well, learning, you exchange time or money for wisdom, fair enough?
Yeah, absolutely, yep.
So, and the cost is always, that's the part that hurts.
Yeah, painful.
And sometimes real painful.
Yeah.
But that's not our goal. Our goal is to make sustainable horsepower, reliable horsepower.
Yep.
Well, this new engine combination, I mean, that seems to me, in discussions previously, that seems to be your total focus, is making something that can work.
I had a hard time getting engine blocks, so I said, well, we'll just make our own, which again is it's a romantic idea. I'm not sure it's always a great one, but so not just make one, but let's make it better as long as we're making it. So both my partner and I were both naive going into this. I don't know, maybe thinking we knew exactly how we were going to do it. I was very naive in thinking that everybody's thought process on how to build the engine was like mine. Well, obviously there's a lot of different ways to skin the cat, and it's not that anybody's right or wrong. There's just different ways of doing it, and for their particular needs. The good thing is, we're small. We can try to adapt, quicker.
Yes. Challenging.
But very, very challenging. Yeah. But we're going to make it better. We're going to make it the best. The goal was not to sell the same thing everybody else has, but sell something that's a level up. And and saying it is one thing, doing it's another. It can't just be fluff. There's got to be real substance behind it. So that's what we've really put our effort into in trying to make that. And the truth is we don't know. There's a lot of things we don't know, but we're learning. We're going to figure it out.
Well, I can say this: someone who has absolutely no background, or let's say less background than you have, that's Russian roulette.
Yeah.
Right. You've tenured yourself in the industry, and you've learned and exchanged a lot of time. You've seen things work and not work. But you're also in an era of engine building that used to be, we were mostly in the industry of normally aspirated motors.
Yep.
Now, we did have some blown applications, blown alcohol, top fuel, so forth. Those are a little bit different deals where you play, but your engine does have the chameleon ability to be normal aspirated, or in this case, you're looking at boosted.
Yeah, that's the plan. And again, with the help of some friends and customers that build different types of engines, they're helping to push us forward to make sure that we're making it better for everybody's application. If somebody wants to make 2,500 or 3,000 horse of one of these, we got to make sure that it does have the ability to do that and to be structurally sound. So.
Well, that is one big challenge, but I just got to tell you, you have grabbed that tiger by the tail.
Yeah, it's definitely a challenge, and but it's also a doable one. So there you go. It's very doable.
Can you talk about a couple of key points you think that it's a little unique, or how much do you want to keep this under your hat?
As you and I talked before, and I say this with everybody, I didn't want to come out with everything until we're really ready, because the worst thing you can do is say, oh yeah, we're going to sell these engine blocks. Okay, I'll take one. Well, I don't have any. And I've already done that with a couple of people, of course. They're friends of mine, so they're understanding. But we've sort of weeded things out, onesie, twosie at a time. We can't produce, super high quantities of them. We're trying to make something that's actually better. So nicer. We probably won't be for everybody. Obviously, financially, they're going to be a little pricier. But the block will be a little nicer than what's out there.
Well, one of the things about racing over all the years I've been associated with, sometimes we put price in front of quality. And in the old days, that was bad, and today it's still the same.
Still bad, yeah. Yeah, but everybody's on a different level financially. Not everybody can afford to have something, and I've been on all sides of it, like where you bought what you could afford to buy, and that's the same thing. Obviously, we're looking to, again, make the best thing out there, so it's not going to be the cheapest.
Well, the ultimate, from my perspective, is if you make good, reliable horsepower, then you have a better opportunity to win.
Yeah.
Blowing it up every time and maybe win.
Yeah, you're not saving money.
No.
Unfortunately, Danny Jessel, he pounded this into my head, and he's 100% right. Don't try to save me money, because every time you try to save me money, it costs me money. So, and it's very true because when I take the cheap route out, it ends up costing me time and a half again because I end up having to not only. I wasn't happy with the first one I bought. I had to buy the second one, the right one, the second time. Well, that costs a lot more money. So. But again, everybody's at different spots, and I get that. We can't cater to everybody, but we're trying to make the best thing that we can possibly make.
Well, it also sounds like your future looking in your design. In other words, what the horsepower we made a decade ago, 5 years ago, a year ago, none of it's gone down.
No.
Everything's gone.
No, 30 years ago, if somebody had an engine that made 1,000 horsepower, that was like insane. Well, now. That's like beyond commonplace. It's like everywhere, right? So, things change, and you got to change with it. And surrounded by the right folks who are forward thinking. That's what you got to do.
Well, one thing that I've admired about you've accomplished is that your design and everything you're working for is still linked to your knowledge and the working relationship. That this is a system. And that is, I can make this and buy some really good parts, but they have to work in harmony. They have to be in design efficiency. But the tuner, that's you. You're one of the guys that have a history of being one of the best. So you understand how bad tuning can cause you a lot of problems.
Yeah, there's no question. I don't know. People like to put people on a pedestal, and I don't like to put myself up there because I don't know that I can live up to those standards. But you do the best you can, but you got to look at the pieces and parts afterwards. They're all telling you a story, of course, and again, going back to the block, you don't want to build your house on a pair of twigs, right? Like you got to have a good foundation, so it all starts with that. But the tuning side of it, it's a huge deal. A happy engine is going to stay together for way longer, and certainly in a bracket race type application, the better it's tuned up, the steadier it's going to run, and the better it's going to follow the air.
Well, see, that's where I think your background lends itself to understanding what the block's going to go through. You've sort of learned the weak parts. You've learned the areas that you need to strengthen or redirect, oil, for instance. Last time I checked, most of the objects that we have moving require oil.
Yes, sir.
Rather consistently.
Yeah, well, not only that, but I have good feedback from other folks. I mean, I know a lot of good folks in our industry who have a lot of good ideas. So I try to, tap into that, because the more experience, the more you can listen to other people. Again, you should be able to make a better product that fits everybody's needs in the end. So again, that going into it, I sort of made the assumption everybody built the engine the way I wanted to build it, and that is not the case. And there's a lot of good ideas out there, and again, tailoring it to a specific need is still key. So the block has to have enough built-in tools to be able to do all those things.
Well, I'll be redundant here and simply saying, like anything that's being built, is based on a good foundation.
Yep.
This is where you have targeted.
For sure.
There's a lot of other areas. In other words, there's one thing to make power. And there's a lot of really smart people in the industry. We know how to make power. The question is, can you make reliable power? Yeah. And within that reliability, that gives you the opportunity to now go to the next level.
Yeah.
But if you break parts, just because of lack of knowledge or whatever, that's the wrong trip. It's a road backwards, right?
It is.
That's where your experience checks in. I think this is what's going to be a key catalyst to the quality of your product. I think this is where the industry it needs it, and I'm not disrespecting anybody that's doing this. I'm just simply saying you've been there, done that, got the T-shirt. Yeah. And so I think you've already convinced me of your passion to get this right. That's one of the things that'll add a tremendous value to your product. I think you got a home run headed your way.
Well, I hope so. We got the easy part done. We talked about it, so So actually doing it is the hard part, but we're getting there. We're making progress for sure. Trying to look at all, everything, not just the design, but the metallurgy, all these things. And of course, I'm not an expert in any of those areas, but I've tried to make a point to know an expert in all those areas.
Yes.
And so, if we can put all the pieces of the puzzle together, which we have, it's the fun part of racing. If you stand still, if you don't try to get better, you're going to get run over. So, and the same thing with every part of the engine, including, if not especially, the block.
Well, you were tutored and somewhat mentored, I would say, by Dan. Mm-hmm. He was right in every respect of what he said.
Yes.
And you seem to cling to that policy.
Yeah, for sure.
So I think that'll carry the merit to the durability of your engine. I know you're confident in where you're going with this, but you're also humble enough to have that question mark still in the background.
Well, you have to question everything for sure. I think no matter how good you think it is or you are, you still got to try to make everything better. And so I think that in the end, that's the strong point, because in racing, if you sit still, you're gonna get run over. And the whole quest is to make it the best it can be. So yeah, it's pretty good, but it's not as good as the one I really wanted to get. I mean, who wants to do that? That's the ultimate goal, and it's got my name on it. So I don't want to sell something that's not good, not the best.
Well, I want to sort of summarize this by saying that, number one, thank you for this opportunity. But I meet a lot of people all over the world, and I play Formula One down to guys race go-karts, so forth. The winners all share your philosophy, and I'm not trying to box anybody in, but I got to tell you, that philosophy is the key to your success. Your commitment, and now it's your name on there. By the way, how did you name the company this time?
Well, I don't know exactly how. I'm not even. My brother has a place up in Minnesota called Line Performance, so we just put the J in front of it. It just became J-Line. So my son made the logo for us, and he's super interested in all this stuff, and it just sort of evolved into that.
You hit on a key point, and that is father-son. What an opportunity. Your son, based on the conversation, is all in.
Yeah, I know he is. He doesn't know anything else. He's been raised in the racing environment, right? So he thinks this is normal, and it's his normal anyway. So yeah, he's excited about it. Migrated towards the making of parts. He doesn't want to be an engine guy, but he likes making things, he likes machining things. So hopefully that's a good fit for us.
Well, it sounds like a good in-house link.
Yeah, no, for sure. Well, you got to do something for a living, right?
Yeah,
so,
I can imagine the dinner table discussions are rather different.
Yeah, probably a little unique. Yeah.
Well, listen, I want to, number one, thank you for taking time. We interrupted your whole day, but the bottom line, this is your magic. This is where you make things happen. I'm looking forward to seeing the product, and I want to basically say I understand you're throttling this and release.
Yes.
You are not anxious to be a volume-based company. You're out a quality-based company.
Yeah, 100%. Yeah.
Well, for that, I want to thank you for your time.
Thank you. I appreciate it very much.
Yes, sir. Thank you.
Hi, I'm Jesse with Engine Pro. I'm here with Alan, who is our product manager for Engine Pro Products. Today we want to talk about timing components. Alan, give me a little idea. How long has Engine Pro been in the timing business?
So Engine Pro's been in the timing business for over 20 years. We offer top quality components designed and engineered right here in the U.S., but we also utilize the top quality manufacturers globally. And so we pride ourselves in the fact that we try to make as much of the product here in the States as we can, but we also recognize that in a global economy that there are some really high quality manufacturers globally that we've been able to tap into and use as well.
Obviously today's timing business is not as simple as a three-piece timing set. So give me a little idea about the options that are available through the Engine Pro program.
Yeah, I mean, Engine Pro's timing has kind of followed suit with the rest of the car industry. You start out with the conventional, we call them kind of the legacy, let's call it American V8s, your Chevy small blocks and Fords and Mopars and the three-piece timing set that we're all familiar with. And a lot of them came with cast gears and single chains, and so we would develop along the line with that to where, yeah, sure, we offer those, but Engine Pro's really always been more of a high performance and racing brand, and so we followed suit with the high performance and racing industry, offering not just the single row chains but the double row chains, And those have developed along the years, where we have the multi-keyway crank gear, which gives adjustment, and then also the top gear with the adjustment bushings, where engine builders can really dial in the cam timing. You know, we've moved from the conventional chains that we used to see in the OEs back in the 60s to a lot more advanced, roller chains, seamless, and larger diameters too, going all the way up to 250 diameter. So these are just some of the changes that we've had to make, even in the conventional legacy line. But then you start moving into today's vehicles, and like I've got an example right here of a modern Hemi. And you just look at the difference in componentry with this one, and this one's not even the most components. You start getting into the Coyotes and some of these overhead cam engines, and we could fill up half the table just with a full timing set. But this particular one here for a Hemi, we're kind of proud of this one. Like I mentioned, the double row chain, seamless, roll-on chain. We also have IWIS chains available. This one has got that 9-position crank keyway for adjustability. But we've also got on the camshaft gear itself, this is adjustable plus or minus up to 6 degrees on the cam sprocket. And so this is the kind of direction that we're going with a lot of the product line these days.
Well, again, we're more than just performance, right?
Yeah, we can do everything. A lot of these kits, sometimes you want to just replace a chain, or maybe just a chain and a tensioner, or a chain, a tensioner, and a guide. We have those kits. But in a high mileage engine, you're probably going to want to replace the gears and replace the phasers and all of the componentry that comes in these kits these days. That's why we offer these different levels of kits.
Give me a little idea why Engine Pro.
So our motto at Engine Pro is by engine professionals for engine professionals. And I think the biggest thing that I can say about our distributors and the places that you can buy Engine Pro are the people. We got some of these guys that have been on the phone helping engine builders and machine shops for over 40 years. And that's where we set ourselves apart. It's not like a conventional parts store where you got to walk in and say year, make, model, right? These guys have been in the trenches. They know how to operate the machines. They know how to build engines. These are guys that are true engine professionals, and they're the ones that are there for our customers for any support that they might need.
Well, again, given the complexity of some of this,
that's right.
Our folks can help them.
Yeah, I mean, Engine Pro is a time-tested brand. I feel we represent the best overall value in the timing space, top quality and reliability.
As far as profitability is concerned and support.
I'm glad you brought that up, because that's one of the things that we do behind the scenes. As the product guys, I want to always bring products to the Engine Pro brand that are going to make money two ways. Number one, we want to price them competitively so that at the initial purchase price, you're going to have an advantage there. A lot of times engine builders are pricing as a whole engine build, and I understand this is only one component, but we also want to make sure that the quality is there. Our goal is no comebacks. Our goal is a happy customer, and our goal is to provide the technical support whenever they need it. So these are all valuable services that Engine Pro offers through our distributors and our members.
All right, young man, listen, I want to thank you for taking the time. One thing I'm going to simply say, Jimmy, is that you are a guy of tenure. You've done an awful lot, so I want you to tell everybody here a little bit about yourself.
All right, well, I started in the drag race industry back in the 80s. Worked in the back door Napa store, learned how to disassemble motors and clean them up, and went from there. And finally moved up here, had my own shop in Birmingham, moved up here in '98 and went to work for a Busch Grand National team in the engine shop as an engine assembler, engine machinist, whatever. And I've since gone through Chip Ganassi and retired from Robert Yates. And so now I have a little shop here that I do my own thing since I'm retired, which I haven't had a day off since I retired, but that's okay. Got to stay busy.
Yeah. Well, it's obviously part of your DNA. You love this stuff. Now, you know, with the diversity of all your products, all the different engine groups, you know, from top fuel to the smallest engine you've ever built, inline 4 cylinders, V8s, normally aspirated, power boosted, supercharged. There's a common thread in engine. Now, I can't go into all the things that you know, and like I say, you, again, are one of those guys that have forgot more than I know. But here's one question I have. The common thing about all engines, cranks go round and round, pistons go up and down. Now, in order for that to be efficient, now we have bearings and we have clearances and we have all these things that you take care of in the assembly. But what about balance? How does that play into you?
Well, the balance gives it longevity.
Okay.
It'll run for a length of time, whether it's balanced or not. But the parts are going to fatigue, and it's just like on a 1,000,000-mile diesel motor. The hone has to be right, the balance has to be right, everything has to be correct for it to last that time. So you're adding longevity by balancing. Now, 4 cylinders, that's a different story. They're going to have a vibration in them at some point in the range. By balancing the 4-cylinder, you move the vibration out of your power range and put it down where it doesn't matter as much. But when it's running at peak song, and for a race motor, for instance, the 24 hours of Daytona, that thing's got to run 24 hours. It better be smooth at the horsepower reading where you want to run it. If you're going to run it at 7,400 RPM for 24 hours, it better be smooth there or it ain't going to stay together. That 4-cylinder will machine, it will machine the U-joints out, it will machine the clutch hub out, it will machine everything just like you put it in a lathe and cut it out.
So you have a race car lathe, is what you're saying?
Yes.
Okay.
Yes.
Well, you know, there's all sorts of different theories, overbalance, underbalance, and we accept the fact that people have, especially engine builders, they do come up with what they consider their recipe that's optimum.
And the way you get the recipe, you don't get it from your drag racer that you see their motor once a year.
Okay.
You don't get it from your boat guy that's out with his family. You get it from the engines that you tear down every week. All right, and that engine, if you pay attention, will tell you what it wants. But you have to look at it every time. I mean, a top fuel engine, you tear it down every run. You can look and tell. You can actually tune by how much it crushes the bearings or whatever. The stock car engines, you can tell if it's burning the push rods up. You can tell if it's out of balance if the bearing's fretting in the rod. If it wants a little overbalance, or if it wants a little underbalance. It'll tell you by the way the bearings are moving in the surfaces. And you can, if you look at it every week and you find this is wrong with it, and you work on that problem, and next week that problem is better, you know you move the right direction. Sometimes you move the wrong direction.
50-50, yeah.
There's not a one-size-fits-all for anything. And there's not a drag race motor is not the same as a round track motor, and a round track motor is not the same as a street motor. It just don't work that way. They all take different clearances and different specs, but the balance is the most critical to making longevity.
So basically, though, whenever we do this kind of interpretation of how to handle things, the bearing is the go-to area, right?
I would think so.
Yeah.
Yes.
That's the scene of the crime, right?
Right. And if you look at the bearings every week and you adjust your balance up or down, when you get the bearings look like they come out of the box after 500 miles, you're pretty close, whether it's balance or clearance or a certain type of oil.
Sure.
But it's all works together in conjunction.
Well, one of the things there is, a lot of our work covers a vast array of engine application and racing, drag racing. I always joke about it that if you took a season of racing, they didn't have an hour on the engine.
Right.
Right. And then, of course, I go to a road race course that's, let's do a 24-hour in Daytona. That's 24 hours.
Yes.
Okay. So this thing is just constantly just wearing. And I always use the term, a little baby with a little hammer unattended can destroy anything.
Right.
So it's a matter of this little bit of energy that's pragmatic, won't release, can't change. It's not like you change a spark plug and clean up a cylinder or change an injector or something like that. Balancing is forever. We agree?
And balancing is forever. And the only thing that, the worst thing that can happen is you lose a cylinder in a motor, because then you've got firing pulses that are out of balance.
There you go.
And that's why you have a harmonic dampener and stuff on it, to take care of that stuff that you can't do on the balance machine.
Absolutely, that's an excellent part. In other words, this part right here in this machine, or any machine, let's be fair about it, can only do what's called first order balance.
Right.
But at every 90 degrees on a V8, we get a power stroke, all right? So what we have is 4 cycles plus the first cycle. Now, one of the things we do want to do in balancing is, we'll notice on this particular crank, this is, the counterweight at the moment is straight up, and you notice the rear is straight down. If I was to draw a line from this tip to this tip, ideally it would go right through dead center at the main. Well, that's what this optimum balance situation is. We want whatever energy is here. I'll just use 10 grams and 10 grams, or let's make it 100 and 100. If it goes straight through, it's 0 right here, right? Now, unfortunately, we'll see situations where this one may be here. That's where the load moment is. And then this guy is here. In other words, they're not canceling, all right? That's called coupling. If you can't couple, then instead of having 1 pulse, you'll end up with 3 pulses. Now, the problem with that is, as we decrease the magnitude, that is the amount of energy. But however, I'm back from big hammer to little hammer.
Right.
Now I got 3 hammers on 1 rotation, plus the 4 power strokes. So you can understand, the connoisseur like you are balancing, you're going to sit there, oops, excuse me, we're going to try and get these at the end in opposites, agreed?
Yes.
Last thing we're going to do, though, is we're going to try and set a standard for this. Now, we have a calculator that's set up, and it's based on the ISO, just for a point of reference, it's called 21940. In the past, GM Motors, Ford, Chrysler, all of them, their OEM work, they had a generic tolerance of 2 ounce-inch. Now, to throw that real quick, because depending upon the counterweight, that's somewhere around 20 plus grams. And this was A-OK for down the road. This is not your father's Oldsmobile. This is a different gig. So now we can go in here, because this is an international calculator, so we know this cumulative with the harmonic balance and so forth is somewhere right around, what, 65?
I think we said 65
65 pounds. All right, so we'll enter that. Now, what service speed are you going to run here?
We're going to run about 8,000 with this motor.
All right, so let's do that. Now, we're going to do ounce-inch. That's telling us we want to be 0.154 ounce-inch. That's a little confusing at times. So what I want to know is, what's the radius here? What do we have in the
3.5 inches.
All right, so what I'm going to do is I'm just going to import that right there. I'm going to do it here. And it's now going to tell me at that counterweight, I want to have 1.247 grams. So I've taken this number and basically converted it so I have a better understanding what's residual to the crank. Notice that's not 20 grams. That's what it used to be. This is what stock, by the way, General Motors, Ford, Chrysler, all the new engines, they had to lower it because they lighten the block, which, by the way, the block is a damp device. It will take vibrations and pull it down, or sequester, not quite, but just damp. Now, the deal is that because it's so light, they started having deals where they've learned if lean is mean, all right? The electronic control system now have made the unit so that, quite frankly, it's so lean it's getting a little combustion knock, all right? So they have accelerometers on the block, and as soon as they see that, it says I'm lean. So it fattens the motor up, right? Okay. What they found was, in order to have that have validity, this was contaminating that. In other words, that amount, that 20 grams, was generating just enough force to give a false trigger to the accelerometers. Okay?
Okay.
So this is why the OEs now are balancing at race standards. Remember, I think we used to use a generic term of 0.2 ounce-inch for racing, right? What's that one? 0.15. This is grandma's car. This is what's changed, and this is where technology has a benefit with a penalty. So when we balance even stock stuff, and this is why when you get these crank kits and you're buying, and I'm not belittling any of the crank manufacturers, I'm simply saying they generically set a bob weight. And they'll have, say, plus or minus 2% of your bob weight.
Well, if you're an 1800 bob weight, 2% is 36 grams.
Yeah.
Swing. So there's no way that unit's going to be in tolerance for late model engines. Do you agree with that?
Yeah, that's way more than 3% overbalanced on a 1600 gram bob weight.
Exactly.
And that's just reciprocating weight. That's not rotating weight.
See, we're at an era in engine building now. Guessing doesn't work.
No.
If you can't measure, it has no net. In other words, you're screwed. Bottom line. We're now at a level of industry. We have technology and hardware that can give us accurate data. So I'm just going to go ahead and accept that tolerance, and you see it embedded right here, and I'm going to save that. Now, what it did is it saved to the library, so if you watch your arm there, I'm going to go ahead and spin it. Now, what we're doing is we're collecting an awful lot of data, more than any other machine on the market. But we're getting 40 spins on this side collected, 40 spins on this side collected, and then that's done, the algorithm sits there and argues. I want to see what's going on. When it does it, it'll stop, and now it's going to come up and say on the left side, you're 36 grams out, right side, you're 48 grams, and all I'm going to do here is just come around and bring it up to top dead center. Now, in doing so, what's the problem?
It needs weight. It needs Mallory in it.
Okay.
It doesn't have enough counterweight on it.
Exactly. So I'm going to keep this simple. We used to sit there and do a lot of mental gymnastics to figure this out. I'm just going to change this. And you notice the needle flipped, the screen changed, and saying, you're not going to drill here. You're in the add mode. So I'm going to bring you up. Now you can see I got to add weight. All right? Same thing will hold true on the other side. But we're still not there. So we have another little trick here. We're going to go in, and we're going to sit there, and we're going to take the crank and just let it know the counterweight. This is an important factor because not all counterweights are in the same position. Different manufacturers, I'll use this generously, and I'll say sometimes they have a sense of humor, and they guess. I don't like guessing. So rather than assume, I'm just going to mark. I'm going to go to the other side here, mark. And what it's done is it give me a suggestion. And I want to now know what the material is, but first I need to know this is 0.888. I'm going to let it know. And I'm going to say, see that red light? Is it up? Not there. Now again, it's procedurally stepping you through. So I'm just going to go up here and I'm going to increase the diameter. Now you can see it's green, or 7.11 grams. That's what we need to install right here on the side.
And then we'll be approximately 7 grams heavy so
Exactly.
we can massage the counterweight.
That's right. So can you drill that out? Yeah, that might be one way. A lot of times people are a little more artistic. They'll take a grinder. And we don't like holes in cranks, by the way.
Right.
Okay. But yet, you see that big old drill mechanism? That's rather unique to the industry. That bad boy will make things happen. However, I will tell you as a connoisseur of balancing, and you're the guy that needs to talk about this, what happens when we drill holes in counterweights?
Well, it creates windage.
Yeah.
So you're better off if you can turn the counterweights. You're much better off to turn the counterweights, especially in a racing application. We drill holes because it's easy.
But there's a penalty for that.
There's a penalty by the aeration in the oil and the windage in the oil pan.
So how about Grandma's car? What if we just drill her? She's not going to be 8,000.
No, I mean, Grandma.
Unless remember the old drag-on lady, the drag racer? I mean, she might be the exception.
I mean, we drill a lot of counterweights.
Okay.
But they're relatively low RPM motors. And we do turn counterweights and still drill holes, but we try to keep it to a drill point.
Right.
Rather than a long hole.
Well, interesting enough, as you drill that, you now take the benefit of the counterweight, which has multiple purposes, not just for balance. It also adds strength to the crank. It also acts as a damper, believe it or not, because that mass is harder to push, so it dampens some of the torsion out. But the bottom line is you can go over center and create a whole new problem, especially in racing, that all of a sudden the bearing's mad. Right? All of a sudden everything, even all the way up to the valve train's mad. Right? Because that crank doesn't just have unbalance, it's no longer structurally supportive, it's wiggling. Right? So at any rate, on this particular one, let's do it real quick on this guy. Again, I'm going to set it up, align it, let it know.
We'll go to the other side here real quick. And we're going to do this. And I'm going to go back in and size it. And you notice it went red, so it says, okay, give me an opportunity to fix that. Now this one's 12 grams over, 7 grams. But you now have a target register that you'll set up in your machine here. You'll drill and ring, put it back on. It's going to be real close to these numbers, assuming you did what it said, not what you want. The one thing about computers, they don't lie.
No, and if you don't give them the right information, they will tell you the answer, but it won't be the right one. You have to put the right information in.
Exactly. So, in a nutshell, this is technology is a lot similar. You are tenured your industry, or in this industry for a number of years. Is this the way that Grandma used to do it, or Grandpa?
Absolutely not.
So, what does it really save?
What we used to have to do was clamp a metal weight in here and move it around until we got it as good as we could, and then try to replicate that.
Right. Guessing.
And we still got those pieces. And, you know, we still have metal slugs to go in here. Never put Mallory in this direction.
Why not?
It'll fly out.
Oh, okay.
But, I mean, if you want to put a steel plug in here and weld it in, that's fine, but don't put Mallory in that direction.
Now, isn't that because of the disparity of alloys, the density?
Actually, when you weld it in, you're actually not welding to the Mallory. There's two dissimilar metals. What you got to do is you got to build a dam wall there to hold it in, which you would never put it in that way. But if you put a steel slug in there that's compatible with the crank, you can physically weld the two pieces together.
Sure. Welding 101, only weld similar materials, not dissimilar. Right?
I mean, they make stuff for dissimilar, but not to hold it in there.
And also remember the reason we're doing this. Common sense says if it's going through the side, right, it ain't coming out.
Right.
All right. However, what happens when they drill them too big and then they slip them in there and they weld that Mallory into the crank?
You're not welding to the Mallory.
There you go. You're putting a daub of something on there?
I've had to do it, and I turn a taper on the crank and a taper on the Mallory, and I fill the taper up because the weld will stick to the crank. Well, now you've got a limit to keep that Mallory in there. It's not welded to the Mallory. You're building a dam where it can't come out. Now, I have seen people, and I haven't done it, but I have seen people put a piece of Mallory in here. And to weld it in, you're wasting your time. But I've also seen them, when they had to put a piece in here because of lack of counterweight, you go back and drill it and pin it.
To grab it.
To hold it.
Yeah.
But you have to pin all the way through the Mallory and the crank, and you have to be low enough that it don't tear it out.
Right.
Because if that piece comes out of there, we had a piece come out, it'll knock a side out of the block, it'll knock a starter off, and it'll kill somebody if it hits them.
Well, that's a good point because the service speed, let's go ahead and put it up at 10,000 RPM. Let's say we're about this radius right here. Everybody sort of has an idea what a 9mm bolt is. That's bigger than 9mm. You agree?
That's more like a 12-gauge slug.
There you go. And it's going to leave a mark that you're not going to like.
No.
Okay. So safety is always a concern. And by the way, the technician that puts that in, my daughter's a lawyer. In fact, she's a judge now. And she'll tell you, you'll lose that court and case. More importantly, that's one thing to lose money. It's another thing to cause injury. Common sense says, don't do that.
Yeah.
Fair enough?
Do not do that.
All right, so now we've looked at this. We found out a quick remedy, but you sort of jumped ahead because you already had the bob weights on here. Now we have to build the bob weights based on pistons, rods, rings, bearings, clip, pins, whatever the case is. Now you've already done that, and you put this up, and you've already populated this up here for us. And so you've had the advantage of knowing what the bob weight. So, all right, this is all pretty easy stuff, no worries. But the number one thing in building anything is accuracy. You agree? Primary.
Correct.
All right. Second thing of concern is what? Time?
Yes. Time is money.
Yeah, I check on that. It's 24/7. There is no 28/5.
No.
Nothing. I mean, it's just, that's all there is. So when we do this,
you've been doing this long enough. Where are you at with this kind of technology as opposed to what you used to do?
Well, populating the bob weight card is great because, one, it'll tell you if you're wrong.
Right.
Which if you do it with a pen and paper like we used to do it with a calculator, you better check it twice.
Yeah.
And you better check this twice too.
Yeah.
But, you take a whole brand new rotating assembly, you go through this particular machine here, you can weigh all 8 rods, big end and total weight. It'll give you the little end weight, times 8. That's already in there.
Right.
And then you can go weigh every wrist pin and every piston and weigh your rings and your locks. And if you want to, this will sort this so that if you're a couple of grams over with a tolerance in there, if you have a couple of grams either way, you put a tolerance in there, it'll tell you whether you're green or you're red.
I'm going to tighten the tolerance a little bit there. Now you see it fell out.
Right.
Okay.
And sorting it will take your heavy and your light and you match them together. It'll help you straighten this out without doing a bunch of machine work on the rods or a bunch of machine work on the piston. Because you go drilling a hole in a piston, you're structurally changing the strength of that piston. And grinding on the rod, you're going to make, if you grind enough on the bottom end of the rod, anytime you remove weight or remove metal off this rod, it's stress relieving and it's going to make this hole out of round. Yep. When you untorque it and torque it back up, it's not going to be what it was, and you're going to have to go back and re-hone it to make it round.
Well, one of the things, YouTube is sort of an interesting vehicle of knowledge. It's also an interesting vehicle of humor, and it's also dangerous input. All right, notice I'll save that for the last. In the days of old, when we made rods, we had weight pads.
Yes.
These are now called near shape. Now, the manufacturing developments that we had over here do a pretty good job. That's why we're looking here. But you cannot, under any circumstance, modify this and make it stronger.
No.
Can't even be the same.
No, you can't.
It'll be weaker.
It's going to be weaker. You're going to take material off of these ribs, which is the strengthening of the cap, not to mention you're stress relieving that metal, and it's going to make this hole out of round.
Well, so penalty, penalty, penalty.
Yes.
Okay. On the internet, I'm seeing a lot of guys, well-intended people, come out and talk about this, and these are gentlemen that they believe in themselves, and they say, well, we can go out and whisper this a little bit. All right. Or, and this is the worst one, right here. Get on this end. A lot of people, this rod is designed for what? Load in which direction?
It's in, not tension, but.
Right. Anyway. So then every engine goes in compression and then overlap, right?
Yes.
And we're in overlap. What is the piston trying to do?
The piston's trying to pull off the end of the rod.
That's right.
It'll open the pin end up.
So let's do this. Which end do you think's stronger? All right. If I had to do something, you can see as I weaken this, there's more of a chance of separation. Most engine failures, I think we can agree with this, the majority of it is an overlap event where that's where we'll have the piston and rod separate.
Generally, if you lose a bearing or something in the motor, it'll stay together until you lift off the throttle.
Right. There you go. So that's just a little tidbit of industry, but as we go through these things, here's where I'm at. We've done all this in just a few minutes. We've got a complete diagnosis, we have remedy, we have resources to check everything. We are sending out a better product now because of technology. Fair enough?
Absolutely.
Okay, and then you keyed on the last thing. Time. Time is what?
Time is money.
There you go. So investment, we've been very fortunate a trip out here with Keith Dorton, and we're talking to Jason Lyon, talking to you also. Every one of you has a common thread, and that is simply quality, quality, quality. None of you are talking to me about price. In fact, if I try to talk to you about cheaper stuff, red flag, red flag, red flag. Fair enough?
Fair enough.
All right, so if you were to sit there and say, well, here again, what's the name of your company now again?
Custom Performance Engines.
Located?
In Mooresville, North Carolina.
All right. So people in this area, they are looking for people of your caliber to come in and do work. That's a little bit of a promo for you, but you earned it. So if you were to sit there and a guy says, well, I really don't need to balance my engine, but I bought all these things from a reputable builder, what would you tell him?
Tell him that I wasn't going to, if he wanted me to assemble it, I wouldn't do it without balancing it.
Right. And that's because you're guessing, right? You wouldn't know.
Wouldn't know.
Guessing is...
Couldn't sleep at night.
Okay, there you go. All right, well listen, is there any final comment that you can think of about balancing you think is interested in our viewers?
Well, I mean, you can't do without it. I mean, I've checked a lot of production automotive engines. And I had one the other day that was an LS7 Corvette motor that we weighed all the parts and put it up here and the crank was perfect. Well, that's not a real world situation most of the time. But that one was. But that's one in about 100.
Well, you know, you triggered a thought here real quick, and I know we got to finish up, but what about when guys change flywheels?
Well, the flywheel's just like anything else, especially if it's a counterweighted flywheel. Then you're in a whole nother world there. And it's just like when you change a clutch and a pressure plate. That pressure plate, if that hole in that flywheel is not exactly centered and it moves that pressure plate even 10 thousandths off center, that needs to be rebalanced and it needs to be marked to the flywheel where it goes on in the same orientation or it's not balanced.
Well, once again, I think we know this now in discussion, but a lot of people don't understand that simple error. And I think you told me once about a Ford issue or you had a flywheel change.
Oh yes, we had a tow truck one time that we pulled the ARCA car with. And we had a 429 Cleveland motor in it. And we got a 460. Well, the 460 is external balanced. The 429 we had wasn't. And I mistakenly put the flex plate on the 460 and it about shook the mirrors off the truck. And it was only like 30 or 40 grams, but it was a long way out there.
So even a guy of your caliber, knowing what you know, are suspect to, well, you went through a learning curve.
Well, we made a mistake,
yeah,
and it taught us we needed to correct it.
Right away.
Yeah, yes, because it was just, I actually built the motor, and we actually balanced the crank with the correct flywheel, and it just got the wrong one in the truck. So it was easy to fix, but it taught us that we needed to fix it.
Well, so assuming is a bad thing?
Assuming is always a bad thing.
Okay, fair enough. Well, listen, I want to thank you for your time. You've been a great friend and help, and good luck to your business.
Yes, sir. Thank you.
Here at Engine Performance Expo, we're still here, Lake.
We are.
We're still on. We're still up and running. Time for a little on-location hidden horsepower with our guest, Mark Vieau. Mark, welcome. How are you?
Thank you. It's a pleasure to be here. I'm surrounded by history and heroes.
Well, there's a bunch of heroes out there, that's for certain.
Yeah, out there.
You're my hero. You're my hero.
It's been Is that true? Tell us about your relationship with Mr. Speed here.
I can't remember the first time we met. I kind of vividly remember walking into your dad's car shop, really, and engine shop. I was looking for a dyno, and you were there, and your dad was there. I didn't end up buying the dyno, but that was, I think, I knew your dad prior, but that's the first time we actually sat down and really met each other, closely. It was a long time ago.
In mid-90s, something like that, yeah.
Gosh, it was a long time ago, man.
Yeah. It's that NASCAR history, though. So you're originally from Wisconsin, right?
I grew up in Greendale, Wisconsin, which is a suburb of Milwaukee. Yeah. So I grew up at the same dirt racetrack that Alan Kowicki drove in, Milwaukee Mile. I was not part of a racing family, unlike him, but somehow at a very early age, I decided that's what I wanted to do. So.
Yes, somehow. What's the somehow? We always like to know that because it's the inspiration. What was it? Was it a moment? Was it?
All I can tell you is that I remember the moments sitting down in Milwaukee Mile watching A.J. Foyt and Parnelli Jones drive USAC stock cars. That was probably more impressive for me than watching the Indy cars that always came a week later after Indy. So that was it. And I was a drag racer too. So I would go to the drag strip. It was just, let's face it, it was, as a youngster, it was in the middle of the muscle car era, and what kid didn't want a hot rod back then? The racing was just part of it was just an extension.
I'm pretty sure it's in the water up there too.
And the cheese and the brats. Okay.
A combination of all those things, maybe
so.
But I mean, I'll say it. The Milwaukee Mile is one of those iconic, really amazing tracks. Like it's such a cool track because it's got those giant long straightaways, but yet the corners are real sweeping.
It's a tough track.
It is.
Yeah. I watched again AJ Foyt monster that big old car without power steering. So I was just a kid, but it was intriguing. You know, so.
It left an impression on you.
Oh man, tremendously. You know, the noise. I mean, come on.
The sound.
It's all about the noise.
It's hearing you speak about it. I can't help but think about nowadays. Kids watch movies about superheroes, the Avengers, Iron Man. It's digital. It's computers.
Yeah.
Who's got fire? You watched Heroes too. It was AJ Foyt out there in a
real life heroes.
And there's a difference there. Real life heroes, and you followed him. We can't follow. A kid can't follow Iron Man because it's not real. You followed something that was real, and you made your life about it.
It was very impressionable, for certain, because you knew who they were, the icons. They're still icons, and they don't even race anymore. You know? So, yeah, it was an interesting time. How, what brought that passion and that desire to want to race for a living and as a life, as a career? I think it was just a combination of all of that. And I didn't have any personal mentors. You know, my dad wasn't a racer. Nobody in my family really was involved in it. But I knew at a very young age that I wanted to build race engines for a living. And by God, that's what I did. And it didn't happen easy, but it happened. You know, so I tell everybody, not that it makes it won't buy you half a cup of coffee, but if I wrote a book about all of the doors that opened for me, nobody would believe it. I mean, absolutely positively nobody, because it's just the mentors that were part of my life. You know, one day I sat down and I made a list of all the mentors in my career, and it was over 125 people. Now these are mostly men, but men that showed me how to build engines correctly. They showed me how to race correctly, and those are things that you can't buy. You know, I was just lucky. You know, my first real race car was a AA funny car at 18. So I was racing. As it turned out, not my car, because I had a partnership issue, but we ended up traveling the Midwest match racing with the Pabst Blue Ribbon Charger, which was actually the first beer-sponsored car in the history of drag racing. Okay, and
PBR, baby.
PBR, and I was just a pimple-faced kid, but I was, I would be sitting in the trailer, and Don Gollards would come in and start talking, and all these heroes of mine, and it's like it was if I'd have died at 21, my life would have been complete. Okay, that's just the way it was. So, but you can't even plan that. You know, it's just the way it worked out. So we did a lot of traveling too. So did a lot of sleeping on the floor of a crew cab dually.
That was part of racing in the day, right?
Well, I was the rookie, so the rookies had to sleep where no one else wanted to. Usually I didn't get the sleepers. So interesting time. But you fight for that, and you remember it. I remember every little intricate detail that I was taught working on that funny car, because in fact, I don't know if you want to talk about this, but even when I got involved in NASCAR, okay, there were so many stories about tires that weren't torqued during practice, or wheels.
Yeah.
Weight bars that weren't screwed in when the guys would put them in. Hood latches that weren't latched, and the car would go out and they'd lose a hood.
Yep.
And finally I said, I just looked at everybody on the crew. I said, enough is enough. Okay, that's not how we race. So from now on, I'm torquing all the tires before they leave, and I will be the last one to work on the hood forever. And if you guys are changing anything on the car, weight or whatnot, I'm going to be right there to watch you put the bolts in. So that was my job. I was the engine builder. I was a track sport man, but I was more of a overseer when it came to the chassis guy, until they understood just how important, even if you didn't like the driver, okay, there was a driver driving the car, and it was up to you to make sure that he didn't get hurt because of anything you did. And I was taught that at 17. So you don't forget that stuff. It's fun, it's great, but you don't want to be getting hurt.
Yeah,
For
we definitely want to talk about that. Like that's exactly what we want to talk about.
Yeah, we don't have time to probably get through all 120
Forget about
of your list today.
Forget about spark plug wires.
We'll get to it, but the thing is, so we probably do have enough time.
We are going to talk spark plug
to go through, say, like your top 3 or 4 or 5 guys that were those mentors that gave you that moment that was like, wow, that door opened and this whole new career or thing happened because of that chance or whatever you want to call it.
And you said they weren't all guys. I'd be interested to see that too.
There was a bit of a hero. So when I worked for Jim Ruggles in Atlanta, Georgia, and that's when I officially moved from Milwaukee down south, Jim was involved in the Buick Grand National program, and he also was previously involved in the Chrysler Hemi development. So a very smart engine man. A bit of a curmudgeon, but he liked me, and I liked him, and he would communicate with me. And I would say he had a female engine builder. Her name was Tomoka Brady, and Tomoka had a PhD in business, if I remember right. And the first lady I ever met in an engine shop. Period. Working in an engine shop, and she was awesome. I mean, she was meticulous. We'd have competition together. She was great to work with, but she loved what she did. She would write little notes on the bottom of the intake manifolds. She was a fan of Harry Gant, and we won a lot of races with Harry Gant. She'd write, "Good luck, Harry, at the Charlotte race," and this and that. It's kind of goo-goo stuff, right? But the embarrassing part is when he would win the races, or even Rusty or whoever we did motors for, is they display all the parts on the table.
Right.
So
NASCAR tech takes
you'd
everything apart.
You'd see those little love notes on the bottom of the manifold. It was a little embarrassing. Okay. But you'd have to know Tomoka. She's a great lady. I have no idea where she's at now. But so let's fast forward, okay, to all the shops that I managed as head engine builder. If I had to do it all over again, and I mean this with all the love I can muster up, I would look at women to work in the engine shops. And I don't hold that against any man that wants to work in an engine shop, but I'm telling you, they're so meticulous. We have 7 ladies of different ages that work in our shipping department. I have one that works in manufacturing, and I'm telling you, they run the show. They run the show because they care, they're passionate, they know what life's like a little bit.
Detail oriented.
Most of them are stay-at-home moms, so they've been through that a little bit, and it's like it's a great place for me to be. I tell everybody I clean toilets and I sign checks. That's all I do. But
that's amazing.
But that whole that whole business, that was a gift. Okay.
So Ruggles, that was the V6 era.
V6 from Ruggles. I went to Ernie's and worked for Ernie. We helped develop the V6 Ford Busch Grand National engine.
Ernie as in Ernie Elliott.
Yeah.
Yeah.
Ernie
So talk
Elliott.
about that for a second, because that's a big name by itself.
So how did it work? Or?
I hear he knows how to make power.
It's kind of famous.
Yeah.
Elliott guys.
I would drive an hour and a half one way to work for Ernie Elliott. I lived in Loganville, Georgia, and Dawsonville was an hour and a half away. So a lot of times I would sleep at the shop. But he hired me to work on the V6 Ford program and help design it and build engines for Bill initially. And then ultimately we started building motors for his son, for Casey. But that was an experience. Got to work with Ford, Mose Nolan, whom I'm sure you remember.
Yep.
He was like the epitome of the kind of engineer you'd love to work with. And I fell in love with the Ford program. And it was just really nice.
And people may not understand it, but even at that time, the Busch series, right? 'Cause the V6 wasn't in Cup, but that Busch series, that was a struggle. That was a hard-fought competition. You had guys like Keith Simmons and a whole bunch of other people, local guys from all around the country were battling it out. It wasn't just like, it's this minor league baseball, it doesn't matter. I mean, it was still pretty intense competition.
It was Winston Cup with a 6-cylinder. I mean, you had extraordinary drivers, you had extraordinary crew chiefs and teams. A lot of those teams were part-time teams sometimes. There wasn't huge budgets. The engine programs were, NASCAR claimed that we were going to race the V6s in Cup. And I think
that was a long-term idea, obviously.
Yeah, that was the idea. But I think that whole deal was ash-canned after their ears rang a week later after Bristol. Because I would wear earplugs and radios. And I would still go home with my ears ringing for days on end because there was just a frequency that was just almost unbearable. But as far as the engine itself and the development of the engine and its ability to talk to you as a development engineer, it was phenomenal. It was actually one of the most fun, most responding engines I've ever worked with in my career.
Expand on that, how it would talk to you.
Well, back in the day, we didn't have AVL dynos, at least not in NASCAR at the time. So our data acquisition systems were
more
crude,
crude,
crude to say the least. So you had a tool, and you used that tool as much as you could. The thing about the V6, and I say this, is you could make minute changes, and it would define whether or not the change was viable or not. And I think part of it was the reduced amount of friction, obviously, in the engine, so it was able to respond. I did tremendous amount of spark plug work, tremendous amount of header work with the V6s, and if I chose to do that kind of development on the V8s, I didn't get the response that I did with the V6s. Now I know that might sound silly, and I'm not going to go into necessarily the technical reasons behind it, but it was one of those engines that just it was just sweet to work with. And it only had 8 head bolts, So
right.
That's what I love about the Fords, the early Fords, that they had 10 head bolts on each side. It's easy to rebuild. You're not going to lose count, and never had a failure with head gaskets or anything. So, then we had to go and get smarter and start putting 35 bolts on top of the cylinder. Old school stuff. But yeah, it was a tremendous. Again, that's one of those knock on the door, and that literally was a knock on the door. Okay, I talk about the magic of my little insignificant career. When I left Jim Ruggles, it wasn't because of any other reason except that financially he couldn't afford my health insurance anymore. I had 3 children. So I said, okay, I got to do something different. So I took a day off. I drove up to Dawsonville. I knocked on the door. It was locked. There were glass doors. And just as I knocked on the door, Ernie Elliott walks by. He opens the door and says, can I help you? And I explained who I was and why I'm there. And he knew Jim very well, so there was no animosity. I gave him the truth. And he said, follow me. And he pointed to an engine that was literally resting in a pile of oil, okay? And said, that's my V6 right now. And I said, okay, not what I expected, okay? And 30 minutes later, he hired me. And he didn't even know how to spell my last name, okay? But he hired me. And then the first day I went there, the following week or two, he said, oh, by the way, we have to test Daytona in 3 weeks. And it's like, really? And we don't have a motor yet. So needless to say, the barn door was open, and Mark spent a lot of time there, and I spent many a night sleeping there as well. Because you had to. You did what you had to do. I don't want to medal for doing that. I did it because I wanted to do it. But that's what you do. That's what your dad did. Right. That's what you did. That's what all of the racers did and still do. I mean, they do whatever you have to do to get the job done. And it was an experience. You can't go to school and learn this stuff. Okay, you have to do it. And later on, I did go back to college, but I went back to college with all of this stuff, in my brain. So it was very helpful. So, yeah. So from there, Ernie decided that he was going to do something different with Casey, and we had Casey was going to go Busch Granite. Casey being Ernie's son. Mm-hmm. We had 3 brand new Busch cars. He had raced Busch a little bit, and we had 2 chassis. We had 8 engines, and Ernie was done. He didn't want to deal with the Busch stuff anymore. So we took all that stuff and we took it to Lincolnton, North Carolina, and we started a shop with Radius Motorsports and Tim Fedewa. So that was Tim Fedewa's first Busch ride. So I ran the Busch shop all by myself, the engine shop. I went to the racetrack, I did everything, but I had 8 engines. So I had enough engines ahead of time so I could do rebuilds and do whatever development work we had. That was actually the old Skull Bandit shop that Harold Elliott used to run.
Oh, yeah.
So that was history in itself. And that's where I met Harold. So you want to talk about mentors. Harold is no longer with us, but Harold took me under his wing. He showed me the politics of NASCAR, and we got along very well. Now, keep in mind, I'm a Yankee, okay? I'm a bit of an engineer, and I'm in NASCARville, okay? That wasn't a good mix, okay? Now, I married a Southern lady, so that makes me half Southern, and I love the South, so please don't take that anyway. But it was tough politically, you know? I had to keep my mouth shut, and I had to listen. His dad was one of those guys that I did a lot of listening, you know? He taught me a lot of stuff, and he doesn't even know it, you know? So we did that program, and then we ended up doing the Cup program for Jimmy Hensley and for for Ted Musgrave, and ultimately ended up working for Larry Wallace at PowerTech. You know,
and he's an amazing guy.
If you looked at my resume, you'd say this guy can't keep a job. But the problem is in racing back then is, you know, there was only really a few well-financed teams out there, and everybody else's program was based on a 1 or 2 year sponsorship program. So at the end of sometimes 1 year, 2 years, you know, you're finishing the last race whether or not there's going to be money to go racing the next year, and sometimes there wasn't. You know, that doesn't mean the team wasn't viable and they weren't competitive. It just means you didn't have the sponsor money to do it. So.
That's 100% truth. That's basically the story of my dad's career.
Yeah.
Is that you didn't have those big, long-term sponsorship deals. You had a lot of times it was that small company that was aspirational.
Right.
That they bet their marketing budget on NASCAR. That was going to catapult their business, and that could become more. And a lot of times they would have growth, but it wouldn't hit the home run. Like they could hit a double with their sponsorship deal, which was great.
That's right.
But it didn't hit a grand slam that they were hoping for, so then they're gone. So now you're back to zero again.
Oh, yeah.
It was that same cycle.
I mean, it was tough for drivers. It was tough for car owners. You build a team, you know, you have all the equipment, all the cars, all the people, and you have to shut the doors. And then you have auctions. And that wasn't always a pretty sight either, you know. So, I mean, that was just life in the 90s, I guess.
Yeah, it was.
Good or bad, that's just the way it was.
But, you know, Larry Wallace, he's been a guest on Hidden Horsepower.
Oh, Larry's
and he's a fantastic guy. So I would love to hear more about.
Well, he's another one of my mentors. I mean, Larry, you know, Larry raced. He and I raced against each other in Cup, and we spent a lot of time on pit wall talking. And I'll tell you a quick funny story. When I went to work with Larry, you know, we used to look at spark plugs. No, this is even before I worked with him. We would compare spark plugs all the time. That's all we had. We didn't have, NASCAR wouldn't allow us anything, okay? You had to do everything by the seat of your pants, essentially. So we're looking at spark plugs, and one day he tells me he's colorblind. Yeah, I don't think the world knows that, but Larry Wallace is colorblind. So Larry, how can you read a spark plug if you don't see color? Well, I get by. And you have to know Larry that he could get by. Yeah. Larry was an extraordinary engine builder, and his perspective on how to build engines and the technology behind it was simple. You know, his perspective was it was a different way that he approached problems differently than I did, and he approached it from I guess a much simpler way, and it all made more sense. And he taught me a lot of that stuff. You know, I mean, if you go to a situation like that and you come out saying I didn't learn anything, then you didn't do your homework. You know, great man. He had a great team. He ultimately ended up running Penske in program, sold it to, and which is funny because I ultimately ended up running the Jasper program, which eventually became the Penske program. So somewhere I was stuck in there, and it was all good, you know. I love the industry. I'd be building engines now if it was in my DNA today, but I build spark plug wires now for engine builders.
Well, I think that's the great part is that you have that knowledge base. Yeah. So when you talk to a whole litany of people, like you said, you're talking about Joe Creason earlier, right? And Ronnie at Wall to Wall. So we have all these different customers in common we know that are engine guys. Well, I think one of the things that they really appreciate about you is you've been in their shoes.
Oh my gosh.
And so you can speak this exact same language, and it makes it easier for them to deal with you and trust that, hey, I
think, and that's important, if I may, that and that's all I want our customers to know, or our future customers to know, is that when they buy our product, they have to understand that I look at this meager spark plug wire just like they would look at a piston, a crankshaft, or a cylinder head, okay? Because that's what we do, okay? We critique everything that goes on top of that engine or inside that engine, and that's my perspective as well. And listen, the spark plug wire is the last thing to go on an engine, and it's also one of the last things that these engine builders forget to order. Okay, so what's so the recipe of the day is you get a phone call that motor's going on the dyno and I need wires. You take care of them. We still get that to this day. Okay, so our company was really, our company, thanks to Brian Scott, who started the company 38 years ago, he catered to the engine builders. That was his love. And obviously he and I were best friends, and we got along. I helped him as much as I could, and we've carried that on. We could, it doesn't make any difference, but we could become a $20 million company, but as long as I'm involved in the company, we're going to take care of those guys first. Now, I don't mean first, but they're going to be taken care of. Whatever they need, and whatever amount of time they need it, okay, so relatively quick delivery, we're going to do it, okay, and we're going to do it their way, whatever. And we've got, small block Chevrolet under header, we've got almost 400 engine builders that we deal with. And I could say out of those 400 engine builders, about 300 of them have a variation of a small block Chevrolet under header. It might differ 1 inch, but that's the way they want it, so that's the way we build it. So it's just the nature, that's who we are.
Why spark plug wires? Like after this amazing career that you had, how did you end up in that of all the different areas?
If you're interested in who I am, I'll let you know. So after PowerTech, I talked to I decided I was going to start my own business, and I wanted to build cup engines for a living as well. I mean, why not? I was surrounded by it, and I started a company. Spent every penny I had, and I was about a quarter of an inch away from signing a very lucrative Bush program with Michael Waltrip. At the time, sponsor wanted Jack Roush. I realized that I couldn't compete with these guys. I mean, just from a marketing standpoint, I couldn't compete with them. Technically, it wasn't a problem, but marketing was a problem. So I had to close the doors. I sold my house to pay my bills, and Jasper called me a week later and needed a head engine builder. And again, if I told you the story, we wrote in a book, nobody would believe it. And we ran the Jasper program for several years and had a good time, learned a lot. It was our entry into valve train dynamics, so we were one of the first teams to have a Spintron. We were one of the first teams to have a ferro arm in our cup shop. So the Jasper team was a highly sophisticated race team, both in the engine shop and in the chassis shop. We just didn't get all the eggs together, I mean, there's some phenomenal people. But after that, I went to work with Carl Wagner.
That's where I met you.
And Carl was an incredible man, and we got along very well. And I moved to the Stavola Brothers shop. We developed the Wagner South program. We built motors for Cup and Bush, mostly Bush and truck, and worked with Carl for 5 years. And after that, I didn't know what I wanted to do when I grew up. Okay, so I ended up actually getting involved in drag racing. So I ended up building, and I actually started 2 Pro Stock engine shops in town, and probably worked in Pro Stock, NHRA Pro Stock for about 5 years. And
one of those Shane Gray?
One of those was Shane Gray. The other one was Jags. The other was Mike. How could I forget Mike's name? He won a championship. Edwards. Okay. And so,
I've heard of those guys.
Great experience.
Yes, you have.
Great experience.
I've heard of those guys.
Great people. Just,
That's also around that same time when the Pro Stock guys kind of realized, hey, these guys in NASCAR country, they know a few things.
Yeah.
Especially we're turning more RPM, and all of a sudden now where there weren't any Pro Stock shops in Cupland, now all of a sudden there's a whole bunch of them in Cupland.
I think everybody that has followed certainly the Pro Stock programs throughout the years can attest to the fact that it was NASCAR technology that brought the improvements to Pro Stock. Okay, Pro Stock engine building, I have respect for everybody that was involved in it, but it was a little latent compared to some of the technology that we learned in Cup. And all we had to do was change the numbers, okay, and the stuff started reacting. It's something as simple as piston rings, okay, and beyond. But that was all technical stuff, and that's if you have that foundation, you can pretty much go anywhere with it. And I did. I got involved actually after I left the pro stock situation. I actually went to work for a company, alternative fuel engine company, and I was essentially the designer for the company and the CEO, if you will, and that won't buy you half a cup of coffee. But it was a propane-fired engine that we were going to introduce to the market, and we were sponsored by an oil company. And that's when oil, at the time, we were there for 2 years, and all of a sudden, a barrel of oil went down to 3 cents. And needless to say, we lost our sponsor.
Yep.
Okay, imagine that. We lost our sponsor.
Surprise, surprise.
So I went into consulting for a while, and then Scott Performance Wire, who was, again, started by my best friend, Brian Scott. I look at Brian every day, and I thank him. He died about 8 years ago. He owned the company for 30. He's the one that did all the foundation work. He built the brand. I tell everybody he left me an uncut diamond, and all we do every day is polish it. That's all we do. We polish it with people, we polish it with maybe some technology and a little bit of the experience that we have, and we've taken it certainly to a different place. But it's still his company. I still work for him. Brian was a great friend, but he was a curmudgeon. We could never work together, but he was a great man, a great philanthropist. He gave away more money to charities than I can tell you. But I think everybody in the business knew him. He did wires for everybody. Certainly NASCAR. He did about 75% of the product during the day, and he worked every day, all by himself. He's a one-man band. But we have 7, 8 people in shipping. We have 5 to 6 people in manufacturing, and we built the company up to where it can supply to these, everybody. We do private labeling. We're an international company now, but the foundation is the engine builders. Whether they're, it's a 1 set deal or a 100 set deal, it makes no difference. We'll take care of them. That's who we are. We're racers. Sorry.
No.
I have to apologize for that, right?
No, you don't.
No,
not here. Not here. You don't.
I'm just kidding.
Not anywhere.
I'm just kidding.
Racers.
I love the sport. I love the industry. I've been in forever, and it's an industry that if you're not involved in it, you can't explain it to somebody else. Because
that's true.
And we were eating lunch together. It's like 99% of the people that I've known in this industry, whether it's technical sales, whether it's companies, no matter what it was, there were people that you'd take a bullet for, and those people will do the same for you. And there's not an industry quite like that, okay? Because we all kind of do the same thing. I mean, we all do this to win the race, okay? But we all know we're not going to win every race, but we still try to do that.
Right.
And it's phenomenal. I'm going to start crying if I talk about it more, because it is. It's
the people, right? We keep on saying it's the people that make this industry so wonderful, and that's what's
exactly right.
Fantastic about the Engine Performance Expo is it gives us a chance to get people together who are just engine guys, just to focus on engine stuff. So we got tons more engine stuff coming your way, so stay tuned. Listen up, we're actually going to try to help you out here, right? Chris, you do this, right? So you are a shop owner at this point. So I guess I'm talking to you too? No.
I might be a shop owner, Lake, but I don't do this. I've got guys that are more qualified than I am to do this. But yes, at the end of the month, I'm the one writing the check. Yeah,
all
definitely.
Right. So as I've traveled around the country and around the world over many years now, one of the things that I've noticed is that, and I hate debt as much as anybody, right? So I understand the people not wanting to spend money and to buy new equipment. But the reality is the efficiency of this and the struggle to get employees is so great.
Yes, it is.
What I see, what you've done here is pretty much, I would say, a blueprint for what a lot of shops can do. So I know that people struggle with the idea of making the investment to get machines like you have here. So can you speak to everybody that, as a shop owner, and tell them what your thought process is, why you've done what you've done in terms of, I'm going to call it building a modern machine shop. Now, that's really what I feel like you have here, is a real modern machine shop. Yeah, I don't see any manual machines here. Everything is more modern, automated.
Yes.
Where we've done in the past. We've shown the videos where one guy's running 3 machines. You can go, if you want to see that, you can go look at the archives, right?
Right.
But talk about why you did what you did, and maybe some advice to the shop owners and how to maybe overcome that mental hurdle to making that step, because it seems like that's the resistance I get. People say, I see that, but I can't afford that. And I'm thinking, man, you can't afford not to.
Well, and that's exactly, you can't afford not to. And I know on the internet, and I'm going to nip this in the bud, I get a lot of pushback from shops saying, well, that automated equipment, I can do just as well on this manual machine that I've had for 30 years because I've got 30 years experience. And that statement is, to most degree, very true. The problem is that guy with 30 or 40 years experience, he is now gray-haired, he's maybe ready to collect Social Security, and he doesn't exist. Because let's think about it. The last 2 generations, we have told the last 2 generations, don't follow Dad into the foundry.
Right.
Don't follow Dad into the Ford plant. Go get you an education and better yourself, okay? Well, what we've done is we've taught these last 2 generations to go better themselves, and we don't have anybody to work in the foundries.
Right.
We all struggle. There isn't an automotive machine shop out there in the United States or even in the world. I've got customers in Europe. I've got customers in Australia. We
Right.
struggle with this every day, finding qualified people. Well, if you can't find qualified people, the only thing you can find is automated equipment. And machinery like Rottler, like CWT, like Axe, a lot of these companies have taken and they've allowed these machines with technology to become much more self-sufficient, so that you've got a guy that can run this machine, he can run 2 or 3 machines. So it's not the aspect that the machine is better, it's you cannot find somebody with 40 or 50 years experience
To run the machine.
the machine.
Yeah.
Now, back to your point on I can't afford this. If you're going to find that guy, let's say you find that guy, okay, and he wants to work another 5 or 6 years. Well, you're going to end up spending probably somewhere between $50,000 and $70,000 a year, okay? So let's just use 5 years and $50,000, okay? So over the course of 5 years, you just spent $250,000 on that employee,
Right.
okay? You take a machine that's much more automated, like this CNC head porter from Rottler, this 5-axis machine and stuff. You're looking somewhere fully tooled, somewhere between $300,000 and $350,000. If you were paying a guy $50,000 to port heads every year, okay, then after 5 years you spent $250,000, and then maybe he gets sick. Maybe he has a family member. Maybe he decides, new industry rolls in and they're going to give him another $5, $10 an hour, which has happened all over the United States.
I'm saying 50 may fly in East Tennessee, but it won't fly in Arizona. It won't fly in California.
Well, again,
right?
yeah.
That's the thing is when you like you said, the industry coming in. I can see what's already happened. Like say for us in Phoenix, Arizona, when these chip plants come in and they're putting in these new facilities. Now all of a sudden, that hourly rate goes so high.
Yeah.
I mean, you're talking about for a regular machinist to be making close to $100,000 a year.
Right.
So like you said, in a 3 or 4 year period, you could easily spend more than this machine's cost.
Correct.
So
100%.
It really is about that mindset shift. And the other thing I think about too is, in terms of the quality of work, I have no doubt about it. A seasoned professional that is at one with that machine they've used for 30 years can make as quality a part as any of these machines can. But it can't make as many parts as these things can.
Yeah.
And that's because this can run when the lights are out.
Well, and we talk about that quite a bit in our industry and stuff. Lights out. That's when you make your money. A plant during the night shift and stuff, when they've got a skeleton crew, that's when that facility's making its most money. When we leave at 5 o'clock, the boys make sure that there's a casting in this head and they push the button and this thing runs another 5, 6, 7 hours with lights off in the shop. That's making money. There's nobody on the payroll. All I've got is electricity spent on that type deal while this thing's sitting there churning at $90, $100 an hour type deal and making chips and stuff. So you have to look at what that machine, don't look at what it's going to cost you. what is that machine going to make you?
There you go.
That's the key. What is that machine going to make you? And with the automation that we have today in the industry and stuff, if you've got one qualified guy, and hey, when that chip company comes in, and if you've got 2 or 3 pieces of automated equipment, you may be able to bump that guy to $70,000, $80,000 a year because now he's running 3 machines. So let's say his hourly wage, you're paying him $45, $50 an hour, okay? If he's running 3 automated machines like what we've got here, and let's say your shop rate's $150 an hour, you're paying him $50, 3 machines times $150, that's $450. You can afford that guy at $50 an hour because those machines are allowing you to be able to do that. So I think it's a mindset as far as on the business standpoint of stuff. You have to look at it. What is that machine going to make you? What does that automation bring you to the table? And I'm not saying go out and buy a machine like this because if you're not porting cylinder heads, you don't need it, okay? Now, you may need a seat and guide machine and valves. We've got, we're surfacing heads and that type deal. So if you're seeing a trend where you're getting a lot of a certain engine in there, then you may want to look at a more automated machine that you can tool and fixture so that you've got easy setup time on that. And then that way you can make your money on something like that.
Honing, seat and guide, surfacing, those are the things that are pretty automated.
Exactly. You need to look at some of that type stuff and look at a piece of equipment that speeds your process up where you're making your money so that you can make more money. And that seasoned veteran, because I'm 55 years old, okay? I've probably got another 10, 12 years. Most of my customer base is at least 10 years, if not 15 years older than I am. They're retiring. There's been many shops to close up. And again, since we've not told the last 2 generations follow us, they've gone to go do something else type deal. So as the pool shrinks and we become more of a cottage industry type deal, the more automated shops, the work is going to get more intense. So the more automation that you've got in the shop, the better off you are. I think guys in their 30s, 40s, and 50s, I think the next 10, 12 years, I think we're going to have some of the best years that we've ever had as far as making money on this stuff.
We see that because a lot of the shops have closed, because of the guys are just gotten older and things, and they've stepped away, there's fewer shops. But people still want to race. They still want custom things, be it a boat or a car or whatever it is. They want to go fast. They want to have their toys. So the shops that are left are busier than ever before. Like you said, but you can't get the talent that has the experience. That's hard to find. So this is the answer. And like you said, it's an easy return on investment by saying, hey, I plan on being in business for at least 10, 15 more years. So if you are in your 40s or even your 50s, it's pretty easy to say, I can buy this stuff, I can get it paid for, and I can handle more business and make more profit long term by investing in the automated machines and modernizing my shop in order to be able to handle the increased demand, because that demand's there and it's only going to get bigger as more and more shops close. And really, to be honest, I feel like the shops that don't automate are the ones that are going to be left out.
Right. Matt Hussey's here today with us and stuff, going to do some stuff on some diesel stuff. And Matt and I were over coffee, we were talking about this morning. And he feels that the piece of equipment in his shop that's the most profitable is the head surfacer. So you take an S85 or an S86 from Rottler, that's an automated type machine, and you've got a couple dealerships. Reach out to those dealerships. Hey, I can give you quick turnaround time on any surface of cylinder heads and that type deal. Because where before on the older equipment you'd have to dedicate a guy, sit there and watch it, and lack of a better term, babysit it. They'd have to crank the dial down, move the head down, take another pass and stuff, check everything. With the Rottler or more automated type piece of equipment type deal, you set it and forget it. You walk away and that thing's sitting there working while you're doing a valve job. Maybe you're pulling another head off this. Maybe you're doing a balance job or something like that. So we're back to, the mindset has to be, if you got 2 pieces of, if your labor rate's $100 and you're running 1 piece machine, you're making $100.
Right.
If you've got 2 machines running, your labor rate's $100, it's $200.
Right.
Okay.
Listen, this is where the math is important.
This is where it happens as far as that goes. That's where the money's made. So being
and if you can get 3.
if you can get automation and you can get 3 pieces, $300 an hour now. So now you can kind of make fun of your attorney or your or your cardiologist or what dentist or whatever, because now you're making more money than he is, type deal. And again, the labor pool and the way it has shrunk here in the last, and even pre-COVID, I mean, it was already shrinking. People were struggling. A friend of mine, Frank Beck, out in Arizona.
Absolutely, yeah.
Frank's been looking for a qualified person, and I mean, he's offering 6 figures a year to come out there and work. Now,
that's when you said earlier about 50 to 70. I'm thinking, dude, I know guys who've been in this for a long time. They're offering $100,000 a year for people to come work for them, and they can't get people to come work for them.
Well, and it is. We are in an industry that has been driven by passion, the love of cars, and that type deal. We are, compared to other industries as far as where machinists are needed and stuff, we are on the lower scale of pay. So it has to be a passion. It has to be something you enjoy doing and you're passionate about and stuff. But there's still a good opportunity as far as shop owners to make good money, a reasonable living and stuff. And I think automation is going to be part of it. And it's just, hey, you know, we all had, you know, my generation, we grew up with a rotary phone. Some of us even had a party line. I mean, there's kids today have no idea what a party line is, okay? It's just the evolution that we've gone from a rotary phone to a wireless, cordless phone to a cell phone type deal.
To a smartphone.
To a smartphone type deal. And so now we've gone to equipment in our industry with a touch screen. It doesn't have an amber bulb. It doesn't have a load meter and stuff. But hey, even old dogs like us, Lake, we can learn this stuff.
Well, you made a great point right there. I guarantee you got a smartphone. If you got a smartphone, you can run one of these machines.
Yeah.
It's not something you can't do. You can't teach the old dog new tricks. I'm like, I'm sorry, no, almost everyone that has an iPhone or some kind of smartphone, there's some kind of touchscreen thing.
Right.
So I don't want to hear it that you say you can't learn it, because anyone can learn it, right?
Well, and you know, I am not a machinist. I'm not an engine builder. I publicly state that on a daily basis type deal. Do I love this industry? Yes. And am I passionate about this industry? Yes.
Yep.
But the boys have even been able to teach me how to load this thing. And if you can teach me how to load this thing, but I mean literally, so I'm here on the weekends when I'm up here in Tennessee. I'm here late in the evenings and stuff. If this thing's not running, it ain't making any money, and we're not paying the bills.
Right.
So they've showed me in touch screen, boom, boom, boom. I can sit there, torque the head in there, hit the play button, and it goes type deal. So yes, you can learn. Is it intimidating? Yes. But Rottler will tell you, this is CNC porting for dummies, and here's a dummy. And listen, if they can train me, they can train anybody.
All right, there you go. So no more excuses about why you can't automate your shop, right?
Right.
It's going to make you money. It will keep you in business longer and will make your life easier.
Yeah, much more so, yeah. And yes, do you have to maintain the equipment? There might be a little bit more cost? Yes, but return on money from what I've looked at, the standpoint, and when I first started automating in 17, yeah, it's well worth it.
There you go. You heard it from the man. Automate, don't populate.
Another tremendous panel here at the Engine Performance Expo, and we're still going, Lake. We're still going. Of course, Dennis is back. Saw Dennis right at the very beginning of the show. Mark, we just spent a fair amount of time learning about your career. Just so amazing. I realized that I love learning about people and their lives and careers. There's always an amazing story. John Kazi, who I was super excited, a moment that everybody missed yesterday, happened after hours. John over there checking out Project Pontiac. You know, he brought a Pontiac block like that to Engine Masters a couple times. Pretty amazing, of course. And Mr. Keith Dorton back. And we're going to delve into something early in the day. Darren brought us through the very restricted world of building horsepower in a super stock A Hemi situation where you're absolutely restricted by the rules makers. And we're going to talk about that versus engine development where you have no limitations. And I think that's kind of interesting, since, you know, Mr. Kazi said, let's build these giant engines out of nothing, and created something that didn't exist previously. So I'm very interested in that. Let's start there. Like, clean sheet of paper versus within the structure of what's already there.
Well, when we started on the big engines, you know, we've been doing this for 30 years, you know, or more. we were using a lot of passenger car parts, passenger car blocks and stuff like that, and it all evolved to where we kept getting bigger and bigger, and everything would tear up, so they kept building different blocks and different height blocks, finally they put a cubic inch limit on us for the big inch pro stack stuff, which is good, because who knows where it would have ended, but all the stuff today it's pretty much made out of billet parts, and you can make it strong. You can make it the right cubic inch without really pushing it where it's going to tear up, and it's easier. It's a little harder to get some of the parts, but when you're going together with it, what size it's going to be and how it's going to perform. It's a little easier than it used to be.
Well, I think that's it. You look at that and you compare it to what Darren was having to work on.
Yeah.
it's insane what those limitations are. But I think those limitations are where I'm going to look at all four of you and say, you've had that in your career, where you were in that box, where you had this little part and you're like, man, this thing sucks, but it's all I got, so I got to make it work.
Well, I'd rather have the limitations myself, a lot of rules, because I don't know if it saves you any money, but mostly it probably does, because you can't get that far away from where you're supposed to be. But I would prefer a lot of really tight rules myself.
Yeah, because we are our own worst enemies when left to our own devices. And we saw that in NASCAR when we started the qualifying engines, and there was no rules on anything. The flip side of it, technology was going crazy, making things lighter. The fuse only had to be that long. There was a fuse? Yeah. We loved it as engine builders, making horsepower. We did, and I missed those days, but I don't think we had any control, and the cost became so high.
Costs were out of control. But I said you loved it, but we also were saying we loved that in retrospect too. There was a lot of days you did not love that.
That's correct.
When you had a bunch of scattered parts, and I got to get this together, and you got crew chiefs yelling at you, "Where's my engine?" and
that's right.
Everything, and So, would you agree too that the more rules?
I'm a rules guy. I mean, and again, I'm go back in history a little bit. So let's just analyze stock eliminator NHRA racing back in the day. You had to use stock parts, which I'm sure you remember, and you would have guys literally buying boxes of, let's just say, small block Chevrolet rocker arms, and trying to find the best 16. So the best whatever you could get, because you had to run that. So that was rules, and to me, that allowed your imagination, and your engineering mind to go ahead and try to find the best of what you had to work with. This gentleman's been involved in NASCAR actually longer than I have, and I think not having strict rules in NASCAR, and I might get shot when I get out the building here, but I think that was a bit of a demise for NASCAR as well. They allowed the rules to get so far out of whack that it costs so much money. I mean, let's just look at oil pan development in NASCAR. Okay, for the longest time we were running a steel pan with a windage tray and dividers, nothing fancy. All of a sudden we had to have billet oil pans. How much did that cost you guys?
But we still run that.
I know, but look at the development money.
You can't go back.
It took well, I guess not. But look at the development money,
right?
And just the CNC bills, and all they had to do was stick with an oil pan that was easily policeable, if you will, and they could spend the money somewhere else. Now, again, I'm a rules guy, and the only problem that I have is because I'm a rules guy, I followed the rules too close. Okay, so I wasn't a good cheater. Okay, so I'll have to go on the bottom of the list on that. So, but that kind of makes you want to cheat.
Yeah. So what do you think, Keith? You have the widest arc of experience here.
Oh, yeah.
We can't agree to disagree, right?
Yeah.
Okay. I'm just kind of the opposite. Well, for instance, it's probably already been discussed the last 2 days. Flat tappet camshafts.
Mm-hmm.
We still have series that mandate a flat tappet camshaft, and these poor guys, they try to break a camshaft in, and they're going through 3 rebuilds.
Yeah.
Before they get it to
just trying to get a camshaft to break in.
John's right. There should be limitations. They have to be, because it just,
you can't be blank.
But some of the rules. And I've always thought the people that are making the rules are the ones that have less knowledge about what's going on than anybody else. And whether it's political or whatever, I don't know. But I mean, and I've been part of some groups, organizations, associations, whatever, where we tried to help because we were for rules. Smoking unit was part of the group. But and when we went to the sanctioning bodies, here's how we can make racing better, save the car owner who's paying the bills,
right?
Save him some money, and boy, were we blackballed because, well, we know what you're doing. You're just trying to get an advantage for yourself. So we were looked at in the wrong way. So there's got to be limitations, but boy, it'd be nice to have people like us that's in the trenches to know, guys, we tried this and it don't work.
Common sense. That's what.
Exactly.
I think a good engine builder and a good car owner, common sense would help everybody.
Right.
Well, just look at the spec motor programs. So we have a customer that builds spec motors, and of course I get an opportunity to talk with everybody, and I asked him, well, what's your spec motor rebuild? Because I was curious about price and what it costs the racer, and he said, well, which version? And I said, what do you mean, which version? He said, well, we have a stage 1, a 2, a 3, but 4, you have to put your own seals on. I said, really? That's all I need to hear. Yeah. Okay. So what? I don't know. I love rules.
Yeah.
But they have to be enforced, and everybody has to want to follow them.
I know there are a lot of spec motors go across your dyno.
Yeah, we've seen a few with some of the series. They'll bring them in, and basically after the race they might bring the top 2 or 3 finishers and run them across the dyno, and it's a good gauge. And you'll find a lot of things racers do that before they even get to that point to try to they might have an extra 5 quarts of oil in the pan on a wet sump motor.
Interesting.
But you definitely it's a tough deal to police.
Oh yeah. Well, like I said, the racer is going to be the racer.
Yeah.
They're going to try to find their advantage. And if they have a good advantage, like you said, put special oil in the wet sump motor to try to hide that advantage.
So like Keith, I like having rules and guidelines to go by, but it's the ridiculous things that we have to do. Or the guy trying to break in his camshaft. We all remember the days we had to run them right before we come off this roller, and we've lived a lot of nights in the dyno room, and then we may be back in the home before it was done, trying to put that thing back together to go.
So point of emphasis here at the 2024 Engine Performance Expo, it has now come up 2 days in a row. Rules makers, get rid of the flat tappet cams.
I'd say so. That's pretty resounding.
It's not helping anymore. Maybe at one time it was well-intentioned. But what are some of the other things, Dennis? Like, throw some things out on the table that you think are not in line with common sense solutions.
Well, these may not affect
in your universe.
In my universe, and it's changed. The diversity of work have changed for our business model. But even at the upper levels of NASCAR with weight rules on parts, we all run, and you have a piston ring company. We're going to go after, if we can figure out how to make that thing run with a ring that weighs 5 grams for the set, we will. But they could have put weight rules on things, I think, to protect us from ourselves from spending money, and there's other areas in the motor, I think, that hurt us there. But the things they did that helped, like in NASCAR, is they put a gear rule in. Okay, so our engines wouldn't last more than a race in a day. We run them for 4 or 5 races now, and they last.
Because of the gear rule.
So many other things have come along. Right. We've done a lot of other things in the engines to keep the pistons cool and many other things, but keeping the RPM, because we didn't. Right. If we thought we could get away with 8,800, we'd turn 9,000, right? Or the crew chief made that decision. So the engines just didn't last. Where now you're kind of mandated to do that. And I think that other series in the asphalt world do the same thing. There's might be in the super late models, a 7,800 RPM rule. So it's kept them from, keeps the car owning run his engine longer. I know, Keith, when you were doing a lot of them, I'm sure they were spinning them things like crazy, right? and they're not anymore. So maybe that is better.
Well, that brings up an interesting question. You mentioned gear rule and the rev limit. Would you rather see a gear rule that mechanically keeps it from going too high in RPM versus having just a rev chip where the crew chiefs are just going to put the gear to it to basically live on the rev limiter? Because we've seen that before too, and I can't imagine that's actually good. Does anyone like the sound of that thing hitting the rev limiter at the start-finish line?
That's the worst sound we can hear.
But we all know that the short track guys, you go to Pensacola, and that's
all you hear.
That's when the driver gets the cue when he's going to step on the brake or get off. He's down the straightaway on that chip at the flag stand all the way to the corner. It's going nuts. And in NASCAR they have a gear rule. You have 2 gear ratios at each track.
Right.
I don't know if they do that in the short track world, how that would work as far as cost. And I think that the box is a once all. We just put a chip in it, and that's what you got to run. So I don't know.
Most of those are quick changes too. So I guess you have to mandate what your quick change ratios would be.
It would be more to police for the officials, I think.
Yeah.
And that saved money, not only that in engine life, but you can only have 2 gears.
Correct.
So you don't have a wall of options.
Sure.
And this guy's got 10 and I've got 3 and I'm at a disadvantage.
Right.
We see it in Pro Stock with the 10.5 rev limiter. And so, but they didn't stop spending. They just went and spent in another direction. And that's the thing.
No, the
it's
guys who have money are going to spend money, right?
And isn't that ultimately what it is? If you've got money and a goal, you're going to use that money to achieve your goal, whatever it is, however you have to do it. Hiring smart people, or getting back massagers for the crew, you're going to spend it.
Well, I think about this stuff. We're talking about circle track stuff so much. I mean, John, you do a lot of stuff in the marine industry. How does that translate in? Because those things are, to me, insane and crazy. I mean, the number of engines in one boat.
Yeah, there's 2.
Yeah.
But we, right now we do a couple different marine things. One of them is they're really poker run boats, so there's no rules. They just go out and run their buddies and stuff. But there's 2 engines in a boat, and most of them are big Mercury Marine 4-valve turbocharged motors, and they're 130 mile, 160 mile an hour boats. They're 42, 45 feet long, and they're dangerous, and they're fast, and they're expensive.
Yeah.
But we don't have any rules on those. We want to keep them going. That's all. And you can really make as much power as you want with those, as long as you want to put race gas in it. But some of them can't because they're going too far, so we have to calm them down a little bit. But the other thing we work on in the Mercury, we don't work on those big engines anymore for racing, because there's not really a class for them much. The class that runs those big Mercuries right now is those spec deal, and we don't really work on those that come right from Mercury. But we're doing a lot of what they call supercats, which are big Chevys, and there's kind of fun, and there's rules. Like I said, I like a lot of rules. We have rules with those, and they have an RPM limit of 7,000 and a lift rule on the cam and some other stuff, and they're fun. They're fun to work on, and they're almost as fast. They're 135 mile an hour boats. They run fast. Oval. They basically run a Daytona 500 out on the ocean. They run oval.
Mm-hmm.
There's pylons, and they run 4.5 miles usually, and it's cool. It's just like any other kind of racing. It gets your heart rate up watching them.
Wow. I bet. So, old engines versus, we'll call it, these new engines. So you guys have done the R07s and these brand new type purpose-built engines versus the old one. Which one is more satisfaction in it, or is there?
I think they both have their place. What we did a long time ago, what you had to do was, you had to be very innovative, and there was a lot more craftsmanship, because we didn't. It's like John was saying, we didn't have parts back then. You had to work with what you had and try to get the best thing you could, and things are machined so well now, and everything fits.
Yeah, right.
It just fits.
Sometimes. So it's like, don't let me be involved in your engine build, because you got to make parts to fit.
But that was an old clash with the new.
That was.
That's right.
That was taking new stuff and trying to put it in an old engine in it.
Yep.
It did eventually fit after you bolted it into the lathe.
That's right. That's right.
Don't you think, though, that a lot of discussion about the early days? In the early days, there was not a lot of, there were rules, but because less was possible, there didn't have to be quite as many rules. We're seeing on the NHRA drag racing side a little bit of a resurgence in competition eliminator, where it is kind of a wide open field of whatever,
pro stock.
Inline 6 cylinders though with turbochargers. We've got Toyotas. We've got, Frankie Aragona won a championship with an inline 6. There's 2 of them on the planet. It just total, what I think to be total creativity. We're going to cut something in half and use a cylinder. What, as engine builders, like, what about that? It's like clean sheet. This cylinder could work. Let's make 6 of them.
Well, you at this point in my career, you've kind of learned that you're going to start losing money on some of those projects the minute you start on them, because there's so much time and thought that goes into it. You really can't get paid for it. And because nobody's going to spend, hundreds of thousands of dollars usually on one engine, so you have to be kind of careful.
Right.
But a couple times a year I'll fall into that trap and I'll work on one that's, my guys know we're losing money the minute I start on it, but it'll be, whether it's my gasser, those old gassers with the straight axles,
Yes.
Greatest
So
racing.
talk about that.
That's the greatest racing on the planet. I'm telling you, that's the best thing ever.
Why?
Yeah.
Tell us why. Because I've heard that people are in love with these gassers.
Yeah, it is for me, because I grew up about that time when I first started going to drag races. That's when the cars were like that popular, no starting line limiter. No, they're all 3-pedal cars. They're all clutch pedals and clutch 4 speeds and stuff, and they're hard to drive. It's a real man's race car. There's guys that built them that made a couple runs of them and got rid of them. They couldn't drive them because if they were a quarter mile, they'd be low 8-second cars, and that's a handful on a small tire with a straight axle and no aerodynamics, and it's just cool though. I mean, they're just fun, and we've done one guy and we've done really well with them, but it's a lot of work getting the motors up to speed. And
so talk about the motors a little bit. Mark, you're the first one that told me about them.
I was just going to say we should sponsor Sega. We probably will next year, but great series. Love it to death. But there's this one cat out there that had a Model A Ford in the series. And he's run like, he was a missile. And then I found out he had one of his engines in it. And it's like, hold it a second here. It was, I looked at the program as being a bit of a budget program, but I'm sorry, but when you mention your last name, the dollar signs do go up a little bit. And it's like, but these guys are serious. They're serious. They're serious racers.
No, they're
but it's family too. It's great to go in the pits and just watch these guys. They'll share anything.
But they're trying to be like 1960s, and
they do a good job.
They drive them everywhere. There's no parachutes. They drive them back after the run.
Yeah.
They'll run a whole race in the afternoon and a little bit into the night. The whole race, qualifying and everything. So it's cool.
So my understanding is, 'cause I don't know all the rules by any means, that like manifolds and stuff, like you can't run a new manifold. It has to
look old.
It has to look old. Okay.
Yeah, like an old Edelbrock. They call them a bread box.
Yeah.
So you get a little bit of money in those because you have to. Well, you have to get it to look right.
That's right.
On the inside.
You see, there's racers in all of us.
So much for rules.
It's like, I like rules.
But
it's got to look right.
But you're losing money the minute you start on it. But the thing that makes up for it is when you see the guy win, and you see all their family jumping up and down in the start line, everybody hugging everybody. That, even if you're just watching them on a video, it really makes up for all the hard work you put in it.
Their heart's in it.
Yeah.
Very much so.
Yeah. It sounds like they're fun builds because they are kind of event like with Dad's. It's a blend of nostalgia, but you're still putting some new technology in there, and it makes it kind of fun.
Yeah, and the competition's tough. And there's some other guys, Gene Fulton and some of those guys, they built some stuff's bad. It's hard to beat. But there's close competition though. There's no one guy runs up front. You know, they trade wins. You know, different guy wins every weekend, and it's cool.
That's awesome.
I called John a month ago maybe and told him about a project customers wanting to do, a blown alcohol deal for a nostalgic car. And first thing he tells me, he said, you know you're going to lose money on this job.
But he seems less concerned about that than any of us. You know, his heart's in it so much. He just wants to do it.
It's going to happen. So,
there you go.
No, cool. I think that's part of it. You have to have a passion for what you're wanting to do, and it's not always about the money. You got to have the stuff that pays the bills, that's for certain, but there are certain projects it's about, my heart's in this, I want to see it through. And obviously with your project, with the diesel thing going to Bonneville, and that seems like it should be totally tons of fun.
Yeah, we're fortunate. A lot of them are fun, or not all profitable, but most of them are fun. But I was thinking new versus old. I mean, you were talking earlier that it was hard to make back in the old day before the billet and the machinery and equipment. Well, you physically couldn't do it what you do now without that technology. We went beyond the limitations many times, but and found out the breaking point, and then backed up a little bit. Right. But now with the machining capabilities, the technology, the metallurgy of everything that's available to us.
You're right. When we first started running big engines, big mountain motors and stuff, you could really run whatever block you wanted to build. Mm-hmm. Well, today what we use is a big aluminum block that's made out of big, solid, bare, square block of aluminum. Yeah. Well, when we first started that class, the only way you could have made that block was with chisels and hammers.
Yeah. Right.
You couldn't. I mean, you didn't have the technology to get that thing right with computer controlled stuff.
Yeah. I feel like that's the art.
There's no way to make it.
Right. Now we have 3D printing, and you can, like Tony was saying earlier, you just make whatever you want.
Make whatever you want.
Don't you want to build a 1,000 cubic inch mountain motor engine? Musi's got a 959. They put this limitation on it. It's been a while. Everybody's kind of desensitized to 840 cubic inches, John. Like, don't we need a 1,000 cubic inch engine out there? Doesn't that have to happen?
I see a lot of money being spent for no good reason. That's why we're staying where we're at.
The reason is 1,000 cubic inches.
Well, that's fine, but you got 25 cars or something that all of a sudden it'd have to step up. We have to be sensible.
That makes sense. We have to be sensible.
We have customers with streetcars with 1,500, 2,000 horsepower on the street. It's like, really?
Isn't that nuts?
I mean, really?
Yeah.
So there is no limit.
Yeah.
But how far do you want to go? I mean, 1,000 horsepower on the street would be almost impossible to handle.
All the way. That's how far we want to go.
About 600 or 700.
I'm okay with that. That's just enough to get in trouble right there. Yeah. But what is the limit?
Factory cars with 700 horsepower.
First of all, we're racers, we're engine builders, and we're human. Okay, so just mix all that up together, and it's a volatile mix.
How many Hellcats get wrapped around a telephone pole like 3 miles away from the dealership? Yeah. This is great.
Yeah, no doubt about it. Yeah. Well, to kind of begin to wrap it all up, I want to go back to Dennis real quick on Dad's project, because at the end of the day, we're going to show the video of the second engine going back on the dyno. We won't reveal the number yet, where we ended up. We kind of talked about it this morning, but the second engine, which was really quite interesting, because the first engine was the one that was hurt, and there it was laying in the shop, and you guys resurrected it, but we had tons of help, right? We bushed the lifters, we honed it, we new valve train, new springs, everything pretty much new in the valve train and that. But the second one was almost more interesting, because it was one that Cronin had freshened up and just literally been sitting on the shop. They dynoed it, sat in the floor for 20 years.
20 years.
20 years.
Wow.
And we went in there and looked inside with the bore scope, and it was red as that Rottler logo, full of rust in there. And we were like, okay, well, this is going to be interesting. And, got a can of Foggett from Gary and so
That's right.
Turn it over a little bit. And we ran it, and the thing made within like 1 horsepower what the dyno sheet was from 20 years ago.
Did that surprise you?
That totally surprised me.
Total seal rings?
No, they were like old school.
I'm just kidding.
Perfect circle rings, I think, or something like that. I mean, it was a 1.5, 043 top, 1.5 second, 3 millimeter oil, CP, full round pistons,
What does that have to say about surface finish and preparation and everything?
Well, don't go there.
Yeah.
Well, it was a Molly ring, so back to what I said. But the Molly ring that could hold its own oil. And in fact, it was kind of fresh. And really, I think the Foggett, really helped kind of like turning it over, like honed itself back a little bit. It was okay, right? But then all we did was hone it, change the pistons, went to a side relief piston, new rings. That's it. And we just put it back together, and it picked it up, like 40?
Yeah, when I came through the other day, you were looking at the numbers. I didn't see
that was after we put on the carburetor and the fuel, right? So we went, because if a little's good, well, you got to
there was some there too, but...
Oh yeah, there was definitely some from the carburetor and the fuel going from the E85, or the E15, going to, we ran Q16, so oxygenated fuel, a little more aggressive, you could put more timing to it, and of course it picked it up doing that. So that combination was pretty good, but I think, just tell me, just for a second, what was that experience like, being able to kind of take that old stuff and go back to it after not touching it for so many years?
Really, for me, and Keith probably relate to this in our NASCAR world, because when the invention of the chassis dyno, everybody compares each other in our world, is you brought the dyno sheets over.
Right.
Okay? So it's like, okay, well, dynos can be anything, right? Well, actually, no, we ran the motor and we tore it apart or whatever, but I think you brought them over then. When we saw the dyno sheets, that they were so close, and it was like, okay, well, it didn't change a lot. I didn't know what to expect, but as far as the rust in the cylinder, that was just surface.
Yeah.
It's still.
We could tell that when we honed it, right? We took it over to Greg Anderson's and we
honed it. It was a little
it.
dust on the shelf.
Yeah.
That's all.
Yeah, we ran like 8 or 10 strokes through it and just checked it, and it was like, oh, it's all gone.
Yeah, but that was a good running engine for that day. It was.
Yeah.
That was a good engine.
733.
And we did not change the camshaft, right?
We didn't. So the second one, we didn't change the valve train at all. All we did was just hone it, new pistons, rings, that's it.
Flat tapped?
No, roller.
Not a roller.
Ooh, okay. I thought it was an old cut motor.
Well, it was an old Bush 9-to-1 motor originally, and then Bob freshened them up, and his dad bought it at an auction.
Got it. So in the compression, I think we put that back pretty much the same.
Yeah, it was within like a half a point or a couple points.
Yeah.
It was like a 13-to-1 motor, something like that.
Yep.
But she ran pretty good, so it was kind of fun.
Yep.
So anyway, so speaking of camshafts and engines in development, at the Engine Performance Expo, we have an LS engine. So that Engine Performance Expo LS last year made right about almost 1,300 horsepower. This year, Ben Strader and I put a new camshaft in it. So check out what it did with a new cam. So Ben, new year, new camshaft.
Yeah, totally new program to try. So we had a lot of fun last year. And I feel like we've made a bunch of improvements this year.
We've continued to learn. Every time we do this, we learn a little bit more. So if you don't know, we'll give you kind of the backstory. This is the original Engine Performance Expo LS. It started off as a bunch of the parts contributed to do the machining and all the different demonstrations in the very first Engine Performance Expo. Then we got this crazy idea of, hey, why don't we put all those parts together?
Build an actual engine.
Right. We did that. And what will normally happen when you have an engine built from a various sundry of parts, we faced a few challenges.
Yeah, honestly, it wasn't that impressive. We thought it was, it was good, just wasn't great. But that's because the engine really is a system, and you need all of the parts in the system to be pulling the same direction. And while that first iteration of the engine was good, the reason it wasn't great is because we had a bunch of help from a lot of different people. And so we had all these different chefs, and nobody was really in charge of making the soup. So what we ended up with is a bunch of really good parts, none of which truly matched everything else.
Yeah.
And so we kind of had to take a step back that next year and go, okay, how do we work on this and tune and refine the package?
Right. I mean, we were able to meet the goal. So the first
absolutely.
year goal was make 1,000 horsepower on boost.
That's right.
With an engine less than 400 cubic inches, and we were able to do that really pretty
easily. Now, we did get limited back then because we had some fuel pump issues.
Right.
So we kind of went back and we added a second fuel pump and another regulator. We went through a bunch of iterations there, but we got to where it was pretty reliable, right?
Oh, yeah. It could easily run and do that. But the neat part is you got into doing combustion analysis, and that's really was a game changer.
It was, because the first thing that we did before we got to the combustion analysis is we went to the Spintron.
Mm-hmm.
So we took that engine, the first kind of the machine parts, then we had a real engine, then it was like, all right, how do we make it better? And of course, us, we always want to turn more RPM. So we went to the Spintron, made lots of changes there, and that's what kind of got us up there to be able to run the higher RPM and get more power. So when we started playing around with the boost, that we learned right away with that ProCharger supercharger, right? The higher we turn it, the more boost it would make. And so the thing just kept going up and up and up. So it was interesting because the original kind of camshaft that we had, it wasn't like the best fit naturally aspirated. Remember, we changed headers and all kinds of stuff, and there wasn't really anything we could do to fix it. But like magic, we put the ProCharger on there and suddenly, man, it was like, this is awesome. This thing's
boost
great.
fixes everything.
Yeah, kind of learned that through the iterations. But then what happened is we got into like, okay, we got a lot of the low-hanging fruit, and now what we want to do is really try to push the next level. So we went through the process of drilling all the cylinder heads and machining them to accept the Kistler combustion sensors. And last year we ended up running the thing and collecting a bunch of data on the engine, and that really helped us with our tune-up.
Mm-hmm.
So we learned a bunch of things last year about what we thought the engine wanted versus what it really wanted, and we ended up picking up a bunch more power that way.
In the end, the first year we were making a little over 1,000 horsepower.
Yeah, about 1,040, I think, somewhere in that neighborhood.
Last year we're making
1280.
Yeah, 1280 pretty easy. It's like consistently 1280, 1290 all the time.
I think maybe we cracked 1300 just a little bit. And that, again, that was great. But we could see the camshaft events, the four, intake opening, intake closing, exhaust opening, exhaust valve closing. We could see from the combustion data that they weren't ideal. Now, the reason you could see that is because you could actually overlay your cam events into the cylinder pressure data, and you could say, well, look what the cylinder pressure is doing, for example, when I'm closing my intake valve. And one of the things that we saw was the piston would get to bottom dead center, and it would start going up, and our cylinder pressure would start to rise, and then it would start to fall before we got to the intake valve closing. And what that told us is, well, we were holding the valve open so long that it was shoving air back out the hole, the intake valve. What we did is we went back and we called up our buddy Chris Straub and said, hey, we got an idea. Could you grind these few other camshafts? And we came up with some numbers that was not based on my idea or my emotions or my thoughts. It was data driven. So it was like, here's the problem we have. Overall, power level it's making, not too bad. Now I'm talking specifically about the naturally aspirated, but there's this big hole in the torque curve that we just couldn't fix. We advanced, we retarded, we tried different
header links, everything. With the NA, that hole, and it's a giant gaping hole in the torque curve, is just ugly. It's like, if you had to run this engine NA, you would not run it this way.
It just wasn't great.
You would change something.
Yep. So we decided to change the camshaft.
Right.
And lo and behold, using that data-driven approach from the combustion sensors, I could actually put it up here. I don't know if you guys will be able to see it, but I'm going to put it up here just for reference. If I come down here and I look, we went from 466 foot-pounds of torque. Now I'm talking about, let's see here.
The original cam.
We were at about 4,800 RPM or in there. We were 466 foot-pounds of torque before. Put the new cam in. Really, I didn't even touch the tune-up. I just wanted to see what it would do. The thing picked up almost 50 foot-pounds of torque. It's way over 500. I think at that specific spot there, 510, but real close to 50 foot-pounds of torque, and that was awesome. Like it literally felt like such a, high five, we did it, we accomplished our goals. But with so many things in life, there's no free lunch.
Nope, there's not.
We'll go to the chalkboard here in a little bit and I'll show you the specific changes we made, but by moving that camshaft and changing that event, we got exactly what we wanted to fill in that big hole in the torque curve. But one of the nice things that we had before that we were enjoying was it just kind of kept sailing up top no matter how high we went. I mean, it didn't peak till, 7,800 or 8,000 or something, and it was cool. The problem is the average guy's not going to drive his car there. You're going to spend a lot more time between 4,000 and, say, 6,800 than you ever will between, say, 7,000 and 8,000.
Well, a perfect example, the original Cam, if you had a car that had a torque converter on it, you would not be very happy with your engine.
Yeah, yeah.
It made a big number at the top, but you would not be quick down the racetrack because it was giving up so much bottom end torque to be able to move the car. Now,
that's right.
Again, you had a stick car, and you could run up there very high RPM.
Ratios,
you could do it. All right, you can make that work for you. But most people have
given a typical application,
Right.
you would not want a torque curve that looked that way with this big hole that makes a giant peak number. But honestly, that's the mistake that a lot of younger sort of neophyte engine builders make, is I just care about that big number, that peak number on the dyno.
It's hard to be, I mean, it makes you feel good to see the big number.
It does. It just doesn't move your car.
Right.
So with everything there comes a price. To get that 50 foot-pounds of torque, we had to give something away, which means the power above about, let's say, 6,800 or 7,000, it kind of falls off.
Well,
exactly
right around
what you would expect.
7,000. If you roll this thing over here to say right at 7,400, well, it's 20. It's down 20.
20 foot-pounds, which equates to about 30 horsepower.
Right, yeah.
So a lot of people look at that and go, oh, man, that Cam lost 30 horsepower. I'm like, no. It gained 50 foot-pounds. And so what we need to do is look at the average across the run.
That's right, yeah.
And so when we do that, even if you go to 7,500 and you can see that the peak power number is down at 7,500, really anything about 6,800 and below, it's better everywhere, and it's so much better that the total average, even if you were to go all the way to 7,500, is still a net gain.
I think it was around, from like 4,500 to 7,000, the average gain was like 15 foot-pounds.
Right. You would never want to give that away.
No, I'll take that every day.
So many times we have to deal with the emotions of being a dyno operator, engine builder, tuner, or whatever, and when you pull that handle and the thing goes up and you see the number pop up on the screen and your peak number is way down, you go, man, I feel like I missed it, right?
That's why it's important to sit behind your own engine every once in a while.
Yeah.
Right? Because that's the thing. Like me and Dad, with our two-stroke stuff, same thing. We've been on the dyno, and you can see this pipe will make this number.
Yep.
But you look at the torque curve, and you're like, man, it only makes it for a really short range.
That's right.
I can go put that pipe on the car, go to the racetrack, and feel it accelerate.
That's right.
I can put on this other one that doesn't have that big number, but has a broader torque curve, and it feels like you have nitrous.
Yeah. I mean, unless you have a car that has the ability to sit right at that, in this case, let's say 7,500 RPM and stay there, you're not going to recognize any benefit, right? So everywhere else other than that camshaft was down from what we have now. When we saw that, we were like, man, what we had last year was when we changed from the naturally aspirated engine and put the boost on, the boost fixed it, right? You're like, sweet, it went way up top and it carried super high, and it was like, we might have hurt ourselves there.
I would have, when we did the cam change yesterday, I thought for certain
we were in trouble.
Yeah, it's like, okay, it's going to make more torque, but we're not going to make more power.
Yep.
And the damn thing surprised us.
A funny thing happened on the way to the dyno. Every time we do this, I feel like we learn something new. In this case, when the engine was naturally aspirated, because we had made the cam timing a lot shorter, at really high RPM, it hurt the volumetric efficiency.
Yes.
And so then, obviously, I was pretty sure it was going to hurt the volumetric efficiency with high RPM, and even higher RPM with boost. And you know what? It did.
Yes, it did.
But the funny thing about that is when we talk about boost, we should probably define what we mean. Boost is when we measure the pressure in the intake manifold.
Right.
So I have to ask myself, well, how did it get there? Well, it got there because our supercharger's gear-driven, or in this case, belt-driven.
Yep.
So for any given engine speed, the supercharger's turning the same speed.
Positive displacement. Yep.
Yeah, it was putting out the same amount of airflow. So that means if our engine's volumetric efficiency actually went down,
right,
and the supercharger's still putting the same amount of air out, it had to go somewhere. So what happened is it stacked up in the inlet manifold. So really, anytime the intake manifold pressure is higher than the pressure outside, we call that boost. If the pressure in the intake manifold is lower than the pressure outside, we call that vacuum, right? So whether or not we get boost or vacuum is a function of how fast the engine's taking in and processing the air versus how fast the air is coming out of our supercharger. So what happened was when we made the first run, it was like, oh, something went wrong. This thing actually made more boost than it was supposed to. And then we'd had to think about it, and it's like, no, that's exactly what should have happened. If the volumetric efficiency of the engine went down, but the supercharger's putting out the same amount of air, well, then the boost went up. And so what's interesting is that when it all worked out, we actually ended up not losing any torque at the bottom of the supercharged run.
None.
But we gained a significant amount of power up top.
It did.
Now, how is that possible? How do you lose volumetric efficiency and gain power?
Well, I think it's important here to note that because we have the combustion analysis, it will actually show you the volumetric efficiency in each cylinder. So it's easy to take all 8 cylinders, put it together, and know exactly what the VE of the engine is.
That's right.
At any given engine speed.
Yep.
So it became pretty simple math to start working out and say, okay, wait, our boost did this, our VE did that, and yeah, I'll let him do all the math. But it was amazing.
Yeah, it was cool. I mean, I think what we saw just in rough numbers, we saw about a 6% reduction in volumetric efficiency. And it's like, kind of saw that coming.
Yeah.
However, what we saw was somewhere in the neighborhood of about a 9 to 9.5% increase in the boost because of it. So really, the net change, 9.5% minus 6%, was around a 3 to 3.5% change positive in total density. So funny enough, if you take that and multiply it by our old power number, we were within 3 horsepower of what it should have made if you had a 3 or 3.5% change in net density. So it doesn't always work out that way, but in this case, having the volumetric efficiency of the engine go down caused the boost to go up. And when the boost went up, it increased the density of the air. So it turns out in this case that what we gained in density was more than we lost in volume, and mass airflow was the winner, because the definition of mass airflow is volume in CFM times the density of air in pounds per cubic foot. So the engine doesn't care how we got more air mass as long as we got it. Whether you get that from greater VE and the same boost, way greater VE and a little less boost, or way less VE and more boost, the net change was more mass airflow, more fuel consumption, and therefore more power. This literally was just dumb luck. And see that coming when the camshaft helped the bottom end and hurt the top end. I thought for sure it was going to hurt us at higher RPM with the boost, but we dodged a bullet this time and got away with it. Now, as we keep going up in RPM, that's probably going to change in a hurry, because the efficiency is going away on us. We can clearly see that. So when my 6% reduction in VE and my 9% increase in boost, when those two start to trade places, when my VE is falling off faster than I can recoup it with boost, that's when you're going to start running out of power. And you see this all the time in boosted applications, superchargers, turbos, where you go, man, I turned up the boost, but it didn't make any more power. Well, that's because the boost wasn't free, and so you had to do something to get it. So as long as your net change means more mass of air, you're going to expect more power.
And just turning more RPM isn't going to fix it either, because we know that there's a frictional increase as we increase RPM. So
no free lunch.
We hated it. We hated it.
But in the end, we made more power. So it's sort of like it would be easy to high five yourself and go, I'm so great. I'm such a smart engine builder. But the reality is we just fell into that by dumb luck. The reality is we set out to fix the hole in the torque curve, and we did exactly that. The payment for that for the naturally aspirated engine was less VE at high RPM. I'll still take that trade any day of the week. This particular application actually worked out in our favor because it gave us enough extra boost to make up for the loss in VE. You know what? I'll take it.
You know, over a 3-year period, it's not too bad to go from 1,000 horsepower to 2,500.
1,280. 1,000 to 1,280.
Yeah, 1,000.
2,500 would be
1,000
great.
horsepower to 1,280. Yeah, been nice. Not fuel thing, but
and then from 1,280 to make it all the way to 1,330, 35 or 32. Man, I'm not disappointed at all. This has been a great adventure. Can't wait to see what comes next, because we're nowhere near done with this engine.
Oh, just getting started. It still has a wet sump on it.
Yep. So we can still play with more camshaft stuff. We can play with our efficiency of the supercharger. We've got wet sumps versus dry sumps. We've got different oils. There is nowhere near a stopping point for us in terms of what we're going to learn.
Well, you just mentioned something about the different camshafts. So I think now would be a great time to head over to the whiteboard and show how we change those valve events, right? We've been talking about how changing those valve events is what actually changed the VE, which made the gain. So let's actually show you how to look at it and understand what changes we made and how they end up making more boost.
All right, I'll see you over there. All right, guys, so the first thing I want to do is I want to talk about what we actually saw in that we keep talking about this combustion data. So what does that mean? How did we look at it, and what did we actually see? So I'm going to draw a little graph for you here real quick that should kind of represent what the four-stroke cycle actually looks like if we're talking about combustion data, right? So I'm gonna come up here and I'm gonna make a little kind of like a plot. And so we're gonna call this side top dead center, and we're going to call this side bottom dead center, all right? So what you're typically going to see throughout the pistons travel from TDC to BDC is it's changing volume and it's changing pressure up here. So we're going to call this a PV chart, pressure and volume. So this is volume, there's our pressure. So think about what you would normally expect as the piston moves from top dead center towards bottom dead center on your intake stroke, right? So I'd start over here near TDC, and my line's gonna kind of go down like this, somewhere around bottom dead center. Now at that point, the piston's gonna reverse, so my pressure's gonna start coming back up, and now I'm gonna be on my compression stroke. So depending on how high or low your compression ratio is, will determine how steep this slope is gonna be. So we're gonna go ahead and go up, and we're gonna compress, and when we get to the top here, we're going to have our combustion where we have the ignition vent, and now our pressures and temperatures are expanding. Now, of course, the piston begins to go back down. And so we get the expansion stroke here, back to bottom dead center. And then we have the exhaust where we're pumping it back out. And so what we get is a couple of what we call pressure loops. Up here we would call this one the work loop, and down here we would call this our pumping loop that we work out things like mean effective pressure. This one is like if we took all the average area in here, that's our mean effective pressure that's actually pushing down on the piston doing work. So we'll call this our work loop. And over here we have a loss as the piston's coming up, pumping all that dirty old exhaust out of the engine, and then pumping clean air back into the engine. So we'll call this our pump loop, right? So realistically, this one's taking away and this one's giving to me. So the net mean effective pressure is the difference between all this area and all this area. So in a perfect world, I want this one to be as big as possible and as high as possible in pressure. And I want this one to be as small as possible and as low as possible in pressure. So when we start looking at the data, what we like to do is we like to take a line and plot it in here, let's say, for example, on our chart, and we're going to call this intake valve closing, right? So what we look for is the theoretical slope that we should have along this line that's based on the laws of thermodynamics, and we look at the difference between that theoretical line and the line we actually got. So oftentimes what will happen is this pressure will start coming up, and we are going to intersect the line that we made for when our intake valve closes. If this line was still going up, we might have closed the intake valve too early. If this line comes up and then starts going back down, that's because the piston is now pushing air back out that open intake valve, and so that means we closed the valve too late. So in this case, we were seeing a lot of that too late closing happening in the event. So we went to our cam card and we're like, let's see what we have here and let's make a change to it. So when I think about my cam card, a lot of people want to talk about lobe separation angles, intake center line, exhaust center line, and that's great, but the engine doesn't really respond to those things. Those things are really the consequence of what you choose for the 4 camshaft events. That would be intake valve opening, intake valve closing, exhaust valve opening, and exhaust valve closing. So looking at our chart, if this is intake valve closing, then from there on I do my compression, I have my ignition, I do my expansion. Somewhere over here I would have exhaust valve opening. I'd come back and I would pump it out. Somewhere before top dead center, I'm going to have intake valve open. And then somewhere after top dead center, I'm going to have exhaust valve closing. And so we look at what the pressures are doing at each of these spots. Now I like to plot out the piston's displacement, or where the piston is in the cycle, against my cam card events, because it helps me visualize it. Now in fairness, the way that I'm going to plot this out here is a little different than a lot of the camshaft guys will. Billy Godbold, my buddy, he plots it 360 degrees off so that you're going to see 0 on his plot would typically be where the overlap happens. On ours, the way that we've always been taught since 8th grade in auto shop is the 4 engine strokes are intake, compression, power, exhaust. So I like to start that way. Let me draw it up here, show you what I mean. So if I start over here, I'll call this 0. I'm going to draw a line that comes over here, and that's 720 degrees. So that's one complete engine cycle. So now what I'm going to do is I'm going to draw the piston's travel. So I'm going to go in the middle here. This would be 360 degrees, or what we'd say is TDC compression, right? So starting at 0, my piston travels down to the bottom on the intake stroke. So that would be 180 degrees. It then travels back up to the top here on the compression stroke. So now I'm at 360, okay? Piston goes back down to the bottom on the power stroke. So I'm at 540. And of course, then on the exhaust stroke, the piston travels back up to the top to get me to 720. Okay, so now when I look at the original camshaft that we had in the engine and I look at the events, what I had was, let's see here, I got some notes. So my intake valve opened 17 degrees before top dead center. So that means I'm going to be over here, IVO, 17 degrees before top dead center. All right, so that gets me on the exhaust stroke now. The exhaust valve is still open, but we'll get to that. So I'm going to go from there. I'm at top dead center. That starts my cycle over. The entire 180 degrees to bottom dead center, and then it closed at 61 degrees after bottom dead center. Okay, so when my piston went to bottom dead center and it started going back up, I waited 61 degrees, and we're talking about the at 50 numbers here, not the advertised numbers, but I waited 61 degrees after bottom dead center to close the valve. And we could see from the combustion data that that was considerably late relative to the pressures in the cylinder. What we wanted to do is we wanted to move our camshaft so that it would close that valve about 10 degrees earlier. So where does that need to be then? Well, if we were going to back that up, we would want to close the valve at 51 degrees after bottom dead center. Generally speaking, at lower engine speeds, the earlier you close that intake valve, the more trapping you're going to have of that mixture that came into the intake cycle. So that number primarily is what gave us that extra 50 foot-pounds that we found in the torque curve there. So I have 17 and 61 plus 180, right? So that ends up being 78 total degrees plus my 180, which gives me a camshaft duration of 258 degrees. I'll put it up here. We have 17 before plus 180 to get me to the bottom plus 61 degrees after bottom dead center. So 8, 14, 15, carry the 1, I get 258 degrees. We look at the exhaust side, we could do the same thing. So on the exhaust side, I was 67 and 23. So what that means is, on the exhaust side, I opened the exhaust valve 67 degrees before bottom dead center. Now that happens up here. I did compression, I got ignition, now I have my power stroke coming to bottom dead center. So 67 degrees before bottom dead center, 67 degrees before bottom dead center was when I opened my exhaust valve. Again, we're going to go from there to bottom dead center. Then we're going to go all the way back up to top dead center. And then 23 degrees after top dead center, A, T, D, C, is when we closed the exhaust valve. So our overlap period, when we talk about overlap, is my intake valve opened 17 degrees before I got to top dead center. My exhaust valve didn't close until 27 degrees after top dead center. So if you add those together, that would be 40 degrees of what we call overlap. On our second camshaft, we wanted to shorten that up too, because we could see our cylinder pressures here before and after top dead center were not ideal. They were too high when we were opening the intake valves. Because we were opening the intake valve here 17 degrees before top dead center, there was still considerable amount of exhaust pressure left in the cylinder. And what that's going to do is you start opening your intake valve, and guess what happens? It shoves it right back into the port. You get reversion that way. And so we wanted to go ahead and move that back up there and kind of save some of that time. We were at 9 degrees. We moved from 17 up to 9 degrees before top dead center. And then on the exhaust closing there, we moved that one also to 9 degrees after top dead center. You can see that what happened is we went from 40 degrees of overlap to only 18 degrees of overlap. That's a pretty significant change. And again, that worked really well for our lower RPM torque curve. But when the engine was naturally aspirated, it kind of cost us a little bit higher RPM. We really thought it was going to kill us when we did the supercharged edition of the engine, but in this case, it did in fact hurt the volumetric efficiency, but because we couldn't get that new boost to go in the engine, or however you want to look at it, it increased the density of the charge that was going into the cylinder, and our net change was actually better. So looking at our new camshaft, so our old one was 258 degrees on the intake, and then on the exhaust we had 67 before, plus 180, plus 23 after, right? So if I go 67 plus 180 plus 23, what you get is, let's see, that's 8, 10, and 7, carry the 1. There you go. 270 degrees and 258. So you can work out your center line angles if you want on the old camshaft, but from memory, I think that one worked out to about a 112 LSA. And that means that halfway between my intake opening and my intake closing, I would reach max lift at about 112 degrees after top dead center. Halfway between my exhaust opening at 67 and my closing at 23, I would be about 112 degrees before top dead center. So you add those together, divide by 2, you get an LSA of 112. When we went to the new camshaft though, we moved our closing here 51 after bottom dead center. We closed that intake valve 10 degrees earlier, and we opened it 8 degrees later, so we waited longer before we opened it. So we ended up with a much shorter intake camshaft. On the second camshaft, we opened 9 degrees before, closed 51 after, 180 in the middle. So what you end up with is a 240 degree camshaft versus our 258, okay? Halfway between 9 and 51, we would have been an intake center line of about 111 degrees. Looking at our exhaust side, we went over here, and what we did is we kept the exhaust opening event exactly the same. We left it at 67, but on the new cam, instead of closing 23 degrees after, we closed at 9 degrees after. So then what we have is 67 plus 9 plus our 180, and we get, let's see, what is that? 9 and 7 is 16, I believe. 8 and 6 is 14, and 2 carry the 1, we get 256. Halfway between those would be roughly 119 degrees, 115 on our intake. Add those to, 111 on our intake. So you add those together, divide it by 2 to get the average. My LSA would have been 115 degrees. Okay, so a little lesson on plotting out your camshafts for you. Whether you do it my way or the other way where you move everything 360, you're still gonna get the same numbers. I like to do it this way because in my brain it works well for piston travel, and then I can relate it to my PV chart. I hope that was helpful for you. I hope you can see how we took that data and determined what to do with the camshaft rather than go, I don't know, let's just try something different. This way produced results based on the data rather than the emotion. So take that for what you will, and we'll talk to you about it when we see you in person.
For a new year, and it looks like it worked, and so appropriate that now Billy rejoins us in the studio. Lake, you made a little more power.
Oh yeah, it's amazing how much change there can be with that camshaft. And you know, we were just chatting about it. It was pretty neat to see, because I mean, when we ran that engine NA in the video, you can see it. We probably edited out the part where we were like, man, we have hurt ourselves badly. It's like, this thing is so down on VE, because with the combustion analysis, you can see all of that. And we're like, this thing's gonna be a turd. I mean, and then we made that first run under boost, and we see that boost level, and it just keeps going and going and going, and that number just separates, and you're like, Eddie the Eagle. It's, you know, it's like, wow, where did that come from?
Yeah, and you, like when Ben goes through that system we does, it shows all the events, where it goes, each loop, and it goes that. We do that in our cam school too, and we'll talk about that in a second. But yeah, you can see with one, we go from 40 degrees of overlap to 18 degrees of overlap. You know, when we're working with turbo guys on camshaft specs, the first question is, hey, how much boost to back pressure you have? You know, we ask them about what's the pressure on this side of the engine and what's the pressure on that side. What are you pulling from and what are you pushing into? You know, and so when you think about it like that, when you get one of these big superchargers, you know, you're putting this pressure 20, 40, 60 pounds into the motor.
Yep.
You're pushing in nothing. So when you keep both valves open for 40 degrees, when you've got all this pressure in the intake manifold, no pressure in the exhaust, Elvis has left the building. You know, it goes right in there, right out. That's why it wasn't making, quote, boost, is you were moving all of this air mass. This big compressor out here, this supercharger is your primary driver of airflow. it's pushing all this air into there. And when you open it, it just goes straight through without ever going through, never burning the combustion chamber.
Yeah, it was pretty neat. I know Ben mentioned it in the video that, last year, I think we had the Hero run where it made 1327, but every other run we made was like 1280, 1290.
Right.
We just had the one superhero run. But this time, once we made that camshaft change, once we kept Elvis in the building, they were all 1300 plus.
Right, and then the on the other side, plus at higher RPM, you moved the exhaust valve opening too. So now it wasn't all choked at high RPM. When you're making this power, you think about, okay, making more boost. Well, the exhaust port didn't get better. It's the same exhaust port the whole time.
Right.
And it's pushing the same, more and more massive airs in the chamber.
Yep.
And it's got to go through that same exhaust port. So giving it more time, let it not choke itself at high RPM. So really, the great thing is that the Plex system, that all research Ben did, it let them go in there and see, the motor wants to tell you what it wants.
Yes, it does.
If you have the right equipment, you can listen to it.
Absolutely. So speaking of the CAM school, so you and Ben are doing a valve train school together,
yes,
right?
we do a class together. It's called the Advanced Valve Train, AVD, Advanced Valve Train Development class. And we did one. We had a full class of 12 people. Did that back in August, and everybody just loved it. Really looking forward. We've got another class coming up in April. There's a few more holes left.
Is that EFI101.com is where you would go to sign up for some of the sets?
Yeah, look, if you look at the schedule, it's not on the main page. So if you go on the EFI University webpage, just go on the schedule. You see AVD. It's in April sometime. So we're looking forward to having another event out there. It won't be nearly as hot in April as it was in August.
Absolutely.
But this is a really neat opportunity because there's a lot of places where you can do classroom and there's places you can do lab. But what we'll do is we go in there and put it all together.
Right.
So we build a valve train system virtually. Talk about what's the real acceleration profiles, what's everything going on, how to build this system virtually, and then test it virtually, and then test it in the Spintron, and show how what's really going on in the computer. Things like that people get their minds around. When we talk about how we're building this system, it's not, we're putting in the number of coils on a valve spring and the diameter when we model a valve spring. We're not saying how much load it has.
Right.
And there's things about that are primary and secondary. And building a model helps these guys see, okay, what's really matters about this system. And so, how we're working from valve motion, not from a camshaft.
Right.
You're working from valve motion on design back to the cam motion. And then what's that cam motion go back through the valve and then the deflection, everything like that. So it's just a really interesting paradigm change. We also spend a lot more time, we spend so little time talking about load separation and duration. Everything we're talking about is about valve events. And so it goes very much, and the way Ben and I do it is I'll do a session or two, and then he'll do a session, and then I'll do a session. So if you speak fluent geek, we had people there from, professional race team engineers and hobbyists, and they all enjoyed it. And it's because we're just sort of laying things out there. We'll say it one way, then say the other, and we sort of like interpret for each other.
Absolutely. And that's what Ben's great at. I mean, Ben's a fantastic teacher, which is why, if you're interested in this stuff, you should really go to EFI101.com, look up, find the AVD, the Advanced Valve Train Development class, and while you're at it, if you haven't done it already, you should sign up for the honing class, the honing school class, because Ben's a great teacher. If you're interested in this stuff, it's a great way to really get deeply involved, up your game, if you will. That class, the honing class, they're both fantastic. You know what? I bet that those old guys who were putting into this Engine Builder Hall of Fame wished they could have learned that way. They had those kind of tools because they had to do it the hard way.
Oh, absolutely. Can you imagine if you could look inside? It's like Ed Iskandarian. I'm the biggest fan of Ed Iskandarian because I've sat down and talked to him about how engines work. And it's a pinball wizard because we've got lasers, we've got prox probes, we've got cylinder pressure, we've got all this stuff going on to tell us what's going on, and how well he was able to picture it in his mind without all that data acquisition. And that's what these guys were able to do. They were able to see what the engine sees.
Right. So you're going to see right now the next 4 inductees into the inaugural class of the Engine Builder Hall of Fame.
Edward A. Winfield. I heard that there was somebody in San Francisco that was doing custom camshafts for the people. I was involved in setting up the Half Moon Bay drag strip. But Ed Winfield was a recluse. He had a shop in San Francisco in an alley, and you could not go in his office. He would open the door, you could hand him the cam, tell him what you were wanted. He said, come back in 2 weeks. And he had a certain number of items he needed to know from you. He wanted to know the RPM. He wanted to know how much lift you could use with your valve spring. And so I started making a form and handing him this form with a camshaft. I would come up with my own list. Here's the engine, the bore stroke, the rod, static compression ratio, and what we're doing with the carburetor and the exhaust system. And then he told us, well, the Zenith carburetors don't seem to flow enough air for this wild of a cam. So he also helped me bore out, told me how to modify a Zenith carburetor, boring the carburetor out, putting in larger throttle plates, actually having no venturi, and having a proper velocity stack on it. And one of the first things I had to learn about was the diameter of the lifter. He always wanted to know what the lifter size was. Well, I found out that was how much velocity you could have on the shape of the cam lobe. And then at that time, I just said, how the heck do you check that out? So I started putting bluing on a lifter and running it on a camshaft, finding out what the white was, so I called it lifter print. I finally got to get some of this information from Ed, and after a while, Ed and I became good friends, especially when I started doing Porsche cams. 4-cylinder Porsche cams, had an engine dynamometer in the shop, and the job was to build a good 4-cylinder Porsche engine to beat the Huffaker MGBs, and we were successful. No, he worked for Harry Miller as a kid. He went to YMCA trade school as a young man. He didn't go to college or anything like that, but he liked geometry and mathematics. When I heard that he liked mathematics and geometry, I was asking him, well, what can I learn, what can I learn? And he told me, find these books because these people did it and you can learn from them. I'm not going to tell you how to do it, you have to read it. And then when you ask me a question and you've read it, then I'll explain it to you. But if you ask me a question and I see that you haven't gotten a background on it, it's a waste of time. So I would go there at lunchtime, and sometimes I wouldn't get back to work till 5 o'clock that day, because he actually let me in the office and let me talk and ask questions. And when I'm in his office, George Vignotti would call him, and also Granatelli. When Granatelli had the Novi engine on the dyno, Granatelli was always calling him on the phone, as did Don Garlitz. I'm there and Garlitz calls him on the phone. So I got to listen in, which was kind of fun. Winfield was selling carburetors to the truck industry because the brake-specific fuel flow was flat. The trucks got better fuel economy. And with good fuel economy, that saves a lot of money for the truckers. Carter and Stromberg Carlson, I believe, were suing him. Patent infringements, and any simple thing they could sue him for, he would have to go back and fight with them and prove that they were wrong. And after a while, he could not afford to go back because he was his own lawyer. And he said, this is baloney. So he just had to get out of the truck selling stuff to Detroit just for the racing people. I would run a Triumph engine on the dynamometer and take off the stock Triumph carburetor and put the Winfield carburetor on it. And within 2 minutes, it tuned out perfectly. There were a lot of little things you can do to the carburetor depending on the altitude, the application, and then having the accelerator pump style carburetor, which didn't have any linkage. I thought that was quite interesting, where the diaphragm would open with pressure differential and let more fuel in. And you could regulate that with a different spring on it too. So he was a genius. He was actually a genius. He helped me with making cams for the 356 Porsches and the Chevy V8s for drag racing. So anyway, he would not tell me anything about making a camshaft till he said, if you buy a camshaft grinder, I'll talk to you about making camshafts and trying to design a camshaft. So I found a used, broken down Storm Vulcan cam grinder at Automotive Engineering, since they bought a couple of new ones. And I had to get the table rescraped, put new bearings in it, found out things didn't line up where the damn on the thing. And I finally got it running, and then I said, well, now what do I do, Ed? He says, well, I'll grind you some sample lobes and see if you can copy them properly. So he would send me, I'd send him a cam, he'd grind some lobes on it, I'd put it in my machine, duplicate it, check it out, tell him what I found. Then I learned how to properly copy a cam, which most people don't know how to properly copy a cam either. And then I started making a list of lobes that were Winfield lobes. I made some pretty good camshafts, whether they were for Porsche or for Chevys or Chryslers. When I would give him a problem that I was trying to solve, he would take his long slide rule out and he'd give me some answers on his slide rule. And I remember using a slide rule when I was going to school. I said, wow, that's pretty cool. So I had friends at Hewlett-Packard, and the HP 35 calculator came out. And I bought an HP 35 calculator. My wife was very upset because I spent all this money as a gift for somebody that she didn't know. And I sent it to Ed, and then he sent me a postcard. This is a beauty. This is a beauty. Thank you. Ed Winfield taught me about ramps, clearance ramps, how important clearance ramps were. Been able to get into his office and sit there for 4 hours to pick up a camshaft for $35 or $70, whatever it was at that time in the 60s, was just like going to school. You know, that's when I found out that the first valve float problem was the valve hitting the valve seat and coming back up and letting the pressure out of the cylinder. Second with valve float is when it lofted over the nose of the cam. And I ground so many cams that had a mark on the back side of the lobe, I knew it was lofting and hitting the lobe. The lifter was hitting the lobe on the other side. If you revved the engine up too high and it didn't have not enough seat pressure, the valve would bounce back off the valve seat. So seating velocities are really, really important. And on the opening side, if you hit the valve too hard, the valve spring would surge. If big is good, bigger must be better. That's the attitude everybody has. And that's not true. It's not true at all. Beating everybody with his 2 up and 2 down Model T. And he was always going too fast on the streets. There are street cars and stuff like that. He was #1, just like in scrambles. If you're first in your class in motorcycles, you're #1 on your motorcycle. So he was #1. And he was in movies, in the old car movies, racing around track or on the street. And he was one that could actually turn the steering wheel like this with one hand and doing all kinds of fancy stuff for the film industry too. So he was quite the character when he was young. He was quite the character when he was older too. Having a mentor like that was, if it wasn't for Ed Winfield, I wouldn't be here.
Well, Vic Sr. was, he was a hands-on guy, and the one thing he did do is he hired the right people. He hired Bobby Meeks, he hired Don Toll, he hired Fran Hernandez, he hired Bob Bradford. These are all key people at Edelbrock. And Vic and I were very good friends. I think he took a liking to me in my early age and helped me wherever he could. Every once in a while, a barrel of nitro would show up on my doorstep that he would buy and have it delivered to me. And his first business, as I remember, was on Highland Avenue in Los Angeles. And there was a gas station in front, and he had his in the back. And he ran a midget, and he would never build anything and sell it until he tested it and knew that it was good. So he raced a midget with a V860, and he was one of the first guys to run nitro. I think Fran Hernandez met the guy that supplied him nitro, and they run some midget races and smoked the offies off. Only V860 to really do that. He was one of the few guys with a V860 that beat the offies. I think you can count the others on one finger. He made good equipment, and he had good people working for him. You know, because you're only as good as your weakest link. So, and he didn't have any weak links. Bobby Meeks went to work for him, sweeping floors and cleaning parts and that kind of thing. And went in the Navy, spent a few years in the Navy, came out of the Navy, went back to work for Edelbrock, and he worked for Edelbrock until the day he died. And Fran Hernandez, Fran worked for him a long time, and then Fran ended up going to work for Mercury. He moved back to Detroit, and he handled Mercury Racing Division. In fact, Fran had something to do with the design on this engine, the camera. And then Don Toll was a machinist, and Don Toll went to work for him early years and worked there until he died. But Bobby Meeks worked there the longest. Everything he touched was a winner, or he wouldn't touch it. Manifold, cylinder heads, and in fact, he had a lot of the moonshiners, the guys peddling booze. Edelbrock built them engines. Now, a lot of them, I don't know which ones, but a lot of them had Edelbrock flatheads in their 40 Ford Coupe or their 36 Coupe. When they opened up the company on Jefferson Boulevard, it was a machine shop, a dyno, a balancing department, and an engine department. But come here, I'll show you something. There's Bobby Meeks and Fran Hernandez on the Edelbrock's dyno, and that dyno is right in the middle of the machine shop. And Fran is the one with the apron on, and Bobby's the other one. After Vic Sr. had died, and I'm pretty sure, and Junior was running the place, they were going to put a new Heenan Pro dyno in, and they took the Clayton out, and they lent me the Clayton because I didn't have a dyno at the time, and I got the Clayton dyno until I was able to get a Heenan. So Edelbrock and I go back a long ways, yeah.
Holman Moody, when I went to work there, and prior to that, was that was the go-to place if you raced Fords. Quite a big operation at the time. I mean, it was the place, well, by the standards of that time. You know, if you look back at where the facility was, it was an old barracks at the airport is where their shops were, and it was scattered at different places. Quite an operation for that time period. A lot of talented people there. They started in the 50s, from my understanding. Of course, when I went there, I guess I went there in late 63. So they were established. And, you know, it was not a glamorous place by any means, because I say it was, their shops were in different barracks and warehouses that the airport had used. But I remember some of the photographs and some of the things that some of the guys had been there for quite a while told me back in the Y block days. You know, they were with the superchargers and so forth. They were very instrumental in getting that program going for Ford. As far as Holman and Moody, they were entirely opposites. John was a businessman, and probably as smart a businessman as certainly, well, I've only ever worked for one other businessman, or for one other businessman, and that was John. And so he was the business part of it. Ralph was the racer, the people part. People didn't necessarily like to deal with John. He was strictly by the book, very strict. I remember when I got the job there, and scared to death, went in for the interview with him, and he took everybody in their office, in his office, and done an interview. You know, what do you expect out of this, and so forth and so on. And you know, very intimidating, very firm, but I certainly respect that. Did then and still do. Now, Ralph was the guy that would walk through the shop, and at break time he'd sit down and have a break with the guys, or, you know, just not so much outside the shop. I didn't see him that much, but he was a car guy, you know, and didn't want anything to do with running the business from my understanding. But they made a great team. One that comes to mind that people would know now is Waddell Wilson. And Waddell actually came to work there just about the time that I was leaving. The others are quite a few of influential people at that time that people today is not going to remember. But I remember there was the guy that that was the general manager, a guy named Howard DeHart, that he was John Holman's right-hand man that ran the place. And the foreman of the engine shop, his name was Lee Terry. He came from Virginia, and he was overseeing everything that happened in the engine shop. Quite a guy that was very influential on me and was quite a benefit for the company at that time. Was a guy named Willie Thompson. And a lot of people now know his son, Kenny Thompson, that is a renowned builder of cars. Really one-off cars, non-standard, something nobody else has done. And his dad was the same way, and his dad is the one that taught me balancing. I remember he had had a head injury in a modified at the old Charlotte dirt track where the fairgrounds used to be. And but it didn't affect his ability to teach, and just maybe explained it in a little different manner. But and another one was a guy named Luigi Lazowski that was a real craftsman. He came from Indy cars. So the team, the Holman and Moody team, had the resources to hire these people that were as good as you could get at that time. As far as, and they were a warehouse also for Ford. If you wanted a Ford part, you got it through Holman and Moody. Now, there was two parts of Holman and Moody that a lot of people didn't know it then, and most people don't know it now, but John, he had a passion for boats in the marine industry. So there was a Holman and Moody division in Long Beach, California. And it wasn't as much tied in with Ford as the NASCAR thing was. But gosh, it was a big part of their business. I think he done very well financially off of that also. Because there was a semi that went back and forth from Charlotte to Long Beach every week. We did special projects like the 24 Hours of Le Mans, Monte Carlo road race. And in fact, that was one of the first jobs that I had when I actually went there. I didn't get to go directly into the engine shop. They put me in the race shop. The Holman Moody was, it was a full service, full racing service facility. They built the chassis, they built the cars, the bodies, you know, it was a turnkey deal. Now, a lot of the teams that they supplied engines for had their own deal also, but quite a few of them got the cars, you know, the whole deal from there. But the Monte Carlo Road Rally, I was there when they first went there, and when Ford came out with the 289, and we first thing we did was they wanted a little more power and durability for the chase cars. And they used, of all things, an Econoline pickup truck for chase vehicles. And you know, I don't know how they did it, but I remember one of my first jobs was 289 high performance engines with the 4-speed top loader transmission from that era. And you know, the way that Econoline is, you know, you're sitting beside the front of the engine. So one of my first jobs was, you know, here, you know, the engine transmission mounted in the car, we need the shift linkage on the column to shift this 4-speed transmission. That's how I got to know some of the fabricators, because the guy from IndyCar racing, he's the one that kind of took me under a wing and helped me do that, because I'd still be working on it if it wasn't for that. But no, they did. And then the 24 Hours of Le Mans, when they won that, you know, that was quite a deal. But that was all done in-house there. They used common sense to build the race cars more so than, of course, we didn't have computers and so forth. So they had engineers. But the engineers were almost secondary to the technicians, the people that actually done the work. They had a lot more control over how things were built, it seemed like, than they do now. In other words, now it seems like it's separated. You got your engineers over here and you got your technicians over here, and they're butting heads all the time. It seemed like they worked together so much more, because I think having the caliber of people that had to build those cars, and gosh, we went out and kicked butt, you know, so it worked. The engines at that time made 510 horsepower. And I mean, we kind of softened up the compression, dropped RPMs a little bit, and they were, if I remember correctly, in the 430 to 450 range. And at that time, all those big block Fords, single carburetor, made 510 horsepower. They all did, you know, and they were redlined at 7,000 RPMs, you know, for quite a few years. So but basically the same engine, just detuned. Same cubic inches, just the biggest thing was compression ratio, a little milder camshaft and so forth. The engines for the NASCAR side of it, and even for the Marine and even the Le Mans, our procedure was at that time, you didn't get a block and heads and whatever from Ford. You got a complete engine. There was a warehouse over there, I remember, that they had, the engine was coming in, there were 427 cubic inch FEs with 2 4-barrel carburetors. That's the way they came from Ford, completely assembled. They'd been fired on the run-in stand, and that's it. No dyno or nothing, just fired. And there was a warehouse full of those things in 64, 65. They were stacked in this warehouse, you know, on big pallet racks that were, you know, 5 layers tall. And but the procedure was, we would do usually about 20 engines per week, and serviced all the teams. And there's a lot of Ford teams, you know. And we'd get those engines complete. Well, on usually Thursday evening, Friday morning, sometimes even into Saturday, depending on how the week went, it'd bring all those 20 engines over from the warehouse to the engine shop. So those engines would be disassembled. You would all the heads would go to the head shop. All the crankshafts would go to the balancing shop. Parts would be clean. So they were basically blueprinted. And my job at that time, when I did get to evolve into the engine shop, was doing all the balancing. And then as I got the balancing done, I would help on cylinder heads and then help on assembly some and dyno. But by usually, and we worked quite often 7 days a week at that time, which was great for me because I was a young guy, and I was, I needed the money, and you get time and a half over 40 hours. So it worked good, and it did for most guys. But our normal day was Monday through Friday. Monday through Thursday would be 8 to 5, 30 minutes for lunch, an hour for supper, come back at 6 and work till 10. That was 4 days a week. Friday you'd work from 8 to 5. Saturday, 8 to 4 to 5. Sunday was a little more lenient. You didn't have to work. You didn't have to come in at 8 o'clock. But like I say, the place was run very strict. At that time, Mr. Holman's office was where you came in. You had to walk by the window in his office to hit the time clock. You didn't want to be at 8:01. You wanted to be there 7:58, 7:59, and you go straight to work. But anyway, getting back to the engines, usually by Monday morning, I had 20 crankshafts. And the way that we did them that time, they were pretty close. You didn't have to use heavy metal and do a lot of, whatever that we do now. They would come to the balancing department with the flywheel and harmonic balancer bolted onto them, standing on end. And we'd take all the rods out of all 20 engines. They were all just put on a workbench, and we balanced them, or I did. I'd balance them by not removing any metal, just by putting them in sets of 8. And sometimes you'd have some overlap, and you'd have some left over from the previous week to swap around. And they were all magnafluxed. The cranks were magnafluxed. Used the same pistons, put new rings in them, new bearings. And by, like say, Monday morning, I had all those 20 crankshafts lined up to balance. And it was pretty quick. So by that afternoon, I'd have all balanced. They would have, in the meantime, they were decking blocks, honing blocks. Wasn't no line honing or anything done at that time. And the cylinder head guys were doing the valve job, decking the cylinder heads and so forth. This was not a big shop either. Everybody kind of worked back to back, So, but by Tuesday, we were assembling engines. And by Thursday, those 20 engines had been assembled and off the dyno, and they were picking them up. It sounds really crazy to think about it now. Yeah, it was every week, because they raced a lot of races back then. Of course, stuff broke back then not like it, it's unlike now. I mean, pieces broke because they weren't meant to run as hard as they did. So, but that's the way the engine shop worked, and it was a well-run procedure. Of course, drivers and crew chiefs would always whine about, he's got more power than I got. I mean, that still goes on today, you know, it'll go on as long as we race. But they weren't, you know, engines have their own quirks, but as far as power, these things, 510.
Well, Holman Moody back in the early 60s, you know, they was Ford backed fully, and they built the cars and the engines for all the Ford drivers and for sale to the public and whoever. And we built a lot of engines. They also had the parts department at Holman Moody. Also made all the wheels for NASCAR. So, you know, there was a lot going on in that place. I remember in '65 we built, there was 4 or 5 of us in the engine room, we built 500 and some engines, blueprinted. Well, when I went to work there was only 30 some people, including the secretaries. You know, how we turned that out. But a normal day was 8 in the morning to 10 at night. And then on the weekend we was off to the racetrack, you know. I remember in '63, you know, they put me in the engine room, and for the 10 years I was there, I stayed in the engine room the whole time. I wanted to get out because that was standing on your feet, you know, from 8 in the morning to 10 at night. It was tough. And, but I could never get out of the engine room. But, you know, on the weekends then we was off to the racetrack because in '63 they put me on Fireball pit crew, and then in '64 Lorenzo and Moody come along and want me to be the jackman on their car. But that's all about getting the engines that I built. But they come to me and want me to be the jackman. I'm thinking, I've never been a jackman, but I was very athletic in high school. I can do it. So there were several guys in the shop wanted to be that too. They wanted a shot at it. So then we had tryouts. And the first time they said I didn't do it right, I cheated. So then Ralph said, well, do it again. Well, I had a little feel for it then. I'd never done it before. So I was a lot quicker the next time, and the guys, they all just went out the door. So anyway, I was the jackman. And then it went to, I was out for the year and then went to change the front tire. And then through the rest of my career, I was a front tire changer. Well, you know, they didn't really get along that well, but anyway, they made it work, and they were very successful. And, you know, building the cars, building the engine, and not only that, running race cars. Normally we run 2 to 3 out of the shop. You know, start with Fireball and Renzo, and you know, David Pearson, Bobby Allison. There's a lot of drivers that went through Holman Moody, and real good drivers. Mayo Andretti, AJ Floyd, they drove out of there at times. You know, I had a little room where I built the engine for the company car. I was always on the company car. I was always wanting to make more horsepower than the last one. So that was an ongoing battle. You make horsepower, and at the same time, you got to make sure it was durable for 500 miles.
Those that might be interested in more detail about Holman and Moody and what they did and the history of them, my good friend Tom Cotter wrote a book quite a few years ago, probably 15 years ago now, that's very detailed, a lot of photographs and a lot of history in it. It's really a good read.
My first introduction with Bob Glidden, and it's really hard to put a definite time on it, but Bob had worked with Cam Dynamics and Comp Cams early on, and somewhere I met him during that time before I was even involved in Comp Cams. I was still at Racing Head Service. And Bob came to me and we were talking about cylinder heads. You know, and anybody that knows Bob very well knows he was a little persnickety about his cylinder heads. And this is when he was running his Cleveland, and we did some pretty extensive modifications, had to cut some heads apart and weld them together and do all other stuff. And from a business standpoint, it was an awful idea to try and do that. But from a personal standpoint, it really did a lot for Bob and I to understand and know each other, have confidence in each other, and kind of, we both understood that we were shooting for something that we didn't know what was there, but if you don't shoot, you're not ever going to hit. So Bob was the kind of guy that always wanted the impossible, and we were able to think about it and try and come up with an idea and go for it. He was not a frills guy. Had a manual dyno where he had to have the whole family around with clipboards writing down what the torque meter did and this and that. But he was, let's give it a try guy. I remember we had to make him some rocker arms one time because something happened and all of a sudden he went faster on a particular pass or quicker, and he noticed he had a broken exhaust rocker arm. And he was smart enough to think, what is that doing? And it's doing this. And so we had to make him some rocker arms that flexed. He didn't understand what it was doing, but he wanted to thin those out and make it flex a little bit. And this is way before spintrons or spin fixtures. This is all here. And we made that, and I argued with him and said, that's a dumb idea, but we did it. And he liked the fact that I would help him do the dumb ideas. Well, once we got something to measure what was going on, we realized really what it was doing is changing the timing events of the cam, and we started doing it the other way. But, Bob was not a guy that followed the normal path. I mean, hell, he raced a Ford and nobody else did. So he took the path that he believed in and was usually able to prove that he could figure out how to do it. Bob outworked everybody. And it was funny here, and talk about Warren and Bob for just a second. Bob was pretty to the point. And Bob looked at me one day early on and he said, I don't ever want to see you or hear of you even speaking a word to Warren Johnson. He was so afraid that I might say something that Bob was doing to Warren, and they didn't like each other. I mean, honestly, did not like each other. Wouldn't speak. Vicious competitors. So Warren did his one way, Bob did his the other way. Clearly, they were both very successful. Bob worked himself and his family to pieces. And I'm not saying Warren didn't either, but it was probably only a year or two ago at the Engine Expo that I sat down with Warren and formally introduced myself. After 50 years in this industry, I said, I'm embarrassed that we've never officially been introduced. And he laughed and said, you're right. So it was just funny that people chose their partners, if you will, and you didn't dance with the other partner. That was something. But Bob would usually work hard enough. If he had an idea, he would work hard enough to figure out how to make it work. And technology was coming along at the same time, and their crazy ideas would get tried and sometimes proven, sometimes disproven, but their crazy ideas would bring some technology in. And I'll give you a good example. Bob called one day, and if you'll picture a cam lobe, Bob called one day and said, I want you to take on this exhaust lobe and just cut the back half of it off. Just put it in a bandsaw and cut it off. I said, Bob, you can't do that. The lifter's going to go and it's just going to fly out somewhere. And he said, that's what I want you to do. I said, it won't work. Yes, it will. I said, it won't work. He said, I've already done it. Well, Bob did it and ran it, but before he ran it, he went on his lathe and put a cam in there with this crazy lobe and put a lifter block in the tool post on the lathe and a lifter in it with a valve spring and all. And he spun it on the lathe. He said, it's noisy as hell, it raised as hell, but it will run. And then he had done it his goofy way with a grinder and a bandsaw and put it in an engine. And what we learned later was it was just changing the opening, the closing point of the exhaust valve. And we knew why, because we knew how to build cylinder pressure and so forth, but we didn't really understand how to measure it. We didn't have spintrons, we didn't have optrons, we didn't have any of that. Bob used his ear and just listened to it on that crazy tool post thing on the lathe. And that was the first part of how we tested valve motion. Now, Warren may have been doing it a completely different way. I learned later that the guys at Chrysler were doing it with some technology on the NASCAR side. But none of this, everybody sort of worked in silos and none of it got together. And I think this competition, as you were saying, this rivalry, sort of forced a little of that technology to come together, and that floated all the boats higher. Early on, when I very first knew Bob, we were at Englishtown racing, and Bob had 2 dogs, Dobermans. And Bob's boys were little bitty guys. And after the race, everybody was sitting around, and Bob, I'm pretty sure his whole life, and Bill and Etta have never drank a beer. Now, Rusty's probably drank enough for all of them, but we're sitting around after the race drinking a Coke or something, and one of the rental cops came around and said something to Bob, and the dog bit the cop right in the butt. And they had to chase him around the whole racetrack to get him back. I don't know what that cop did, but they had to stay an extra 2 days because they quarantined the dog before they let him out. But that was just a little aside thing that probably nobody ever knew about. But early on, and some of the people that will see this may know Dean Harvey. He was a kid that I had from high school, and I sort of grew him. And Bob and I were having a feud, and we would scream and holler at each other like brothers. I mean, really, Bob could get kind of rough around the edges sometimes. And we were in the middle of one of those arguments about something. I don't even know what it was. It didn't matter. They were all the same. You know, they'd flare up and go down. But we were at Indy, and it had been wearing on me and wearing on me. And I said, Dean, we're going up there in the trailer. We're going to get this over with. He said, man, I don't want to go with you. Please don't take me in there. I said, come on. We went in there and we shouted and hollered and MF'd each other and all, I'm sure the trailer was rocking. Finally, Etta poked her head in and said, Bob, we got to go make a run. He left. I left. So a couple hours later, I said, Dean, I can't let it stop like that. He was on top, and I'm not going to leave this conversation until we win. And Dean was begging me not to go back in there. Back in there we went. And we ended up settling things, and we're all buddies. And you know, something that kind of made me feel good is, a couple of things. We were up there for a PRI years ago and went to visit, and I forget who was with me. Somebody from Edelbrock was with us. May have been Rick Roberts or somebody at the time. And we're in the shop, and Bob comes over to me and hugs me and tells them all that we're as close to best friends as anybody could ever be. And I thought, you know, that makes me feel pretty good. And it just shocked the rest of them. They said, holy mackerel, you know, we can't believe he'd be best friends with anybody. But when Bob got sick, right before he passed away, again, Dean and I, at the PRI show, we left, said, we're going to see Bob. Knew he was real sick. Called, and Bill said, it's not a good day, don't come. I said, too bad, we're coming. So we went, sat around the kitchen table, and it's another little story. Bob loved to cook, and he loved to cook and entertain. And we had sat around that same kitchen table and eaten dinner several times. And man, could Bob cook well. He was a good cook. And he came out, and we sat at that table for probably an hour until he got so tired he couldn't hold his head up. And he told me something that I'll never forget. He said, you know, we lived in a magic time. He said the generation that we grew up in was so cool because you didn't have to have anything but the desire to go make it happen. He said, we just could do anything we wanted to do as long as we had our mind set on it. And that probably epitomizes Bob as much as anything. We used to race at a little racetrack, drag strip in Nashville. It was Union Hill drag strip. A little short, it's still there today. It's called Music City International or something. Little short 8th mile up on the top of a mountain. You'd go through the end, you'd fall for a week and not hit anything. And we'd go up there and I'd see, here he'd come. And you knew when Bob came to race, you're not going to win. He had a ramp truck with a trailer, 2 cars, and then they run 2 complete rounds of stock or super stock, whatever it was. Everybody runs, the winner sits out, everybody comes back and runs for another round. Well, Bob would drive one car, Etta would drive the other. They'd get first and second place in round 1. Come back, Bob would drive the car in round 2, and they'd win round 2 every single week. And I think about that, you know, that's where Bob set his vision and his goal and his mind on, that's what I want to do. And he figured out how to make it happen, and it was pretty cool. Pretty cool to watch that from beginning, because at the time, Bob was a line mechanic at a Ford dealership. I was a line mechanic at a Chevrolet dealership. So we kind of started about the same place, and we just sort of grew because we were convinced we could make it happen. That's what Bob was. Bob was an incredible person. He had the most unbelievable drive inside of him that made him what he was. And he surrounded himself with people that could help him. And you weren't just okay with Bob. You were if he either trusted you or he didn't. And it was pretty cool to be on the good side of that. I really loved the man. He was unbelievable for our industry, teaching us how to be better, teaching us that we didn't need a lot of the things that people thought we needed. We just had to go figure out how to do it. And it changed, it helped change, mold our whole entire industry.
When I was a young kid, I used to get on my bicycle and I would ride over to the library to see if they had the results from the U.S. Nationals. And then, you know, Pomona, any of the big things, because you'd send in these pictures and they were on this roll and you stuck it in there, a slide roll, and it had somebody voiced over and it had the sounds of the cars and had somebody talking about what happened at this last big NHRA event. And I remember as a kid riding my bike over there to find out about it. You know, fast forward, 16 years later, and I'm given a number to call. And I get on the phone and I can't believe myself. I am talking to Bob Glidden. You know, to get an idea about the passion Bob Glidden has. You know, this is a guy who was competing at such a level that when he wrecked his car and it's on fire, knocks the front of it off, he jumps out, takes off his fire suit, and covers the intake manifold so that nobody can see what he's doing on the intake side. Bob was such a competitor that nobody wanted to try to make money in pro stock, wanted to try to compete against him because it was just too hard. You know, Bob would, when the Hemis came around, everybody else just threw a Hemi on it. They went, hey, the Ford Hemi doesn't work so good compared to the Dodge Hemi. What's Bob do? He gets in there and plays with the valve angles and like tries every couple of degrees intake and exhaust valve angle to try to get the valve angle just right to make the most power. And it was very opposite of what people would think, because when the valves were laid over more, you got better flow, but the combustion chamber wasn't as good, and it didn't get as good of combustion efficiency. It didn't make as much power, especially at high RPM. So Bob's over here with this Ford Hemi standing up the valves, making it work until NHRA made it illegal. Bob with his Fairmont. This is a car that actually the only car that I know of in NHRA professional categories that went undefeated. You know, it went through about half of a season and never lost a round. Every round it won. Bob was able to tinker with anything. He didn't care. I mean, whether it was on the car, whether it was on the motor, he would dig and dig and dig and try to get every last bit of performance. One of the earliest things I saw was Bob Glidden was actually balancing the camshafts. You know, we had old camshafts where he'd go in there and balance it. Bob Glidden built probably what was one of the first Spintrons for use in pro stock. But Bob's Spintron wasn't a Spintron. He just took a lathe and took a lift, put a camshaft on it and used the tool compost, bored out, put a lifter bore on it, put the spring on the side of it, and started to watch how well the lifter followed the profile with a rev kit on it. And then worked on how could he carve on it. And so he would literally go over to a grinding bench and start grinding on a camshaft until the lifter wouldn't follow the profile. You know, this is the type of thing, I don't know if any of this made him faster, but the fact that he'd do all of this made him faster. He would try anything. There wasn't anything that he wasn't going to try. You know, some people go, oh, it's hard to shorten the deck. Bob just did it. Oh, it's hard to rotate the valves. Bob just did it. Oh, it's hard to make a different intake. Bob just did it. Everything that needed to happen to him. And that's why, you know, when he retired, he left NHRA as the winningest driver in pro stock. Why? Because he just worked that hard. And you see it, you know, the other day I called up Billy and I'm like, you know, his son Billy Glenn, Billy, when was the first time you went to the drag strip? And Billy's like, I don't know. He goes, I think it's 7 or 8 days. I'm like, what? Yeah, Mom was, you know, Dad was out doing something and we had to go to the track. So I think I got over, I don't think I was, according to her, I think I was like 7 or 8 days before I went to my first drag race. This was the first family of drag race. His wife was out there, his kids were out there. They were absolutely 100% put in the most work they could do. I mean, I jokingly say that Bob Glidden's the reason that Jack Roush went to NASCAR. That there's just got to be an easier way to win races and make money than to race against Bob Glidden.
The inaugural class of the Engine Builder Hall of Fame. And Bob Glidden was a great cook also? Who knew? My goodness. Like, incredible videos, incredible interviews. Watching Scooter talk about, you know, when Bob rolled in, you knew you weren't going to win. Just those moments, just amazing. Simply amazing.
Well, it is. I mean, I think I feel like Bob and John, and really each of them bring about that ethos of there are people that just left an indelible mark on the industry. And Billy, you said it earlier, yeah, you summed it up the best.
Yeah, I mean, when you win a race, they give you a trophy. So, you know, that's the reward for winning a race. And, you know, any great engine builder is going to win races. The greatest of them, they leave their impression. They make a change throughout the industry. The industry is transformed because they were there. You know, and that's what we really want to see with these guys. And I know people out there have, okay, well, what about this guy? What about this guy? What about this guy? You know, one of the things, if you're researching this for us, and, you know, I was talking to Keith Dorton. He goes, well, you know, I said, Keith, we're having breakfast. I said, I don't feel like I'm, like, worthy to do this. Right. But nobody else was doing it, so it's like, okay.
We just stepped up and did it.
We're just going to do it.
Right.
And, you know, when you're thinking about people for Engine Builder Hall of Fame, think about, you know, not what races they won. That's great. You know, who did they inspire? How is the industry different today because they were there?
Right.
You know, what things wouldn't have happened, you know, how did they change the way the game was played?
Right.
And, you know, one thing we can say is that each of the 8 people that we put in this industry, that our industry is forever fundamentally changed because they left a mark.
Absolutely. I mean, think about Holman Moody's, for example, because you've been probably noticing this book is on the table, and that's actually Keith Dorton's book that we showed in one of the videos that kind of culminates and captures the history and the legacy of Holman and Moody. And what's amazing about it is that, like you said, that impression, that legacy, not only did they win Daytona 500s and NASCAR championships and the 24-hour Le Mans, right? Ford versus Ferrari, that's their engines.
Right.
They did that. But that is where Keith Dorton, Waddell Wilson, and Robert Yates came from. That place generated this tribe of people that have gone out and influenced others and others and others. That legacy is huge, huge. And the one I want to talk about just real quick is Ed Winfield.
Yes.
That's a name that not a lot of people probably know, but I'm like, there's not an Iskey without Winfield.
No, that Miller did so much, and he was such a great guy. But somehow this Miller thing goes to Ed Winfield, and then it just explodes everywhere.
Yes.
You know, and PRI, and you can just basically trace, if you go through PRI, you can go and find out where each of these engine companies kind of trace their way back, probably toward Winfield.
Right. I mean, Winfield and Vic Edelbrock are like the founding fathers, if you will,
of the performance industry.
Yes. Yeah, those are the guys who started making performance parts that enabled everything that we know to be our industry comes from those guys, which is why they're there.
Yeah, and they really are amazing. And you think about like Winfield Camshafts. Yes, that was the camshaft. There was nothing without there's no Harvey, there's no anything, you know, Crowler, you know, Iskandarian, Dima Elgin, me.
The family tree goes to there.
It goes to Ed Winfield. But, I mean, he was so well known for intake manifolds and for carburetors. You know, like you weren't going, there was years that you were not going to win the Indy 500 if Ed Winfield wasn't doing your carburetors.
Right. We could spend 5 more minutes right now just telling the story that John Calley's related about how the carburetor for the turbinator, that GM wet flowed that carburetor that Winfield did, and the calibration engineer said it's the most perfect air fuel curve they've ever seen. Like they took it out of the box, put it on, and it was perfect.
Could have put it on a Briggs. You could have put it on a 5 horsepower, 500 horsepower, 5,000 horsepower. It was going to meter fuel correctly.
Right at the end, there was a moment where Scooter was talking about Bob, and they sat down at a table. And I think this is, like, we don't talk about it enough, but Scooter brought it up, and I want to drive it home, that Bob said, we are living in the most amazing era. And when he said that, I thought, of human history. The idea that era, which I personally believe extends till right now. I know some people get pessimistic about things that happen in the world, but if you want to do it, you can pretty much do it. Find something, a way, a machine, a person to help you, capital. It's out there. The limiting factor is your imagination and your drive. And to see Bob at the cutting edge of that, just worked perpetually to accomplish his goals, which he did. When else has that happened? Like, you go back hundreds of years, people were trapped on their farm. They had to grow their food. They couldn't worry about, like, hey, I want to do this thing that I want to do. It didn't exist. And it exists now in, our post-World War II era, where technology is kind of a thing and education was kind of a thing, and there was some free time to mess around with stuff. You weren't necessarily stuck in a plant full time. You think about all those stories, the Dale Earnhardts of the world said, I'm not going to go do the textile thing. I'm going to go race a car, make it happen. That is completely unique in the timeline of Earth till right now. And if you think about like that timeline, however long you want to make it, it's a micro spot on the timeline, and we're getting to enjoy it.
Absolutely.
The random luck of that, like we happen to fall onto the planet at the, at me much more recently than these two, clearly. But you get
I'll say that I think you're right. I agree with you that timeline extends to now, because if you think about it, what additive manufacturing, 3D printing, and those kind of things, the material technologies. I mean, the reality is, working with the guys at Southwest Research, that Peter Lee and that group down there, they literally in the last 18 months invented a brand new coating technology that could potentially change how we look at running in any surfaces. Well, that's now. So all these things, in fact, to get ahead of the game a little bit here, there's a reason why we drew that line right around 1990. It's because that's when CNC started to come in. Because that's going to be another ball game.
Yep.
So they weren't just arbitrary timelines here.
No, there's some real to it. And he called it a magic time. And it was a magic time because he could go from kind of nothing to this amazing world champion. Yeah, but it wasn't too long ago that Roy Johnson took Alan. Alan's like, I want to go race pro stock. And Roy got a whole lot of people working together, and a guy who used his line mechanic became, pro stock championship team owner, right? So, it was a magic time, and then it was a magic time. There are people out there that can make this era a magic time for them. They just have to find something and just grab hold to it.
Yeah,
absolutely.
It's amazing.
And the technology is available.
Yes.
And little things just like installing bushings so that your lifter geometry and performance is better is something that you can do. And here's a video that will show you how.
Hey, Ryan Thompson from Rottler Manufacturing here. I'm with Embry Herrick of CNC Blockworks here in Piney Flats, Tennessee, and we are talking today about the how and the why of lifter bushings and lifter boring, right?
Good to see you.
Good to see you too. Good to be back.
Yes, great.
We're here at the F69 LS block. These guys.
Keyway lifter bore bushings.
Yep, and you've been doing a good amount of them.
Yes, we have.
It's been a process. You've developed the recipe, your recipe, and found different tooling, and we've all worked together.
Sure.
But start this off for the folks and for me. I mean, why are we doing it?
Well, I kind of put it in perspective with when you index your camshaft in, you have to know exactly between the crankshaft degrees and the camshaft degrees. Well, it's the same thing with the lifters. If the lifters are kicked, not centered, in different positions throughout the whole block, you lose that tune, that fine tuning that you need. So you need to know exactly where they are, where they're located, and that's not going to become a problem in the future too. So that's kind of why we do it.
Yeah, and we have the unique opportunity with modern technology, F69 and CNCs, and we were just having this conversation this morning.
Yes.
And you get your print, right? And we have blueprint values, and you can look that up in the spec.
Right.
And it's very easy to say, well, that's just it, and that's all in. And we don't even think about, well, where the heck is all this stuff actually lying in here, right?
Right.
And the machine gives us numbers, and we can use our probe here, and we can compare, and that's exactly what we want to do, because sometimes it's pretty astonishing just how different it is, even a factory block, even something that's new, something it's not, because everything has tolerances.
Sure.
And as I always say, everything had a tolerance to begin with and was within that tolerance, and then it wore out, and now it's way more out of tolerance. So
we see that quite often with the LS aluminum blocks, especially because of everybody wants to push them, a little harder, a little faster. So,
well, and the horsepower out of all engines, it's just
sure.
I mean, 1,000 horsepower engines seem to
be pretty easy.
Every shop I go to, they go,
20 years ago, that wasn't easy to accomplish, but today it's gotten much easier to do.
Right. So with that, all the components, and to get to that level, I think is something that you just said. The geometry and where it is in the block and the angle that these lifter bores are at really, really matters.
It does. It does.
The longevity of the engine, we talk about it all the time with the honing stuff, and getting a straight and true and round bore and getting the friction out of the system is what gives you longevity and gives you power.
And you got to also have the correct clearance between the bore of the lifter and the lifter itself, and that improves on, how do you want to say it, leakage of the lifter, especially on hydraulics. And if you can correct that, now's the perfect time to correct it.
Perfect opportunity, and that's what we're doing. We're correcting. Let's go ahead. So we typed in some numbers here, and we'll just let this probe, because it's always fun to watch a machine run on the video,
yes,
right? So on here on the left, you got the blueprint. I know it'll be tough to see on camera, but let's just go to the blueprint side. So those are all the numbers you typed in, and then And then for the location on the in-out, the programming, where this Y location is, we had all the numbers. We were just talking about this.
Yes. We always use the dial area for the cylinder head gasket, and there's a specific, and then for the Y-axis we use from the center of the crankshaft to the center of the camshaft.
And we can get these specs, right?
We can get these specs because we have what on the machine is called calculator in and out, and there's where you put your distance between the two, and it finds the automatic Y for you of the center of the camshaft itself, which makes it really nice.
Pretty intuitive, actually. It's typing in numbers.
Right.
You know, and you know, I know I've shared with you, like I say, when you're doing things with manual equipment, manual machines, and as an operator, you're very much focused on where this ththing is going and how much do I turn this and that feel.
Right.
And you know, we were talking this morning. You're like, yeah, you're looking at numbers on the screen, trying to, because you're so focused sometimes on the theory and the application, what you're doing behind it, that you go like, what am I even doing? Yeah. Because you're so. But that's the beauty of it, right? You have intuitive software. You have a machine that assists you and alleviates some of that, you know, mundane task, that you can sit here, have these conversations, and focus on what you're actually creating.
Right. Yes, you can.
So the process we're doing here, and kind of the recipe you have is like you said, picking up that dowel pin hole. We zero out, we let this thing probe, and we're going to see here in a moment just how different these locations are compared. And then we have, you know, the choice and the ability to then correct and move that, assuming we have material, and that's why we want to go and put these guys in, right?
And one of the things it does too is it takes 4 positions, so it's basically 12, 9, 6, and 3.
Right.
And it comes across, and it will actually give you a diameter of the lifter and or the lifter bore itself, and you'll see a variances of 1,000ths or more, depending on.
Yeah, just from
probing.
Yeah.
And
to collect that much data that fast, I mean.
Oh yeah, I mean even when you do the cylinders on the thing, it's the same way. It goes, oh lordy, which is incredible about the machine. And I assume too is what it'll do is that after this one, it's got a set where it'll roll over and do the right bank also. So you're going to get a complete basic print of exactly where everything is located.
So this is the first step in the process. I know we have some tools here, and we can you know, hold these up. Starting with this guy normally, right?
Right.
Rough the material out, long end mill.
Right. Yeah, you can very easily with this. This is actually the tool we use for clearancing for crankshaft stroker clearancing. But yes, and we've actually got a tool built that say we're putting in a lifter bore sleeve, and it's an inch 060. It'll rough it out, and even if we're going to do like the 9/30 seconds lifter in the thing, we've got a roughing tool that'll just go from the 842 setting up to within 10,000ths of it, and then we finish out from that point. Okay. It's just to speed the process up.
Just to speed it up.
Right, correct.
Because otherwise you'd be taking.
Oh yeah, if you do that away,
yeah,
a single point cutter like this, and to do that, you can't take a tremendous amount of material because it's fragile. You know, it just won't take it. But unless you run it super slow, but.
So we run that first, right? And then you're switching over to that, like you said, that single point cutter.
Yes.
Talk to me a little bit about this. Now I know this is, you know, pretty unique lifter bore tooling, and obviously Rottler's packaging this to us, and you have a hydraulic holder on here, which I always think is fantastic because the run out and clamp force of that is
it's much better.
Than a collet or a set screw style holder. But this is your finish guy. So normally you're saying you're taking 10 thou and that's your finish pass?
Yes, and what we do is we set up the lifter bore tool for checking the diameters, the clearances and everything. And then like we'll try to get it within 5,000ths, and then we'll either cut it to finish size, or we'll leave a couple of like 1,000ths left, and we'll use the diamonds and hone it out that way.
Use the diamonds just to get that absolute if you have to. And this has quite a pretty good adjustment on it, right? You're adjusting down to the 10th here.
Oh yes.
Right on the machine, so you can check. You can bore that first one, check it, and then make an adjustment right here, and as you go, because like you said, things are fragile and it's quite a few holes.
Right.
The insert is going to wear out, and thermal expansion happens, and you are still. But as the operator, you focus on that, pause, and take your time, and let the machine just repeat. Right.
Let it do itself.
And yeah, I mean, you want to control, because anything, we're doing press fits here. Usually you're probably putting 5,000ths on there or so?
We put a little less than that on. Aluminum, we're a little tighter, than that part of it. So, but yes, we put a little less.
But again, like anything with a press fit, finishing with that single point and controlling that finish, or even using stones to get it, because once it's pressed in, I mean, all the heat's got to go through that, right?
That's true. That is true. So we had one customer that he did a one of a kind. It was an LS and a cast on version, and the block came with no hose in it. So we had to build a program in the machine to tell it where to go.
Go from scratch.
Off of a blank or billet camshaft, and it'll do it. You punch your hole, you go to finish, you push your sleeves in, finish them out, and
of course that's the final step. We have these mandrels. I mean, and these are keyed, right? You slip your guy on there and make sure she's flat, and then the nice thing is boy, you already got the whole location. You just put them on that, and you just keep loading these on.
It's going to press every one of them to the desired.
The height, and it indexes these keyed ones, which is so critical, because the other way to do that is jigs bolted on one at a time.
Forever.
It's forever, right?
Yes.
So, I mean, the time savings and the ability to sit here and have a conversation while it does things.
That's true.
Let's take a look at so we just finished up probing. If we go over to our probe values here, and we've got that difference number in there. So tell me what you're seeing there. I mean,
well, this is a little bit over 14 thousandths from the factory specs,
and we're 17 off in Y.
In the Y-axis. So it's telling me that at some point in time, and it's consistent. This is one of the things you can look at too. And this is on the left side. We're consistently the same off all the way down the line until it gets to the end. We'll go to the other side, and you'll see it's consistently off, pretty close to. That's common with factory cut blocks.
Is it?
Yeah. So it's nothing out of the ordinary. And
I mean, 15 thousandths just sounds like a lot, but
it is.
Is that kind of normal for what you see in the?
Yeah, it is. I mean, I've seen them well. And the one thing too that we're looking at in this particular block is this is supposed to be a 802 or 842 lifter, and we're at 844.1, 845.3, 857, 846.2, and it's just getting bigger and bigger. And on the right side, it's pretty much staying fairly consistent. So already you can tell as you go down the line on this particular block that it's the lifter's housings or bores are actually so loose that they're creating a problem.
And when you see that, so you're getting a story, you're putting it in your head there of what maybe could have happened with the applications of the ceramic. So you see numbers enough and you go, well, that was a factory block where this is worn out. You're seeing things that are oversized, and you can see that really quick and begin to put together.
Yes.
What's this been through, and how good or bad was it really being ran?
It's not that bad, but at the same time, there is room for improvement. Yeah. And you know well as I do, anytime that we can get everything mechanically sound and online, then it's going to duplicate to the efficiency of the motor, whether for fuel efficiency or horsepower or whatever. Mm-hmm. So it does.
And wrapping it up and correcting this, I mean, you have the opportunity here now.
Right.
And it's the combination of what the process here, the machine being able to give you this data quickly and be able to say, oh, okay, I can shift this here, I can do that, I can put things back to get those efficiencies out.
Sure.
And I think, the biggest part I would say with CNCs is the fixturing.
Yes.
And here we're in that ideal state. We're on the mains and we're using that cam locator.
Yes.
And we're precision fit. And if you're doing these things through and through, you have that opportunity to make the main geometry right, make the cam geometry right, and then get all your bores right, and get these lifter bores right at the same time. You're doing, truly blueprinting the whole thing and using the right datums and the right tooling to get the best product.
Right, yes.
So
it's good.
Well, I appreciate it, Embry.
Thank you, sir. Appreciate you anytime. Come back, visit us.
You know it.
Coming down the stretch here, day 2 of Engine Performance Expo. We started the day with Darren Morgan, an amazing presentation, but we got to learn a little bit more about this person.
Absolutely.
So hidden horsepower on location. He's like, what am I doing here? We're going to learn about you and how you got to this point. And kind of a conversation that Darren and I just had. I would love for you to tell Lake what you told me about your experience here at Engine Performance Expo.
You know, a lot of times at PRI, we're beseeched by new products, and you spend all day just traveling around, but you don't get a lot of time to talk to people. And here I've gotten so many great ideas and exchanged information with people, like-minded people, you know, and I've heard more good ideas here than I've heard at PRI in the last 10 years.
That's a sound bite. Okay, we'll use that one.
I hope somebody is actually marking these down, because there was like 4 really great ones over the past. But it is.
It gives us time to network and work and talk. Literally sit down and talk with people.
There is a kind of a frantic feel to the PRI show, and it's great and it serves its purpose. But this is like the after party. A month later, almost, get back together and reconvene. But we had some conversations about, you know, back in school, where'd you get the bug? Cars, mechanics, all of these things. What interested you?
I was forced into it against my will.
Really?
Yeah.
Okay, we're interested.
Yeah, you're the first one.
My father was a drag racer, of course, and 70s, raced AHRA, you know, and I have 8mm silent movies from the 1976 Winter Nationals at Beeline Dragway. You know, and I was a little what we call a pit rat back then, running around all the top fuel teams, grabbing, you know, souvenirs
Stickers.
And whatever. Yeah, I was that kid, and I'm sure that a lot of people my age grew up that way. But my stepfather, Kip Martin, is the person who had a race shop, and he taught my brother and I how to build engines, how to think about engines, more importantly, and. Then
were you willing though? Like in that moment, where did the transition? Because teenage kids, they don't seem to want to do anything.
18, 20 years old, you're chasing other things. You know? You're out partying and doing other things, so you're not serious. And in '91, I think it was 24, 5, 6, somewhere in there. We started working for a pro stock team, Gary Herman's pro stock team, and that was my first, you know. Pro stock engine I'd ever seen. So after a year, we actually had good qualifying runs. You know, we were qualifying 5 or 6. It came too easy, of course. You know, I didn't understand the perseverance and the level of commitment it literally took, because I was relying on, at the time, my stepfather's experience and the other people on the team's experience. And we had good success, but at that point, something clicked in me, and that's all I ever wanted to do. So it's normally aspirated, unlimited engines like that. So after that, I went to work for Madcap, which was V. Gaines for a while on his pro stock team. And then Bob Glidden, and then I was with Larry Morgan's operation for 6 years. And then I went to Rare Morrison for 24 years. So that's literally all I did for 22 years, was find power at any cost, meaning 80, 100-hour work weeks, meaning it doesn't matter how much money you make, the engine's power and the end result of the team is the only goal. And I was ate up with it completely. I loved every second of it.
It is the most addictive thing ever.
Yeah.
It really is. I can attest to that. When there's unlimited
when you're on that dyno at 3 a.m. in the morning and you can barely keep your eyes open and you gain 2 horsepower, you're wide awake.
Yeah, and you don't sleep for 2 more days.
Yeah.
That's exciting. The time at Rare and Morrison, you referenced it a little bit earlier. We were off camera, but we were talking about Lee Shepard.
Yeah.
And you mentioned the moment that you realized you were sitting at Lee's desk. Can you share that with us?
I grew up, I got my first flow bench at 20. So, and you know, I had no idea what I was doing. You know, you're flying in the dark. You have no experience. So I looked up, as many other people did, to Lee Shepard. You know, he was the man. And I thought, God, if I could only know what he knows, learn what he's learned. And 20 years later, I'm sitting at his desk at Rare Morrison in his office, taking over that whole department. And it hit me. It was like, oh shit, I have some shoes to fill. I have some big shoes to fill. And I just put my head down and started working.
Amazing.
It is. Well, you mentioned somebody else you worked for, but Larry Morgan. So Larry's like one of our favorite people.
Love Larry.
Larry was great to work for. I loved working for Larry.
I think we need to say world champion Larry Morgan because, pro modified world champion this year with Mike Castellana and, of course, Frank. But, how great is that? Back on top.
Mm-hmm. But that's somebody that has that itch, that drive.
Yeah, he's a survivor. He's the type of person that will do anything it takes to work on engines and succeed. Anything.
Yeah. And never count him out.
No.
He keeps on working and going, and I'm sure that's part of your training, right? You couldn't, like Billy said earlier, you can't go to school and learn a lot of this stuff.
No
one
really
teaches
can't.
these things.
You really can't.
It
really comes down to applying yourself to the job and perseverance. Just keep at it, And young people, they come in, and this is the information age. The information is easily obtained, but the application of that information is extremely difficult and perplexed. So, kids come in nowadays where we had to learn every single thing ourselves through trial and error and testing. A lot of that information is readily available to people, but they don't have the insight that from that testing and those experiences that led up to that data. So they're missing a huge part.
It's data without perspective.
Exactly. So young kids nowadays, if you want to get into this, by God, if you have a dream, go do it. But just remember one thing, you're going to have a lot of perseverance, a lot of trial and error. Keep your head down, keep working. 10 years from now, you're going to look up and say, wow, I can't believe how far I've come.
Reminds me of Ed Morrell sitting here yesterday. Actually, Ed was sitting where you're sitting right now yesterday, and he was talking about that he went to work for this gear company, and he was hired as an engineer, and he's thinking he's going to go this way, and 2 weeks in, the maintenance guy quits. The next thing he knows, he's now maintaining and working on all these pieces of equipment. But he said it was the best thing for me because I had to learn how all these machines worked and the processes to make the parts. And so he ended up understanding the process that led to the product so that when it got to be the time where he needed to be in charge of making the product, he had the data, but he also had the perspective now.
When I asked my stepfather, I said, I want to learn how to do this. He goes, sure, I'll teach you. I'm not going to pay you, but I will teach you. That FICA, you get your, how much you paid into the system. Well, I have 3 years with 000. And it was the best paid education I ever got. I started tearing down greasy blocks and cleaning out the oil galleries and getting everything crack checked. And then a year later, I moved on to the rods and then mill. And then it was 6 to 8 months per machine. And once you mastered that machine, my father would move me on to another machine. And then after 4 or 5 years, I could do everything in the shop myself. And then after that, we got a flow bench. He saw the flow bench, played with it for a couple of days, said, screw that noise, it's all yours. And I climbed on and never climbed off.
Amazing.
That's crazy.
No, it's a great story. Spent a lot of time in pro stock. Now working, we just did the whole Dodge Hemi Challenge, and that's a mind blower. If you missed it, go back and watch. Any desire to get back into the pro stock fights once again?
Of course. But it's a different world now. There are a lot of things with the pro stock now. Back then we had a lot of sponsorship and a lot of time. And at one point at Rare Morrison, we had 13 pro stock engines in rotation and 2 rental customers at $26,000 a race. Now it sounds like a lot of money, but it's not. The amount of man hours it takes to do 10 major engines and 3 spares is immense when you have 5 to 6 guys only working on that pro stock team. So what happens is you need that R&D time to keep building power. You have to gain 10, 15 horsepower a year or you're going to get left in the dust. So now you spend all your time developing engines to rent out to fund your existence. Your R&D falls behind. People start kicking your butt. Your rental customers leave. You go back to work on the R&D schedule, get more power, they come back, and it's this vicious cycle. Well, those days are long gone.
Yeah, that sounds about right.
Yeah. we need a third power factory in pro stock, or fourth.
Yeah.
Or fifth.
Well, what's
anybody
nice
out
is
there.
now that you're with BES and Tony, those guys, you're getting to do a whole bunch of other things.
I've kind of gone back to my roots, I guess you would say, because I'm dealing with a whole bunch of a variety of engine platforms, and I love it. I enjoy it. And I don't know if a pro stock team offered me a position, I don't really think at this point in my life I would probably take it, because I'm having so much fun doing everything else.
It's funny, I at the grocery store the other day, right before New Year's, I passed by a guy that was one of the engineers, former engineer at Joe Gibbs Racing. We got to chat a little bit, and we both said, it was the best. I would never trade a second of the time we spent doing that, but I wouldn't go back and do it again right now.
And I don't know if I have the physicality to do that anymore.
No chance.
I mean, I'm 59 years old, and that many hours a week, I don't know if I could do that.
And that's it. It's nonstop. All right, so we have got to get Darren on a full episode of Hidden Horsepower. Audio podcast available, Apple Podcasts, Spotify, SoundCloud, because not everybody can watch the screen.
That's true.
There's a lot of audio only folks, and we're gonna go a little more in depth on concepts and different issues. This one is kind of an abbreviated version.
Yeah, exactly. So what we've got coming up next is something that's pretty interesting, because we talk about honing, and we're going to come talk about your project Pontiac in a little bit.
Darren loved these, by the way.
These are awesome.
These are fantastic. What's neat about those, so these are all these surface finishes on freshly honed blocks. But what does that surface finish do? How does it look? How much does it change once the engine has run? And we're going to show you that right now. Longevity of your engine. But how much does it change? How precise do we need to be? How much do we need to worry about things like RPK, those peaks that are left from the honing process? Well, we're gonna find out. We have this brand new block right here that's just been honed. It's one of my dad's old Ford C3 NASCAR blocks, and we're gonna be doing a piston ring coating test. So guess what? It's the perfect opportunity to measure it before we put it together. And then once we have the short block together, but before we put on the cylinder heads, we're going to measure the surface finish again to see how much it changed. And then once we complete that first set of coating testings, our baseline coating test, we're going to take the engine apart and we're going to measure it again after initial break-in. So we're going to be able to show you as honed, after assembly, and then after break-in. So stay tuned, this is going to be fun. So this is the block that Greg Anderson honed. We'll actually leave a link to that video in the description box below, so if you want to check out the honing process, you can go see that. So what this process delivered, we can actually measure it with the profilometer, this really cool tool that drops right in here. If you don't know what a profilometer is, there's a little diamond tip stylus that actually drags across the surface of the cylinder bore. Some people even call it like a digital fingernail. It's a pretty great device. It can measure to a millionth of an inch. And it's going to give us this trace that's going to show us exactly what that cylinder finish looks like. And the great part is it can see that you have all the valleys down there to hold the oil, and then it's got those little bit of peaks on top. Those peaks are what we're kind of going to be studying here. How much do those peaks change from the hone to assembly and then post break-in? What we don't want to see is those valleys change that much, or the core roughness, because that's what's going to be holding the load. We want to see this nice plateaued finish we have here. Now, in terms of the numbers, the RPK, that's the peak height. The RK, that's the core roughness. The RVK, that's the valley depth that holds the oil. So on our RPK, we're right at 10 microinches right now. We're at 39 microinches on the RK, and then our RVK is 69 microinches, which we kind of like this idea of this finish, a little bit deeper valley to hold more oil. That way it seals better, especially when you put more fuel to the engine. That's really important because the fuel is trying to wash away the oil, and that oil is the gasket and the lubricant between the piston ring and the cylinder wall. So good longevity, good seal. You need to have enough oil at the right place, the right time, and the right amount. And that's what this engineered surface finish is all about. So let's go ahead and put in the crank and the rods, turn this thing over. It's gonna be kind of curious to see how much those numbers change, if any at all, just from putting the engine together. Okay, so we have the short block together. Once you put it together, you can't really measure it. So we're gonna simulate running the valves. We're gonna turn the engine over several times. Then we're gonna measure it again. So let's see what happens. Up and down she goes, you hear her moving. And you can see it working. So I can't wait to see what this actually shows us. All right, let's measure it and see what we find out. Okay, so we've put the engine together. We've turned it over several times to simulate running the valves, getting the engine assembled, because obviously you can't measure it after it's already been assembled. But before I decided to put the profilometer here, I decided to put the paper towel in there just to clean it off. Look at how much stuff came off. This cylinder was perfectly white glove clean before we put the piston in and before we turned it all over. This is how much has come off just that cylinder just from putting it together and turning it over a few times. So let's put the profilometer in there and see if it tells us if there's any difference in that surface finish. Again, the little cool tool, let's just drop it right in here. That same cylinder we had measured previously. Now, with that located, come over here and hit go. So now that diamond stylus is dragging across that bore, and we'll be able to see if there's any change in the surface finish just from the assembly process. So what we see are the peaks beginning to round off a little bit, but you're beginning to see a little bit of change in that trace. So what will be really interesting to see is what the microscope says. All right, so our handy dandy USB microscope will go right in here where the profilometer is. So all we have to do is remove the profilometer, put it away. USB microscope goes right to that same spot we were just looking at. And now on the screen, we can pull it up and see what we've got. And right off the bat, you can see how much clearer the surface is. Where before there was a lot more white area where there was roughness, we're seeing that come down a little bit, and that's just the ring beginning to wear in that cylinder, knocking those peaks down a little bit. Yeah, crosshatch angle hasn't changed, right at 30 degrees like it's supposed to be, because it shouldn't change. All right, so the really cool thing is going to be is to check these with the camera and the profilometer after break-in. The last time you saw this engine, we had it on the assembly stand and had checked the cylinder bore surface finish to see how much it had changed between just honing it and basically just putting it together. Well, now it's been on the dyno. It's been through a 30-minute break-in. It's had 10 power runs made on it. Now it's completely back apart again, back on the engine stand, profilometers in there, and guess what? Those peaks had come down. And with the microscope, we've been able to look in the cylinder bore and we can see that fuzz has started to go away. We saw that fuzz from the honing process. It started to go away as we put in the rings and assembled the engine. Now, just after that little bit of dyno break-in time, they're all pretty much gone. And now we have those deep valleys still. That's the key. The profilometer is letting us know we still have those deep valleys to hold the oil. We still have enough RK to support the load. That way we have plenty of oil to both lubricate and to seal. That's what we got. So now we can know you don't need to worry too much about what those peak numbers are. It's kind of like Goldilocks and the Three Bears. You don't want too much, you don't want too little, you want it just right, But the nice thing is you have a pretty wide margin of error there with those peaks. They could be as low as 7, they could be as high as 14, or maybe even 21 like on this engine, and realize they're going to come right down, come right in just through the assembly and the initial break-in. The key is you want to make sure you have the right amount of RK and RVK. That way you got proper lubrication and ring seal.
We are back at the Rottler F69. Myself, Jolie Woods, Lake Speed, a little Project Pontiac update. Jolie's going to give us a little insight into what went down so far, but we had planned on being on the honing machine at this point in the day.
We had, right, that was why we had the honing video queued up right before this about the surface finish before and after, because we were going to lead into honing your block. But reality is we're missing something critically important to be able to do that job.
Well, exactly. You don't do nearly 100 episodes of the Hidden Horsepower podcast without knowing that you need a torque plate.
Like honing 101.
Own a profilometer, hone with a torque plate. And the bore on this particular block was larger than any of the plates that we had nearby and available. Fortunately, David Butler is across town, Pontiac guru. He's sending one down along with a set of the studs that we're going to need for our Edelbrock cylinder heads. So that will get taken care of tomorrow, and we will still be on schedule. But we just missed the shot of the honing, which is a little bit of a bummer. But now Jolie is going to tell us, like, what was this experience like? What did you guys do? You working with Dave Bullock, who works at Wilkins Racing Engines, worked at Roush Yates back in the day. It was great to watch you guys work together. We've been talking all weekend long about information exchange, how these guys want to transfer their knowledge to the next generation. You just experienced it, so why don't you tell us what happened?
Dave has been amazing. So personally, this is a brand new experience for me. I ran a honing machine last year at Engine Performance Expo 2023. It was wonderful. I loved it. I was invited back this year to work on what I thought was just a normal Pontiac block. Then I was told when I got here that this block has a lot of history behind it. So
considerable pressure.
Yeah.
Pressure on. This was not some ordinary engine for an ordinary person. Continue. I'm joking.
So I helped Dave do the lifter bores and the cam tunnel, and it was a very, very new experience for me. I came in completely blind to this, and I came out with a lot more knowledge, and I realized this is a lot funner than I thought it was going to be.
That's awesome. So everything, we see all the holes and everything looks like it's in the right place, but you used the F69 to find out that it was not, and you had to correct it.
Right. So one side of the cam tunnel was, if I remember correctly, 37 thousandths out of place.
That's a lot.
That's a lot. So Dave and I, we came up with a couple things, and we used a vertical bore, and we pretty much evened it all out. Then we did a line boring to get the inside holes that the vertical bore can't get to.
That is amazing, and thank you.
Thank you.
Most importantly, thank you. And I was checking in the whole time. For the amount of time it's on the machine versus the amount of time spent making sure it's on the machine right.
Oh my goodness, yes.
Talk a little bit about that.
I was thinking, with the amazing Rottler machines, you can have a full conversation while the machine is running. I'm no stranger to that. Well, I didn't realize how much time and effort it took setting up the motor. It takes almost more time setting the motor up to be honed or bored or whatever than it does actually making the process of it. So it takes a lot of time and delicacy and patience that I didn't think it was going to require.
Interesting. Lake, how cool is this?
Well, it's amazing because it is so true that if you just throw it in there, it'll make a hole. It'll be
won't
round,
be the right one.
It's straight, but it's going to be the wrong place, right?
Right.
And that's the
sure.
key thing. And so I think one, having somebody like Dave that's a master craftsman actually to be able to teach is pretty cool.
He is incredible.
And you got the double throwdown, right? So you got spoiled rotten here. You got the great teacher and the great equipment. You can never go back.
Exactly.
Right. Now you're roped into this, right? You've done this
100%.
twice now, so you're part of the crew now. This is neat because again we've been talking about that next generation and handing it down, and here you are doing this. That big iron's got nothing on her. She's crushing it. I see the chips everywhere. But you've done a good job with this. I mean, and I think it works out nice too, because now that we've got everything correct, you can feel confident about putting it in the home tomorrow and getting the surface finish done and completing every step of the process, however long it takes. I know you had to go back and do a couple of passes on the Ultra boards,
yes,
right?
sir. So it took a lot of passes to get it right where it needed to be, because when it comes to machining, as you know, you can't slack off. You can't leave just that bit of room because you don't have the time or you don't want to do it. It has to be right there. Has to be that exact number, or else you're going to have a lot of problems.
Yep. Yeah, however long it takes is how long it takes to get it right. That's the whole thing. It's like, how long is this job going to be? Well, however long it takes to do it right is the answer. And the same thing. If we could have honed it today, because we had all the tools, we would have honed it today. But we didn't have all the tools, so guess what? We didn't hone it today. We didn't cut corners. One, we love you.
We're not going to cut the corners.
We're just not going to do right.
I'm against cutting the corners. I did talk to John Kazi, but it's like, I could have figured out a way. Thank you, John. But no, we're gonna continue away. I think it's great. I'm thrilled. I told everybody, like, I felt nervous. There was anxiety because this is mine. I know how much it means to me and how much help is going in. I think it's awesome that you were involved and you got to use this as a learning experience. But since we are engine, we're trying to bring in the next generation. Why do you like this, Jolie? Why is this where you want to be? And I'm looking around, I don't see too many other 16-year-olds. We don't need hundreds of them. We need a couple of them, though. Why is this fun? And I hope you're talking to the parents of other younger people who might encourage their children to do this because of what you're about to say. What do you think?
So, my dad grew up in a machine shop, and I've grown up around racing. I've been racing ever since before I could walk. And I've always been really interested in it, but I've been particularly interested as to why. Why does it go fast? Why is this motor better than another? And I was given the amazing opportunity by Straub and Rottler to come here to the Engine Performance Expo last year and actually see why and how, and get to ask the questions to the right people and get to learn why these motors do what they do and how. And I encourage everybody, my age, older, younger, whoever, that this is a crazy field that we need more people in. It really is.
That's exciting. It's exciting to hear you say
that. You
that.
asked the right question.
Yeah.
It's the why. Not the what.
It's the why.
And isn't understanding the why so much fun?
It is. It honestly is, because when you grow up in racing and you hear these terms, you eventually understand what they mean, but you don't understand how they become to be or how the process works. So this was an amazing opportunity to see just that.
Excellent stuff.
Pull it all together, right?
Pull it all together.
Well, speaking of pulling it all together, we're going to kind of pull it all together. We are in the last lap of the Engine Performance Expo, and we've got my dad in the race car getting ready to go back to the racetrack. Okay, Engine Performance Expo viewers, the last time you saw this block, it was in the hone at Straub Technologies. This is the one that we scuffed the pistons before. We had 3 scuffed pistons. One was really bad. We got it all cleaned up within 3 thousandths. We were able to save 5 pistons. We got 3 new pistons from the guys at CP. Used line-to-line skirt coating on all 8 pistons. New rings, new hone. The guys here at PME put the engine back together. So now, that's where we are. We're in the dyno cell at Pro Motor Engines in North Carolina. We're gonna run it and let's see how she runs with this new hone with that line-to-line skirt coating. See how it does blow-by-wise, and we'll show you the results.
so that's last time, just to check ourselves. That's yesterday. That's right now. How about that?
That's pretty good.
Do one more just to make sure. Look at that.
So now we're at 32 degrees timing with the VP Q16 with the big carburetor. Let's see what kind of number she makes.
There we go. All right, here we go. 32 degrees, baby. Bring it up. Look at that pickup right there, baby.
Woohoo! $791. Wow, that's a huge gain. This engine, when we first found it last year, it had been rebuilt 20 years ago and just sitting in the shop, it made 733. All we did was hone it. New rings, new pistons. Of course, we went from old school full round piston, old school type hone, old school piston rings, 043, 15, 3 millimeter. Went to a modern 0.7, 0.72 millimeter. We put little bitty lateral gas ports in the piston. We put gas ports in the rings. We doubled them up. We did all that. We changed the fuel. We changed the carburetor. That, just those changes, was basically 60 horsepower. This thing is making a little bit more vacuum than it did before, so I'm gonna say job done. Both of Dad's engines, both Ford C3 engines, we did the complete rehaul on it before with valve train, pistons, rings, hone. This time, we let the valve train alone. We just changed the hone, the rings, the pistons. Both times we put the carburetor on there. Both times we put the oxygenated Q16 fuel. So definitely the carburetor's worth some power. The fuel is worth some power. But my gosh, using the Rottler H85 to get the cylinder bore geometry and surface finish just dialed in, using the thinner total seal piston rings, using those CP Ford side relief pistons, even the line-to-line skirt coating, that entire package, man, that's worth at least 40 to 50 of all of this. It's pretty nuts how much power we were able to gain just by making a few small changes. I mean, same block, heads, cranks, rods, cams, rockers, springs. All this stuff is literally 20-something years old, and it just made 791 horsepower. Hey, but that's why you watch the Engine Performance Expo, is because we're showing you how to make big power the easy ways. Not everything has to be the trick of the week. Sometimes it's about just doing the fundamentals, blocking and tackling, right home, right ring gaps, all those little things all add up to big gains. So I can't thank Dennis and all the guys here at ProMotor enough for helping us with this project. This is super cool. Can't wait to get this one in Dad's car and get him back on the racetrack.
Hi, I'm Jesse with Engine Pro, and I'm sitting here with Alan, who is our product manager for Engine Pro products. Today we want to talk about Engine Pro racing valves and give you an explanation why they're most premium valve offering in the marketplace. So Alan, tell us what the differences are between our different offerings.
Yeah, so we've got 4 different series of valves. Starts out with our 1000 series. This is a 21-2N stainless steel. It's a high purity stainless steel made to US standards. This is a great valve for your street strip applications. If you're building for something maybe like a naturally aspirated dirt track or asphalt, maybe one of the entry-level late models, let's say. There's classes that have a cam lift rule, maybe sportsman drag racing. This is a great valve for that. Beyond that, we step up to the 2000 series, and in that you get a material change to a 21-4N. The difference there is the 4N has double the nickel content of the 21-2N, so it adds a lot of toughness and more wear resistance because of the higher nickel content. So if you're building something that's a serious effort, maximum effort racing engine, anything up to and including professional racing, that's the valve that you would go for. One of the other differences that I'll mention too is that the 2000 series valve is actually swirl polished, whereas the 1000 series is not. So then from there we move up to the 3000 series, which is the nitro black, and we give it that name because of the 5-step salt bath nitriding process that we put these valves through. And this is actually a surface treatment. It's not a coating. It's a metallurgical treatment that embeds right into the material of the valve. So the benefit of that black nitriding really is that it's 21% smoother than hard chrome, which these other two are hard chrome, by the way. So the smoother finish is going to lead to less valve wear, less guide wear, and it's also harder for carbon to start sticking on the backside of the valve.
Well, especially with the tight tolerances that are involved here too.
Very
that
very much.
Smoothness and durability is incredibly important, right?
It does make a big difference, especially if you're talking like an endurance engine, something that let's say an offshore boat, where it's really going to see extreme temperatures and extreme power levels for extended period of time. That's where you can see the difference within that. So beyond that, we have a 4000 series, which I don't have an example here, but the 4000 series is really the same as the 3000 series. It's also a nitro black valve, but those are specific to diesel applications. So the intake valve is basically the same set of features. The difference is on the exhaust valves. The exhaust valves, because it's for diesels, they're a bimetal Inconel valve with a stellite facing on them. So that's kind of your basic rundown of the.
So that gives it a little more tolerance to heat then?
The Inconel stands up to heat better than stainless steel does. Yeah.
Well, what makes a quality valve?
So there's really 3 things. I mean, material, like we've talked about, but tolerancing is extremely important, and concentricity is very important. So for example, we use a fixture like this to check for concentricity. And the reason that's important is that if the head of the valve is not concentric to the stem of the valve, you run into all kinds of problems. So what's going to happen is that valve, as it goes to the seat, it's not going to seal correctly all the way around its circumference. What it's going to do is it's going to hit off to one side. That can put a bending force into the valve, which that's harder on the stem. Also, it's going to start shoving the stem over into the guide, so you're going to get more guide wear from that. And that's not to mention the sealing problems that you get, because it's not seated correctly. You're going to have vacuum loss, and you could actually be bleeding off some compression in there as well. So concentricity is really, of all of it, the most important thing to have right, and that's what I think that our nitro black valve does better than anybody else.
And again, these are all made in the same plant.
Yeah, exactly right. There's a single plant that is not in Asia, by the way, and all they make are racing valves. And they have some of the strictest quality control processes in the world.
So they're made to American standards.
Yep, the material is American spec. The standards are all American quality standards. Yes, all of that.
How does our material or our valve compare to the competitors in the marketplace?
Well, from our own research, just using fixtures like this, we've gone out and bought all those valves, and we've compared them to ours. And just with the results that we've seen, we have better consistency in both the margin and the concentricity than any other valve on the market. The nitro black valve is just, we really feel it's the best valve on the market today.
So obviously, just looking at a valve, they all look the same. So how can you tell you're getting a genuine Engine Pro valve?
And that's a great question, because there are a couple of other black valves on the market. And the way you tell you're getting a genuine Engine Pro valve is you'll see the Engine Pro logo is etched right on the head of the valve.
All right, well, thanks a lot for this deep dive into Engine Pro racing valves.
My pleasure.
For more information, go out to enginepro.com and check out some of the videos that are linked to this. They'll give you a little more in-depth explanation of the processes and the quality specs on these valves. Thanks for your attention.
The final roundtable of Engine Performance Expo 2024. I wanted to break into Europe. It's the final countdown, but I spared you guys because you don't want to hear that.
Thanks, Joe.
But you're very welcome. You're very welcome. Pim is back. Chris is back. Joe Woods. Oh my goodness. We got to talk to you in a second. And of course, Randy Neal back late. Jo Lee is Joe's daughter, for those that don't know. Hopefully you do know. How proud are you right now, Dad?
Man, I don't know that I can wipe the smile off. To be honest with you, you know, when I had 3 girls, I wasn't sure if I was ever going to have a car nut, you know. And she was 6 years old going down the side of my Z28 with a wrench, dink, 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 dink. And I'm underneath it thinking, no, that's paint. But
money.
I mean, to be honest with you, that whole time that was happening, I remembered myself in the bed of a Chevy truck doing the same thing with a little ball peen hammer. So, yeah, couldn't be happier.
Amazing.
Could not be happier.
No, she did a great job and looks highly motivated to continue the journey, which is exciting.
Very. I wasn't sure. You know, I mean, kids get in things, kids get out of things, and she's, for those that don't know, when we do the MPK stuff, I don't touch the valve train. She runs the valve, she warms the car up in the mornings, I take care of the bottom end, she takes care of the top. So she has taken it serious and wants more responsibility every time we go out. So I just keep feeding it to her.
Wow, that's the way you do it.
Well, she impressed everybody last year with her ability to pick up and run that machine. That was super impressive.
Yeah.
To be able to take that, beginning off with the other machine, which was fly cutting, that was nice, but to run that F69, that's a big daddy machine right there.
That's a big deal.
Doing this kind of work, the level of complexity in line boring a cam tunnel, that's not just nothing.
No, it's not.
That's not beginning entry-level machine shop class right there.
No, it's not.
And to pick it up like that and to be able to relate back, and she carries herself well. Hats off to Mom and Dad. Did a good job on that one.
Thank you. She, I may or may not have added a little bit of pressure because I informed her where that engine was going. But, the reality is it's no different being his engine, my engine, her own personal engine. Jimmy, Joe, Bob down the street. It doesn't matter. You have to look at all of them exactly the same, just like they're your own.
We're building this massive pressure around Project Pontiac. It's not that big a deal, except no, it is when everybody gets in to help out. The feeling of the day when it happens that I roll to the starting line, it's going to be crazy. Randy, you're always talking about bringing in the next generation and all this knowledge that has been acquired and passing it along. We're seeing it happen.
Amazing. That's the best way. Kudos again, Mom and Dad. You guys have got the crown. Not the poster boy, she's the poster girl, if you will. But the point is, she has validated the opportunities by young people to get into the trade. And getting immediate rewards. Your success is obvious, but she is just, I can't think of anybody that's been here with all the men and everybody here. Every single person goes, really? Are you kidding me? Now, that's what we're after. We, as a group, understand our next generation. We have to sit there and dedicate to that. It's nice to see someone, especially 16, come on, really? This is just, I had to sit down and rethink this thing. She is good.
Yeah.
Now, she's the poster girl. Here we go. And I think that's what we're going to do with this thing. We're going to have a little fun with that. I can see a poster coming. So the deal is, I think this is just showing the young people that there's something available. And we always do what we love, fair enough. I mean, we're all here, we're gearheads. This is in our DNA.
Yep.
Well, the new generation, I got to tell you, we got a lot of opportunities here. And she, once again, is vindicating and validating, I should say. And for all you young people out there, here's a start. Ask any of us. Ask anybody who was here. We'll mentor you. We'll help you. Just ask. You'll be amazed what kind of career you can work yourself into.
Yeah, it was great stuff. And what did she say? Like, what was great about this? She said it was fun.
Yeah.
She didn't say, and as much as it's important to earn money in your career and have a successful business and keep the race teams moving forward, what was good about this? It was fun. And I think that's an underlying, my job is fun. Nobody says that. It's probably, people don't think you're working.
Right.
But it is. I know when I go to work, I have a good time. And Chris Straub looks like he has a pretty good time when he comes in.
Well, I love what I do. So, this is not work. I love what I do. And to add to, I had the Tumanella family come down. Customers.
Mm-hmm.
This is my problem. Become friends. Drag race family, 3 generations. David's here. The son, who we nicknamed Crew Chief years ago when he's 9 years old, same age as Jolie. And they came down, picked their motor up. We just got done with it. And he has, and his dad, mom, and his brother. Sorry.
That's good, man.
Been here the last 2 days, and I told Frank, his dad, I said, if he wants to come down this summer, come down. And he has stood at every machine, watched it go on. So, to listen to Keith Dorton and where he came from and how he got into it at age 16, 17 and stuff, Jolie and David are the future.
Yeah.
Absolutely.
Well, to me, this is the culmination, Chris. 4 years ago, we sat here and we did this, and we were vision casting, hoping that one day these young people would show up, and in 4 years, they're already here.
Yeah.
That next generation.
It is so cool to see that. Yeah. And the beauty is the interaction. You can interact with anybody, from people that are, TV stars, Brian Tooley Racing, Brian. Nicest guy.
Tell your Brian Tooley story.
So I had never met him. I hung out with a sales guy. We had dinner with his whole crew at SEMA or at PRI, and I walk up and I see his logo on his shirt. I say, "Oh, Brian Tooley. So are you the local rep for Tennessee?" And he looks at me and goes like, "No, I'm Brian Tooley." I'm like, "Oh, oops." But he took it. He took it very well, and so now he is the Tennessee rep in my eyes, and so they're going to call him from now on. But it was, that's the interaction we had here. It's so cool. And so for the younger guys to come in, and gals, and to be able to get that opportunity, it is priceless. And I can see the emotion, because our industry, unfortunately, it's aged. Yeah. And to get new kids into it and be able to, when you walk them into a machine shop, or and it's dirty, it's work, it's hands-on, and not everybody is for that. But when you get one, you need to nurture that and grow it, because there's a beautiful future in this.
Well, and Jolie and David know it's hard work, because they're working with their dads and stuff.
Yeah, they see.
And it's and again, can you make a decent living in this industry? Yes, but you have to have the passion. You have to have the love, and to see their age come in, because hey, we're all going to be we're going to leave this earth whenever he decides, but we need them to carry it on.
Yeah, and it's amazing. What blows me away is that the shops that are good at it are all overwhelmed with the amount of work they get.
Yes,
absolutely.
Yeah, and so you get young people and you train them and you make them good, and they know what they're doing and they know how to repair that stuff. And I don't care whether it's a race motor or just a motor or an old motorcycle. that is a trait that is, people don't want to do the work anymore, but they want the results.
Yeah.
And so if you get good people that are good, capable with the equipment available to them, can make this, put these together and create a good working engine, or restoring or racing, it's a beautiful, well-paid future, I guarantee you, because you're one of the few.
Let me pick up on that. WJ, first time we ever had him up here, he made a statement to all of us. He says, you do realize that we've arrived at an era where our technology has arrived, that you can come in this trade, learn it well, but you can make the equivalent of equal to doctors. Now,
Yes.
you say, well, that's a stretch. No, it's not.
No, it's not. I agree with you 100%.
That's right.
Yeah.
The opportunity, some people are motivated by money. We're motivated by, well, I'm not sure yet sometimes. I have to figure
We're
that
still
one out.
motivated by a little money. Yeah.
But here we go. And at the end of the day, Warren's statement is absolute truth. See, a lot of the guys, the young generation, they are certainly motivated. They're told they don't want to sit there and work for minimums. You don't have to work for minimums. Yeah. What you do have to pay is pay the rite of passage.
Yes.
You do have to come in and honor the teacher, and you have to reward them with efficiency. But you know what? The cycle of life here is they will move on and you will move up.
Yeah.
But you start, like every trip, it starts with the first step. First step is come talk to us. Let us show you. Not hearsay, we got facts. Just come on.
Listening to you guys speak about it, and I'm really lucky because I get to see people at their best. They want to race. First of all, they're at a racetrack doing what they love, period. Okay. And then I get to interview them after they just won a big race and they're having a historic life moment that they worked their whole lives to achieve. And I get to be a part of that moment all the time. So that's always great. But I think about parents out there, and you mentioned a doctor, and that was like, we're on the same wavelength right now. What do parents want their kids to grow up to be? What jobs do parents want their kids to have? What are the jobs? Well, everybody wants their kids to be financially stable and comfortable. So it's like, doctors, lawyers. But you think about those professions and what they're dealing with, and we need doctors. Lawyers, but sorry, lawyers. I got plenty of friends with law degrees.
I second that opinion.
Right, but you got to have it sometimes. But this is an admirable profession. It's absolutely necessary. It's connected to national security. You have to have people who know how to do what you guys do. Yes, we're doing it for fun, to make power, to go racing, but that knowledge can be used for so many other things in an important time of need. Someone has to know how to do this. So who's it going to be? You guys make money, you do what you're your own captain of your own ship, you're handling it, watching Jolie at the machine, controlling her own thing, not sitting at a desk pushing a piece of paper over and back. Yeah. I think parents should feel comfortable and happy if their child wanted to enter this profession.
Sure.
And the timing's perfect because there are so many shop owners that are at that age. They're looking to hand the baton. They're just looking for someone to open their hand. They're, like you said, they're willing to pour themselves into someone that just is willing to be available and open and learn.
That is so true. I have an example in our hometown. I've got a small machine shop. The guy is a motorcycle repair guy. He restores old motorcycles, and it's a fully operational shop. I guarantee you, if he had somebody he could train and hand it off to, he would. I mean, he says, "I'll walk away from this." If I have somebody that I can hand it off to, and that is often, you look around our industry, a lot of our customers, they're very good at what they do, but at the end they kind of lose that interest because they don't have anybody to hand it off to. If they don't have it, you don't see that passion in their eyes. Yeah. And if they were to have somebody young that would be interested, that would be willing to take that over, that would be willing to put in the time, it's rite of passage. Very good saying.
The buy-in.
Yeah.
Let's be clear about it. When I got started, I had 2 nickels and they were both borrowed. Right? So the way we went through it is just we plowed our way through. We worked and everything. So we evolved. Now, there's a lot of companies that are out there that are successful, but they have no legacy dynamic.
Yeah.
And the guys sort of potential waste away. For the young people out there, you got to simply understand. Solicit it. Go out and just say, hey, can I be part of this? Now, I started by sweeping floors.
Same.
Right.
That's exactly
Oh,
what I was sweeping the floor just to get the knowledge.
I was learning mechanics, and I walked up to a small shop, and I said, I'll come in Saturdays and work for free. Whatever you have me do, I just want to learn. And he's like, because I'm not hiring. I said, I don't want you to hire me. Just have me work here. I'll sweep the floor. I'll do whatever you want. And I started there. And I still today, I remember the first days of crawling under a car and doing stuff for him. Installed LP gas installations at the time. This is back in Europe. So,
but the bottom line is, this is not a blacksmith industry. This is a high technical industry.
Yeah.
We are so totally different. And so the technology is right up their wavelength. These are the ones that are, hey, I can sign on. Matter of fact, they can take some of these guys that are in there and they're, I don't want to touch it. Wait a minute, let the kid in there. Let him show you. Now, the owner will sit there and say, cool, I'm motivated. I want to see next gen. Work your way through. Pay the rite of passage. Let's be fair with that. Don't think that this guy's going to say, here's the keys, got to go. No. Learn. Make sure you take it. But you now have the resources. Technology has come your way. Man, I've never seen in my lifetime such a nice opportunity. You know, people talk about degrees. I'm okay with that. I don't have a problem with education. I like education. But education, I can find everything you ever want to know is already in a book. It's already on the shelf. All you got to do is take the initiative, open it. So let's do this. Just go in and ask that guy, can I open your book? Can you teach me? You'd be surprised how you can manifest this into, quite frankly, you are, as you said, captain of your own ship. Man, what an opportunity. I never had that.
And as a shop owner, you know, we appreciate what Rottler has done as far as technology. We appreciate what CWT has done for technology. We appreciate what United Engine Machine and Icon Pistons. You know, that having vendors like yourself, manufacturers of equipment, to be able to give us the ability to produce the products that we do and keeping up with the generations. I mean, there isn't, you know, kids today, they don't know what an amber bulb or an analog screen is, but they know what a touch screen is. You know, so for Joe Lee or David, you know, they can look at that touch screen and they say, oh, well, yeah, I can do that. Boom, boom, boom. I mean, when it comes down to it, they've been raised with a flat screen ever since they were young. And for the boys and girls, it's almost like a video game. Yeah. You know, the machine becomes, can you break Tetris or whatever that kid just did the other day?
First kid ever think about that.
Can we get Joe's block absolutely perfect? It's a puzzle that we've got to make perfect. And if you look at it that way, and at the end of the day, it's a cool thing because we get to make guys like this go fast.
Right. Speaking of which, by the way, good job saving the day on the Joe's block.
Hey, listen, I did not save the day. Shout out to David Butler and the boys at Butler Performance. I'm not going to say what size bore Joe's block is. Let's just say it's a very large bore. I don't want his competition catching up with him. But I shouted out to David, and I said I need a torque plate, and he said, well, and I said, listen, you get it to me Saturday, we'll have it back. I'll ship it back Monday. Perfect. I said, by the way, you got a set of head studs for Pontiac. Of course, Mr. Pontiac had the head studs. And of course, this block's got a special head stud. David had it on the shelf. So David Butler and boys, thank you. I will get that back to you on Monday. I promise you, sir. Excellent. And shout out to Joe Stefanici, Steph's Performance. When I worked for Joe 3 years ago, or several years ago, I shouldn't say 3 years ago. Hell, I just turned 55 last year or last week. Joe said, Chris, it's not what you know, it's who you know in this industry. And that right there saved us probably almost 10 days. So,
absolutely. And while I'm, handing out kudos, of course, how about Mr. Lake Speed Jr. over there? Engine Builder Hall of Fame. A year ago in this moment, in this round table, I think it was at this round table, you're like, yeah, there should be an Engine Builder Hall of Fame. And boom, 1 year later, first 8, go into the hall. Everybody's talking about it. Everybody's buzzing about it. We're seeing, Scooter talk about Bob Glidden, revealing all these amazing stories. You did all of that. Like the lion's share of the work. You don't want credit, of course. Definitely doesn't want credit. Nobody wants credit.
I can't take the credit. I mean, really, Billy really should get the most credit here because him and John Callie's really work together to help define that matrix. Because that was the whole thing we talked about yesterday that we set it up. It can't be a popularity contest. It can't be, well, who has the most trophies? Billy's words were perfect on that. You won the race.
Yeah.
They gave you the trophy for that. That's your reward. This has to be something that is that enduring legacy. And that really came from Billy and John Callies and Scooter and those guys, created that. And then fortunately we were enough, we had to kind of keep Ed Pink out of the loop on him being in, right? Because we didn't want Ed to know we were putting that in, because Ed was one of the guys, Ron Shaver, Jeff Smith. So we had a really great group of people that were all contributing, and we would get these Zoom meetings and stuff. That's one great thing about technology, right? Yeah, guys from all around the country, we could Zoom in and we could chat about these things and have these discussions and argue back and forth about this guy and that guy and this and that. And it was wonderful to have that initial thing. And we were like, okay, you knew it was right when you had everyone kind of looking at each other kind of like we are now, and they're like, yeah, this is it. This is the equation. This is what it looks like. And then we were able to kind of say, okay, well, now we have the idea of what it looks like. Let's litmus test it. Let's take the popular people and start plugging them in. Do they fit? And the ones that everyone had agreed on would fit. The ones that we didn't agree on didn't fit. And that may rub some people the wrong way. I'm okay with that. Because it can't be for everybody. It can't, because if it's everybody, it means nothing. But if we can maintain that, we'll build on it year over year. Obviously we played all the videos from all 8 inductees for the first year, today and yesterday. And what we'll do is, there's a website that'll be coming out, enginebuilderhalloffame.com. We'll be live in a couple of days, ebhof.com for short. Saves you some typing. And then each week for the next 8 weeks, a page for each of those persons will be unveiled with that embedded video and an extended bio and other assets. And I can't thank all the sponsors. I mean, Pim, you guys at UEM stepped up to help out. Obviously, I
thought it was a privilege. Honestly, it's a privilege.
I twisted Hartford's arm and said we're in, right? And then Chris Douglas, Mark Campbell, and all the guys at Comp and Edelbrock, they stepped up so we would have that initial group. But we couldn't do it without AAM and Chris and everybody, Randy, everybody here, the folks at Rottler, without the Engine Performance Expo as the launching point to build that and support it. It's just a collaborative effort. And yes, I am extremely proud of the work that we've done, and I'm glad that as an industry, just like Project Pontiac, we all came together and contributed and created a 401c3 nonprofit. This isn't about money, it's about honoring the legacy of the people that made this possible.
Yeah. Amazing. Just a question, and I don't know the answer. From here on out, inaugural classes are usually the biggest class. How many people go into the Engine Builder Hall of Fame each year? Is it 4?
We will maintain 8, so 2 from each category for at least the first 5 years.
Okay. It's like they have a plan and everything.
Yeah.
Kind of do.
Have you ever seen Lake Speed's schedule?
Yeah.
I mean, it is an Excel every day. There is a plan. I can do.
You may not know the plan. You may unveil it in the last minute, but there is a master plan
Still formulating
somewhere in the background.
There's a plan. No, that's great. That was a big part of it, and those videos were awesome. Can't wait to watch them online. So where do we go from here?
That's a great question. I mean, the one wonderful thing, circling back to earlier discussion here, is that we start off with this idea that we needed to create this platform that could inspire, encourage, and bring in the next generation so we could pass that torch. Right. And we're beginning to see some benefits from that. Well, I think the next part of that is, okay, you showed interest, but what's the next step of that? Is now empowering. So I think we need to continue to really double down on the educational parts, right? It's great to give them vision, but now you got to set them in the right path and give them the tools to move forward, to take those steps,
and look at the tools that they have today.
Right.
Yeah.
I mean, honestly, I learned on an old Stuart Warner balancing machine, right? Strobe light and a gauge, and you were hand grinding valve seats. And I mean, the Rottler equipment will do in 2 hours what it would take you 2 days to do the old way. Yeah. Where's it gonna go? I mean, you give kids that age, I mean, we have the entire world's library on our cell phone.
Yep.
Right? So you give them the digital technology and the ability, where are they going to take engines? Where are they going to take race cars? Of all platforms.
Yeah, we're just scratching the
We're
surface.
just beginning.
Yeah.
And that's the truth. It's just beginning. The next level that they go to is going to be extreme.
That is our salvation, next generation. We have an obligation to pass along. The bottom line is, and like you say, everything we're about, the entire EPE program has been education. Awareness, though. We're trying to let people know this is the path. Look, it's a great path. It's a clean path. It's a fun path. Your daughter's, I can't say enough there. I wish I could put it in the right words what I see from that young lady. But that is just that nice little flashing light that says we have hope.
Yeah.
I am thrilled to death to see this, and I hope any young person out there, come on, I'm being redundant. Purposely, I want you to understand, we want you to come talk to us. You are, bottom line, our salvation. End of story.
Yeah, there's got to be someone to take over the reins.
Absolutely.
There has to be.
Well, I'll say this. Just thinking about this interaction, like you said, the digital age and growing up and stuff. If you like playing Minecraft, you're going to like these motors because you can dream up these worlds in Minecraft and you can make it. The digital tools that are available today allow you to dream up a motor and make it. And you'll get your hands just about as dirty as you do playing Minecraft. And that's fair.
Yeah.
Especially with additive manufacturing and what's coming in, the ability to draw these parts, model them, test them virtually before you actually make them. There's never been a better time to get into this industry that I've ever seen.
And when all that's over with, there's nothing like a 1 second 60 foot time.
There is Jan 20.
No, is that what you did, the 60 foot?
No, that's my goal.
Okay.
That's my goal.
But like a sub 1 second 60 foot time. Like that will get your attention.
200 mile an hour.
Playing Fortnite is awesome, I'm sure. And I love video games as much as anything. But there's nothing like when that transbrake lets loose and all of a sudden you are in full motion in a tenth of a second.
And you see that at every NHRA national event. Because when you go to one of those races, there's every different kind of person under the sun there. Different ages and stuff.
Yep.
And what happens the moment the first fuel car does a burnout? The pits are empty.
Yep.
Everyone comes to the starting line because there ain't nothing in the world like seeing two fuel cars go down that racetrack. Whether you're into cars or not, that is impressive.
Incredible machines. And this year we've got this young rookie driver going to jump into Top Fuel for the first time. Upstart named Tony Stewart. It's like really like
Some
this
kid.
he came from some other forms of racing, his background in different styles of racing, but he's going to try to run Top Fuel for a championship. So much to be excited about here at the start of the season.
Well, that's going to be tons of fun to watch.
Oh yeah. Because he's been nice, Tony, till now. Like I'm out having
a
good
you're
time.
right. Exactly.
Having a good time. Suddenly,
competitive Tony's going to come out.
Don't you think?
Oh, absolutely. Tony the Tiger. Tony that got, all the NASCAR guys scruffled up, that guy's showing up.
It's got to happen.
Not the nice Tiger.
No, yeah.
It's got to happen. And others, others. I don't want to oversell any one of our great storylines, but no, I'm real excited about what's going to happen here in 2024. And hopefully people will come to the racetrack, whether it be a round track, whether it be the drags, whether it be their local track, go see you guys. Get out there in person, though, I think is a message that, those of us on the media side, we put fans in the stands, racers want to race. That means they're going to need engine builders and engine balancers and the cycle, the virtuous cycle of racing. It really comes down to the people who want to see this.
Yeah, whatever it is, it'd be a dirt track, drift, it doesn't matter. Formula One, there's 3 Formula One races in the United States now.
Yes.
How incredible is that?
Amazing.
And so now is the greatest time to go because the technology is there. There's opportunity of every different type. The diversity of motorsports available right now is unlike any time ever before. So go to your local racetrack, So I think we need, speaking of going to your local racetrack, you know what? It's time for us to close it down. We are in the final minute or two of the Engine Performance Expo. And Joe, I know you got a lot ahead of you on the schedule this year. And like we were just saying a minute ago, that the next thing is to empower, to educate. So there's some opportunities for both of those things coming up this year.
Yeah, education doesn't stop here at the Engine Performance Expo. It's just getting started. For instance, when I go out to the Mission Foods Drag Racing Series this year, I know in the Total Seal Pit, we're going to have some more trackside tech talks for stock and super stock racers, for race fans, for engine builders. You want to be in or around a pro stock pit and see and hear the lessons of all of these engine experts. You can come out and be there and be a part of it. It comes along with the price of your ticket. We're going to do that at a couple of races. Of course, NHRA starts in March at the Gator Nationals.
And we will have a Total Seal Trackside Tech Talk at the Gator Nationals. So we open the year with that first educational opportunity. As we mentioned earlier today, there's educational opportunity classes, the hands-on honing classes. That first one's going to be March 16th at EFI University. We also have the Advanced Valve Train Development class. Again, EFI101.com is going to have both of those available on there. But then, again, all these videos. I know this was an incredible amount to take in, and there's actually a catalog. There's 3 previous years, 4 episodes of these before. You can go back and watch them at any time. So we just keep adding and growing and going, which is why we do the Engine Performance Expo.
And thank you all for all the effort on Project Pontiac. You can follow that story on my WFO radio podcast and live stream. We'll be talking about it throughout the year. What's going to happen? I don't know, but I feel like I really do kind of know.
Oh, yeah.
Yeah, it's going to turn out okay. Lake, take us home.
All right. So, again, thank you, everyone, for tuning in and watching the Engine Performance Expo. Make sure you tune in so you can stay tuned up.